Welcome to my Pygame platformer tutorial where I will be covering the basics of Pygame and quickly ramping up into creating a full platformer game where you're a ninja who can run, dash, jump, and wall jump around while fighting enemies and beating levels. If you don't know who I am DaFluffyPotato. I've been working with Pygame for over a decade. I've released 2 Steam games with it, won multiple game jams, and just won the graphics category of the last Ludum Dare with Pygame. This tutorial is for anyone who has a decent understanding of Python. I expect you to understand the basics including lists, dictionaries, and a bit of object-oriented programming. If you're not comfortable with object-oriented programming, you can check out my old Pygame Tutorial Series where I did the whole thing without it. Whether you're brand new to Pygame or you just know the basics and you want to learn more, this tutorial is for you. We'll start with the basics and work our way up to some advanced topics like level editing, visual effects systems, AI, and more. As you follow this tutorial, there will be several breakpoints for which I've uploaded the project files to a resource page for. There will be a link to this page on screen and in the description. This means that if you make a mistake, you'll have a working reference to figure out what went wrong with. Additionally, all of the resources, code, art, sounds, music, etc. for this tutorial are released under the public domain. You can use them for whatever you want and even make something you'll sell with them. Before we get into Pygame, I'd like to give you some tips on getting the most out of this tutorial. The overwhelming majority of people will learn significantly better through experience and experimentation than by just listening. It's important to be coding along with me in some sense during the tutorial. It doesn't have to be the exact same thing, but making something will help you both understand the topics and remember them. It would be a shame if you sat through 7 hours of a tutorial and then forgot all of it the next day. Also, it's important to not just copy what I'm doing. If you're following along, it's important to periodically pause the video and try changing the code I write to do various things to ensure you understand what I'm doing and how it might be used for other purposes. Tutorials are most valuable of a learning experience when you learn to apply them to a broader use case than the specific topic being covered. Now let's get a bit into Pygame. So what is Pygame? Well, in technical terms, it's the Python wrapper for SDL. SDL is a media library widely used with C++ and C to make games and other applications. In other words, Pygame is the adaptation of SDL to Python. If you're curious for more details, I have a video dedicated to the more technical overview of how Pygame works and its implications titled Pygame's Performance: What You Need to Know. The important thing to understand is that Pygame is actually considered a pretty low-level way to make games. There is no such thing as an animation, a camera, or even a player. We have to code all these things ourselves, and I'll be showing you how in this tutorial. Pygame gives us user input, and we have to create a window and generate every frame of the game primarily by just telling it where to put specific images on the screen. This approach has upsides and downsides. It's an incredible learning experience that teaches you things that are very useful in the software engineering field. In my case, I've found that lots of my experience with Pygame translated very well into being able to work on rockets and flight simulators as a software engineer. Additionally, working at this level gives you a high degree of control over how things work, and once you've developed the basics, you can reuse things you've already made to enable you to develop games rather quickly. My performance in game jams can attest to the fact that you can compete with people using game engines when you're using Pygame. The downside is that the initial learning curve is steep, and the initial progress can be slower than using a game engine. So if all of that sounds good to you, it's time to get started by installing Pygame. To install Pygame, you need to use Python's package manager, pip, to install just the package Pygame. Funny enough, there's a recent fork in Pygame because of some open source drama stuff. I have another video about that if you want to look into it. So there's actually 2 versions. There's the original one, which is just Pygame, and then there's another one, which is Pygame CE. I've been using CE lately, and at the moment, I think that's the better option. I'll keep the pinned comment updated with what I recommended. For this tutorial series though, I will be using CE. At the moment, there's not too much of a difference between them. All of the stuff that I'm covering in this tutorial will work in both versions of Pygame. So to install it, like I said, you need to use pip. The way that you would normally do it is just type pip install and then Pygame or Pygame CE. Although the problem is that sometimes it's pip, sometimes it's pip3, sometimes you don't have that bound at all, and you have to do Python pip but then sometimes your Python is not under Python and it could be under Python 3, and funny enough, in my case, it's just under Py. But actually, if you're doing the Python thing in the front, you have to do a -m. That's the Python module, and you're then calling the pip module and telling it to install Pygame. So, like I said, it would be Python 3. If you're on Linux, normally it's going to be Python 3, I think. I would assume it might be the same on Macs, but for Windows, it's all over the place. So just try them all. Something to check is to make sure that you're not using Python 2. So if you just type Python, you can see your version, and you don't want this to be a 2. It needs to be a 3. So in my case, I'm using Py, so I'm going to do py-m pip install Pygame CE. Alright, so it just installed. With that, I can just run the shell by just typing py, and then I can do import Pygame. And then you can see it imported. If you get an error on that import, then it's not installed correctly. It's also possible to get an error when you're installing it. Typically, you're just going to have to Google it. If you get an error while you install it, all sorts of things could have happened. Usually it's because you did something weird with your setup, but for most people, it should install fine. And then if you get the error on the import, it just means it didn't install correctly. If Python, and Python 3, I don't actually have this one. If none of these start the shell for you, you're going to have to find your Python install so that you can actually use that. There's a million things that can go wrong in this part because there's a ton of different ways you could have Python installed. So I can't go too into depth here. A lot of this stuff is kind of just general installing packages with Python type stuff. So if you run into issues, you can just Google it. Anyways, with Pygame installed, it's time to go ahead and create our very first window. All right, so I'm just in a folder that just has the assets in it for the project. I'll get into those later, and there'll be a link to those assets in the description so that you can follow along. But for this first step in making the window, you don't need those to begin with. So let's go ahead here and just create a new file, and then we'll call it game.py. So the very first thing you're going to have to do is just import Pygame. And then after that, the next step is to do a pygame.init. This will start up Pygame. After we initialize Pygame, we can create the screen or the window or whatever you want to call it really. So we can just name our variable screen, we can call it window. I like to use screen. I don't know where I got this from. I think I found it in some example code like 10 years ago, and I just kept using it ever since. But we'll set that to pygame.display, and then we'll do .setMode. So this is a bit of a misleading function. This is actually the function that creates the window, kind of. For some reason, it's called setMode. There are technical reasons for that, but it's a little bit confusing. The next argument is going to be the resolution, and we pass that as a tuple. So I'll say 640 by 480. That's the resolution of our window in pixels. So just this function call here will create our window, and then this is kind of the handle for a window so that we can draw onto it. The next thing we'll need is a clock. The use of this is for forcing the game to run at 60 FPS, because normally if you run code, it'll just run as fast as possible. But in games, you might want to restrict that because you're running a lot of stuff in a loop. Every frame is its own iteration in the game loop. So if you ran it as fast as possible, you would like max out your CPU and just your fans would go brr and stuff like that. So that's not ideal. So a lot of times you don't want to run it at the maximum frame rate. Another thing worth noting is that normally you would use something called delta time, which is the difference between the time in the frames, in order to just kind of change how fast things are moving and stuff like that to adjust for frame rate. We're not going to get into that in this tutorial. I'm going to work with a fixed frame rate because it's a lot easier mathematically. So that's another reason to try to set up something so that we can restrict the frame rate to 60 FPS. So for the clock, as you can see, tab 9 suggesting here, which is pygame.time.clock. So that will instantiate a clock object, and then we can use that for a couple things. The next step is to create the game loop. So the idea is that, as I mentioned, in a game, each frame is an iteration in a loop. And in that loop, Some games will have multiple loops running at the same time, like maybe one for rendering and one for physics and stuff like that. But in our case, we're going to do it all in one loop, and every loop you'll have to update everything, and then you'll have to put it onto the screen, and then you'll finally update the screen at the end so that the user can see it, and then you go to the next frame. So the idea is that games run in a continuous loop, and you're just constantly working with changing data, and the main thing that affects that data is the input that the player gives, which you also pick up in that loop. So to do this, we'll just do a while true, so that's an infinite loop. And then in here, we can do a pygame.display.update. This will update the display. So we can draw onto the screen, but until we actually call this function to update the display, we won't see anything changing. By default, the screen's just going to be black. So if I don't call this function, you're just going to get a black screen. And then after this, we'll want to do clock.tick 60, and that's for 60 FPS. So this will force this loop to run at 60 FPS. So this function in itself is effectively just a dynamic sleep. It'll sleep for however long it needs to maintain that 60 FPS. There's other stuff the clock can do, but we won't need any of that for this tutorial. Alright, so the next step is to get the input. If you were to run the code right now, a window would pop up and it would work, but we don't want that because in SDL, you have full control over the input handling. If you don't ask for the input, Windows will think you're not taking input. And if Windows thinks you're not taking input as an application, it doesn't matter if you're updating the screen. It will think that the application has stopped responding, and it'll do that thing where it grays out and gives you the spinny thing on your cursor, and it'll ask the user if you wanted to shut it down. So to prevent that, we have to get all of our events and then process them in some sort of way. So we can do a for event in pygame.event.get. So pygame.event.get is what gets the input, and this is where it kind of interacts with Windows and gets that user input so that the thing doesn't freeze. And then in here, we can do something with our input. It can be whatever we want. An event is just like, it could be a button press, it could be someone clicking the mouse, it could be someone even moving the mouse. I think there's some touch type events and other weird things that can happen. There's events for like resizing the window. There's all sorts of stuff. So the way this is structured is that the event will have a type attribute that specifies what type of event it is. So we can do if event.type, and it's suggesting it here is pygame.quit. So the pygame.quit type just means that you click the X on the window. So believe it or not, we actually have to code the part where you click X on the window and it closes. So to do that, we do a pygame.quit, and we can do a sys.exit. Sys.exit will just kind of exit the application. For that, we need to import sys up here. Pygame.quit will just close Pygame. So you need both of them. Anyways, we should have our window now. Here we go. This is our window. We can drag it around, and I can click X, and it will close. And that's all that is so far. One more thing that we might want to do, if you notice, the window name is Pygame window. We might not want that. So let's go ahead and change the window caption. We can do pygame.display.setCaption, and we'll say Ninja Game, and that's the name of our game, I guess. And if I run it again, it now says Ninja Game. You can also change this icon here in the top left, but I won't really get into that in this tutorial because it's not super important. Anyways, it's time to give you a bit of a tour of some of the assets that I have prepared for this tutorial. I will link them in the description. It'll just be a zip file you can download. Just make sure you have it set up the way I do, where it's just a folder, and then you drop the data folder inside that other folder, and then the game script is right next to the assets folder. So inside of data, we have a few things. So we have this music file. We have sound effects for a few different types of sounds. We have maps. I'll show you how you can make your own, and then I'll also do the level editor and everything. But I do have these pre-made because they can take a little bit of time to make. If you look in these at the moment, it's JSON if you're not familiar with that format. And it's just a mess of data. You can try to read it if you want. It's not a good idea to try to edit this by hand. That would not be a fun time. That's what level editors are for. Anyways, if we go into images, this is where most of the stuff is. We have things like a background, a gun, a projectile, and then we have other stuff. We have a tiles folder with a bunch of random stuff in it. Like, I think this is a tree. No, that's a crate. Okay, that's flowers. The tree is, I think, this one. Yeah, here's the tree. We also have our tiles right here. So this is like the different grass tiles. I'll show you how to auto tile these as well, so that you can just place some tiles and they'll form with their edges automatically and everything. And here we also have like different types of particles, just a bunch of images. And then we have our different entities. We have a player with a bunch of different animations and like the enemy, and there's a bunch of frames for that animation. And like I said, we'll get into animations later. And then finally there's the clouds. But we'll get into most of that stuff later. For the time being, the main focus is going to be to show you the basics of using Pygame so that we can get started with the project. In order to make a game that's easy to work with in terms of scope, a lot of times it's good to use object-oriented programming so that you can like pass objects around and just get a lot of the other conveniences of object-oriented programming. I probably won't lean all the way into object-oriented programming for this tutorial, but I will use a lot of that functionality. So the very first thing you're going to want to do, which is a common thing, is to make your game its own object. So let's do class game. Def init self, and then in here we might want to do a few different things. So we can take all of this stuff and indent it so that it goes under init, and then we can do self.screen, so that's an attribute of our object. And then the other part of this is going to be the run function. So this is how the game runs. So you can initialize it and run it separately if you want. So we indent that in, and it loops now in its own function. And the only thing is we have to do a self.clock.tick. And then finally, we have to actually initialize our game and run it. So down here we can do game and then .run. So since this will return the object, the .run will just be called on the initialized object. So if we run it, it should be the same. We get the window and everything. And this is an easier form to work with games in. Alright, so let's get started with actually putting an image on the screen. To do that, we use Pygame's pygame.image.load function. So we can do, let's say, self.image equals pygame.image.load, and then you just give it the path as a string for the argument, and then it'll be able to load it. It can do PNG files, JPEGs, and a couple other types, but usually you want to use PNG because it's lossless. So let's do data, images, clouds, cloud1.png. So we're loading one of the cloud images. So with this image loaded, nothing's changed yet. We actually have to put it on the screen. To do that, we use something called the blit function. We do a screen.blit, and we can do self.image, and we can put it wherever. Let's say 100, 100. Actually, this has to be self, but actually let's do 100, 200 so you can see the differences in the dimensions. Alright, so if we run this, you now see a cloud here. If you notice, I put it at 100x and 200y. So the way the coordinate system works is that the top left is 0, 0. This is actually quite different from how you normally have it in math. In math, it would be either the center is 0, 0, or it would be like the bottom left is 0, 0 if you don't want to have negative numbers. And actually, if you get into computer graphics where you're writing shaders, it would be that way. But for Pygame and other non-GPU based rendering techniques, the top left is often 0, 0. And that's, I believe, has something to do with how when we read text, we start in the top left and just kind of in the order of elements. So say you were to make a website and just place a bunch of HTML elements, it would go from the top left. So yeah, we have 100 pixels from the left side of the screen and 200 down from the top. So yeah, as you can see, we have our nice little cloud there. Now that we have our cloud, it would be nice if we could move our cloud. To do that, I'm going to add a couple variables here. So let's say self.image position equals 160, 260. And then we can use that position as the input over here for our blit function. And something interesting about blit is that the idea is that it's just kind of a memory copy. You're copying some section of memory onto another surface. And blit is just the terminology used for that. And you'll notice that I said surface there. So in Pygame, a surface is basically just an image. So the window itself has a surface, which is the main one you render onto. That's the screen. That's a special type of surface. But most surfaces are kind of like this image one, where it's just an image in memory. It's not, doesn't necessarily represent the screen or something like that. So if you wanted, you could do it the other way around, and you could actually blit the screen onto the image because they're both surfaces, but we don't have a reason to do that. You can blit any surface onto another surface and then at a given location, so you're just merging together different images. If you were to actually blit the screen onto our cloud image, it would erase the cloud and replace it with all black because, well, the screen is black by default. One interesting way I've heard to think of this is that you're just kind of making a collage of different images that you're putting onto the screen, and you can put images onto your images and do whatever you want. Alright, so with this image position attribute implemented, let's go ahead and get the movement part working. So let's add a movement variable, self.movement equals false, false. And let's say we want to move our cloud up and down. So we go back to our event loop here. Remember, we get all the events with event.get, and our event has a type. So the type for a button press is if event.type is pygame.keyDown. That means that you pressed some kind of key down. To find out what type of key was pressed for that event, we can do if event.key is pygame. And we'll use k up. So that is the up key. And we'll set self.movement 0 equals true if you press the up key. If event.key is pygame.k down, self.movement 1 equals true. So something interesting to note is that these events are fired when you press or release the keys. They don't necessarily mean that you're like holding it down in that moment. So you're not going to be getting this event every single frame while you're holding it down. So we have to have something to keep track of whether or not it's being held on our end. There are functions that Pygame has for checking if something's being held, but I like to use my own systems for this because it's easier to hook on some extra stuff if you want to change something in the future. Alright, so aside from the key down event, there's also the key up event, which is the same thing except the key was lifted up instead of being pressed down. So we want to switch our movement variables to false. So the way we're doing this is that we have these two booleans here that we're updating based on whether or not the key is held down. So if the first one is true, that means we're holding down the up key. And if the second one is true, that means we're holding down the down key. So with that, we can use that to modify our position here. So we can do self.imagePosition 1 plus equals self.movement 0. Actually, we should do self.movement 1 minus self.movement 0. I'm using an interesting trick here. So booleans technically can be converted to integers implicitly, and that's what I'm doing here. So a true will get converted to a 1, and a false will get converted to a 0. So if we hold down both, we get this adds up to 0. If we hold down just down, it'll add up to 1 because of this one. If we hold down just up, it'll add up to -1. If we do neither, it adds up to 0. So we're able to just kind of calculate how much the position should be changed based on these two booleans. If we wanted, we can change the speed by doing this and like adding a 5, which actually I'll leave that for now. If I run this and I press up and down, we can see the cloud is moving, but we have a weird effect. It seems to be leaving a trail of some kind. And the issue here is that if you recall correctly, the screen is just, as I mentioned, a surface. So we're putting the cloud onto the screen, but we're doing that every frame at a different location if the cloud moves. So we're rendering the cloud on top of the previous render, which already had the cloud rendered. And you do that a bunch of times and you end up with a trail. What you actually have to do is you have to clear the screen after each frame. Usually you'll be generating a whole image from blank screen essentially, and you do have to clear it yourself. So to clear it, I'm going to do a screen.fill, and we want a nice sky color. So we'll do 14,219,248. So .fill will take a color in RGB, so this is the red value, this is the green value, and this is the blue value. So it's a very blue and green color. It'll fill the screen with that color. So anything that was there previously from the last frame will be just completely replaced by a solid color that we just gave it. So if we run this, we now see that we have a cloud. If we move it up and down, we don't get a trail anymore. But now you see there's this black box around it. If you look into our assets and you go to the clouds here, and you open up this image, you can see that it actually does have that black background to it. There's no transparency automatically in it. So what you normally do is you add a color key. There are ways to just use the transparency built into the image, but it's easier usually to have like a background color that you just replace. So in our case, we're going to want to add our color key here. We'll do self.image.set color key, and then we'll say 000. So 000 is the color for pure black. And if you noticed before in the image I showed you, the background was pure black. So we set the color to 000, and that color will be replaced with transparency whenever that image is rendered, or rather that surface is rendered. So the color key allows you to just say that one specific color should be transparent. And now if I run this, you can see there's no black background to our cloud image, and I can move it up and down just as you'd expect. All right, before I get into the next part, which is going to be collisions, there's something else I want to share to you about input. So for this tutorial, I will be using a slightly unpopular, but what I find to be kind of accessible keyboard layout, where we use the arrow keys for movement, and then we use X, and then if we needed another one, C, but we won't for this tutorial, for extra like abilities and stuff. So the idea is that many keyboard layouts will be quite different. So specifically, if you look at WASD, if you go to a different keyboard layout, they're not going to be next to each other anymore. So using the arrow keys for movement is actually quite universal. For example, it works in QWERTY, which is what I'm using. It works in Quartz, and it works in Azerty layouts. So lots of, I think mainly Europeans, are able to play games that use layouts where you have the arrow keys. And the other thing is that for the abilities, like I mentioned, you use X and C a lot. The reason for that is because those two buttons are actually next to each other in all three of those formats I just listed. I think the major format where they're not going to be next to each other is Dvorak, but I don't think there's much you can do about it at that point. There's a reason why a lot of people use X and C. I definitely get a lot of complaints for not having WASD in my games. If you want, you can add it yourself. For example, these keys become like just KW if you want to use that. In the Pygame documentation, there's a whole list of all the keys so that you can just bind it to whatever you want. And one thing you can do is you can actually just support both, so you can have it working with WASD or the arrow keys simultaneously. And that's a common solution as well. So with that out of the way, let's get into collisions. So when I say collisions, I'm talking about collision detection. I'm not talking about there's a wall, you run into it and it stops you. I'm talking about there's an area, you run into it and you know you've collided with that area. So that type of collision detection is the very first step of getting physics implemented. And it's quite simple to do in Pygame. And this is one of the few, I guess, physics-related things that Pygame actually supports, which is just basic rectangle collisions. So here's what we're going to do. We're going to have just kind of a basic area that we can collide with. We'll just call it self.collision area equals pygame.rect. And then we can do, let's say, 50, 50, and let's make it like 300 wide and 50 tall. And then we'll also want a rectangle for our cloud image. So let's do image r equals pygame.rect. And then we can do image position 0, image position 1, and we do image.getWidth, image.getHeight. And this is actually going to be a self on all of these because this is an attribute. All right, so there's actually a shortcut here, which I won't be using in the rest of the tutorial, but I use it when I'm writing code myself, which is to use the splat operator. You can actually do pygame.rect and just splat self.image position and then self.image.getSize, and that will just spread out the arguments, but I won't be using that here because it's something you have to learn that a lot of people don't actually know about Python. If you do know about it, feel free to use it. It's very convenient, but if not, that's also fine. All right, so the pygame.rect function creates a rectangle, which kind of just makes sense based on the name, and that rectangle has a top left position, which is defined by the first two parameters, and then the second two are the width and the height of the rectangle. And remember, the coordinate system is from the top left, and it's just right is positive x, down is positive y. So There's a couple of different things you can do with these rectangles. The basic functions are things like drawing that rectangle onto the screen. You can draw it as like a box, or you can draw it as a filled in rectangle. You can also do the collision detection with them. We'll be doing both here. So right now we have this one rectangle which we don't want to move, that we're just using to test our collisions, and we have our image rectangle, which is created every single frame based on the position of our image. So the position is coming from that position thing right here, and then the size of the rectangle is being pulled from the size of the image, which you can get with get width and get height. So that will create a rectangle that perfectly matches the image that we're rendering here. All right, so now we can do our collision test. We can do if image r.collideRect self.collision area. That means that in this frame, our two rects are overlapping in some way. And what I'll do for that is I'll draw the rectangle, draw.rect, and we'll draw it onto the screen. And let's give it a blue color, a bright-ish blue color, but not the same one as our background. All right, and then we have to pass in the rect that we want to draw. So we want to draw our collision area rect with the color that's like mostly blue and onto the screen. Those are the three arguments of Pygame to draw.rect. And I'm going to copy this. I'm going to say else, and then this is if we're not colliding, we use a different color, which is going to be darker. All right, so if we run the game, you see we have that rectangle up top. We can move our cloud up and down, and if our cloud touches it, it turns to a brighter blue. So you can tell if our cloud is touching that box with that code we just wrote. And this is, as I mentioned, what we will use to do our tile physics and all sorts of other collisions later. All right, so something interesting you may notice here is that the cloud is showing up behind our rectangle. This is probably not ideal for what we're doing here. You would expect to see probably that the cloud is on top of the area we're colliding with, just from a visual standpoint. So the way that layering works in Pygame is that it's purely based on the render order. Remember, you're just kind of copying an image onto another image. So if you happen to copy one image onto another image before you do a different image onto that same location, that second one will cover the first one. So layering is done entirely based on the order that you render stuff onto the surface. If we want the cloud to appear on top of our collision area, we just have to take this code and paste it under the rendering for the collision area. That way this is rendered on top. All right, if we run it again, we can move our cloud up and we can see it's actually on top. So this can create some problems if you have a specific order you want to like update things and render them in. So you might have to do a little bit of problem solving to figure out how you want to implement your rendering orders into your update sequence and stuff like that. It's very common to separate your updates and renders for different objects. So like if you have a class for your player or something, you might want a function for updating it and a function for rendering it, so you could do it separately, and then your update code doesn't have to be reordered if you want to reorder your rendering. Now that we have the basics down, we can get into the crazy stuff that is actually making a game. The first thing we'll probably want is a player. So I'm going to do this in the object-oriented way from the beginning, which hopefully keeps us from having to rework things later. So the way we're going to do this is I'm going to create a new folder and call it scripts, and this is where everything that isn't the main game script will go. So in here I will create an entities script, and this will be responsible for a couple things. So let's just start with a basic entity class. I'm going to call it a physics entity because later on here it will be capable of handling physics. So let's define the initialization function. Let's take the game as a parameter, and that way anything that's in the game is accessible through the entity. This is a bit of a trick you can use to deal with scope issues for games. The weird thing about games compared to other types of programming problems, I guess, is that in games, it's very common for elements to interact with a ton of other elements. Some people handle these interactions through intermediary systems, but that adds more code and in some cases more complexity. It can help keep things organized if you do it that way. But if you're working by yourself, interacting with other things directly is usually a decent way to go. You just have to kind of keep track of things, and if you lose track of things, it might get a little bit tricky to debug stuff. But overall, this is a quick and easy to understand solution for a scope issue. So aside from the reference to the overall game so that it can access everything in the game, we also want to take the entity type. We won't really be using this yet, but we will use it later. We also want to take a position to spawn the entity in, and then we also want a size for the entity. So let's do self.game equals game, and self.eType equals e. Actually, let's just do type. eType. There we go. The reason why I don't want to use just type here is because that's a built-in function, but using it as an attribute is fine. That doesn't override it. Alright, self.position equals position, and actually something interesting to do here is to actually just call the list function on that. It'll convert any iterable into a list, and the reasoning for that is two things. First of all, if you did pass it a list, you don't want to have a reference to that list. Let's say you spawned like 3 entities in the same location, and you passed a list in. So all of those entities could be, and this is a bit of a more complex Python topic, all those entities could be referencing that same list that represents that position. And if one updates it, all of those entities will have their position changed. So you want to make sure that each entity has its own list for its position. The other thing is that if you pass on a tuple, you can't change individual values in a tuple. You have to just update the whole thing. So it's easier to work with lists for a position because you're usually changing the position. Another thing you could be doing is converting those locations into Pygame's vector2s. I won't get into that, but there is a lot of useful functionality there if you want to use that. So let's do self.size equals size, and then we'll make an update function that just gets called every frame, def update, self, and let's take in a movement variable. We'll update these arguments later and add in a tile map for collisions, but for now we just want to do movement. Something else we're going to want is a velocity. So I can do self.velocity. We don't want that. Equals 0, 0. So if you didn't know, the derivative of position is velocity, and the derivative of velocity is acceleration, so the relationships are similar. Velocity is just used to represent the rate of change in the position. So if your velocity is 5 in the x, you'll move like 5 in position in x every frame. And then acceleration, which we will also be using, will be the rate of change in velocity. You'll be updating the velocity every frame a certain amount based on the acceleration. And fortunately for us, our acceleration is going to be constant. It will just be the force of gravity. A lot of people get confused as to how they're supposed to implement like good jumping mechanics, but if you actually just use the physics formulas for how these things are supposed to work, not all of them, but the basic ones for like position, velocity, and acceleration, you can get some pretty good results. In higher level physics systems, a lot of times they will use physical concepts like force and momentum and inertia and all sorts of stuff like that, but we don't have to get into that here. Once you get to that level of physics, a lot of things actually start to feel a little bit clunky if you're not very careful about how you deal with momentum and stuff. So I actually like to work at this kind of simplified physics level. So you get the benefits of nice, smooth movement, but it doesn't feel clunky. Anyways, moving on. From here, we want to generate how much of a movement we want to make for the frame. So frame movement equals movement 0 plus self.velocity 0, movement 1 plus self.velocity 1. So what we're doing here is we're creating just a vector that represents how much the entity should be moved in this frame based on how much we want to force it to move in this particular frame, plus however much there already is in velocity. So you want kind of multiple controls on how things move, which we'll get into later. But for example, the gravity will be applying an acceleration to the velocity, and that velocity will pass through as well to the position. But for example, for moving right and left, you want that to be instantaneous usually, or at least that's what I like it to be. So for that, we use 2 different inputs for movement. So in order to actually move it, we can just do self.position 0 plus equals frame movement 0. Typically when I have a list of 2 values that represents something dimensionally, it's going to be the first one's X and the second one's Y. So position and velocity. Doing this is just updating our X position based on the frame movement, and then we can do the same thing for Y. It's important that these are separate. We'll get into this with the physics later, but you actually do the movement steps in 2 stages. You do one for each dimension. You can actually do this in 3 dimensions if you want, but I'll also get to that later. Anyways, we have our movement working. So now we can do our rendering, self.render, and then we want to take our destination surface, and let's just say surf.blit, and we need an image. I'm just going to write something in and we'll fill it out later. So self.game.assets, and let's just say player, self.position. All right, so we have our physics entity here. Let's go over to game and import it. We also do have to fill out this assets thing. So we can go over here, we can do import scripts.entities. Actually, it's from scripts.entities import just that object. That's all we want from there. And we can just define our player. Self.player equals physics entity, and then just pass in the game. We'll call it player, and let's spawn it at 50/50 and give it a size of 8 by 15. All right, so we have all this other stuff going on here that we don't need anymore. So there's this image loading stuff for the cloud and all that collision stuff. We don't need that anymore. That was just demonstrational. We'll use a lot of those ideas here in a moment, but we don't need that for our actual game here. So in here, we'll want to do a couple things. So we want to do self.player.update, and actually, hold on, there's the movement stuff back here, which we should probably leave. Well, we want this movement variable because that's still taking our input. But for the rest of the stuff, we can do self.player.update, and then we can do the whole movement, self.movement1 minus self.movement0. And then for the second part, we can just throw in 0. We don't want any changes on the y-axis, because if you're in a platformer, you run right and left, not up and down. So the other part of this is to change these up and down keys to right and left. So we can do right, left. Actually, I think it's the other way around. Right? Yeah. So it's left, right. All right, so just copy these down. And that should do that. Do self.player.render onto self.screen. So the player's rendering, the player's updating, and moving. The only thing is we need to get the assets in. So for this, I'm going to start creating some utility code. So let's call this utils. So in here, we're going to want to create just a basic function. We'll create more functions built on this later for just loading images. So def load image, and we give it a path. And we can say our base image path is data/images. All of our images should be under that folder. So we can do image equals pygame.image.load, and it should be the base image path plus this extra thing that we're giving it. And this is where we'll want to do something new. We want to use .convert on the image. This converts the internal representation of this image in Pygame and makes it more efficient for rendering. A lot of new users forget to do this or don't know about it, and it costs them a lot in performance. So it's important to do this. There's almost no reason not to, so I just do it by default for just about everything. All right, so let's do image.set color key, and then if you remember, all of our backgrounds are black, so black will become transparent. And then we just want to return our image. So we can take this function and use it to start loading stuff. So let's go back over here, and we can do from scripts.utils import, and we want our load image function. So in here, we can finally define that one image that we needed for the player, which is self.assets equals, and then we can do player, and then we can do a load image on entities/player.png. So if you remember, there is that base images path, so that'll go data images, and then we have entities, and we go to player.png, which is this one right here. It's a bit small, but yeah. So if you're a bit lost on how I'm accessing everything from everywhere, I recommend taking a moment to read through everything and make sure you understand how everything's connected. One of the big things that's important to do when you're learning stuff like that is to make sure you fully understand things and one of the best ways to do that is to actually play around with things and see how things work when you start changing stuff. So before moving on, assuming this actually works, so I'm double checking that. I made a mistake here. This is pygame.image.load. And that's why I put that clause that it needs to work. Anyways, so this works. The player can move right and left by just pressing right and left. And we have our character on the screen. It's represented as an object, which is nice. So this is all great. But yeah, as I was saying, it's really good to mess around with things and get a full understanding of how this stuff works by changing stuff and seeing how it interacts. If you just copy everything I'm doing and don't play around with it too much, you're going to get a bit lost. I do recommend if you do end up breaking something and you're not sure where you went wrong, you can go back to the last available reference code that I have on the assets page for this tutorial. So you can always have some baseline that's working while following this. Anyways, so now that we have movement and our player, the next thing is to deal with the fact that we have some pixel art here and it's really small, we can barely see it. So this is where we use an interesting technique. There are multiple ways to do this. Pygame has some built-in stuff for scaling, but you get a little bit more control if you do it yourself. And by do it yourself, I mean what I'm about to get into here. It's a bit slower performance-wise, but it's pretty much a non-issue at this resolution. So we can do self.display equals pygame.surface. And this is another conventional name that I just started using at some point. I think I got this, I don't know if I came up with display or what. I don't know where that came from. But for me, screen's always been kind of the window surface, and then display is the one that I actually render onto. All right. So we have these two surfaces. If you notice, display is half the resolution of the screen. And also I use a new function here, which is the pygame.surface function. Pygame.surface generates an empty surface, so like an empty image. It's like you loaded an image of this dimension using pygame.image.load, except it's all black by default. So just imagine a black image 320 by 240, and that's what Pygame.surface does. This is useful for just creating stuff in memory that you might need for some kind of purpose. In my case, the display is going to be a second surface that we use for rendering. So the idea is to render onto the smaller display and then scale it up to the screen, so that you render on a small resolution and then you scale it up, which creates the pixel art effect. So let's render everything onto this display. To do that, we just swap all this to the display, and then the last step right here, because actually I can show you what happens. You just get a black screen, because now that we're running on the display instead of the screen, you get nothing. So we have to render onto the screen. So screen.blit, and we want to blit the display onto the screen. So if you do this, we now get this. So it's just shrunk. So the next step is to scale it. So this is also something new. We'll do pygame.transform.scale. And the first argument is the surface you want to scale. And the second one is the new size. So what we'll do is self.screen.getSize. So we're scaling this surface to the size of this one. You could pass in like a tuple of any size you want, but it's convenient to just use the get size on the screen here. So the return value of this will be the scaled display, and we can just throw it on the screen, and that's what we're looking for. All right, so now you can see the pixel art has gotten a bit bigger, and it actually looks like pixel art. All right, now this is where things start to get crazy. We're gonna get into tiles and physics. Well, we've already done a little bit of physics in the sense that we've implemented some code for velocity. We're not using it yet, but it is there. So we'll want to create a new tile map script. Tilemap.py is what we'll call it. And in here, we'll want to create a new class. We'll call it tilemap def init. And then we'll want to take like a tile size. We'll say 16. And that 16 is a default value. We'll say our tile size is equal to the tile size. Self.tilemap equals that. And self.offGrid tiles equals this. All right, so what we're doing here is we want two systems of tiles. So we have the tile map, which is where every single tile is on a grid. So it's just a square grid of a bunch of tiles. And then the off-grid tiles are things that we placed all over the place that might not line up with the grid. So the idea is that you can only handle physics with this grid here. It's more convenient to work with. You could add physics here if you wanted, but if you keep stuff on a grid, it's easier to optimize it. So we'll have most of our tiles on this grid in here. And so there's a reason why this one's a dictionary and this one's a list though. So we're going to do something where we map each tile based on its location. If you've done any of this stuff before, you may have seen like an example of a map where you do, say, there's a little hill or something. So if you have a little hill you're mapping, maybe you would do something like this, where you have 3 rows in a list, and your ones represent the ground. So you get a little hill of the ones right here, and there's a slight issue with this approach. Let's say you wanted 2 islands that are far apart. You have to fill in the space between those islands with air. So if a lot of your world is air, you're going to have a lot of wasted space in your setup here. And you also have to go through all of the work of creating that space between the tiles as well. So the approach that I like to use instead of just throwing things into a list, because you can't have 2 elements at different locations without having all of the elements between. The technique I like to use is to create something where you have, let's say, a tile at the location 0, 0, and we say it's like grass or something like that. And maybe a tile at 0, 1 called dirt. And the advantage here is that you could have a tile at 9,999, and that could also be grass. And you don't have to fill in all that space between. So this is really convenient to work with. It's still also very efficient to look up tiles based on location. We'll be using a slightly different strategy here. You can use tuples like this as your location for your tiles, but I will be writing these as strings, so I'll use like 0, 0 or 0, 1 and stuff like that. And that's because of the way the files will get saved. I'll get to that in, I don't know, maybe an hour, but it's a lot easier for this use case to do it as strings because the format we're going to save these in doesn't support tuples. In my own framework, I added a system where I can convert tuples into something else so I can work with tuples because they are easier to work with in terms of the actual code, but I don't want to mess with the export stuff. All right, so let's throw in some basic tiles for us to work with. We can do for I in range 10, and we'll create a couple different tiles. So self.tilemap string of 3 plus I plus, we'll do 10 equals type, and we're going to get a little bit more complex with our tiles here. Type grass, variant 1, position 3 plus I 10. So there's a couple things to note here. First of all, our tile will now be represented as this dictionary. So that way our tile can have multiple attributes. You could implement this as an object if you wanted, and you could do like a tile like that, but I'm not going to go through all that effort, so we're just going to use the dictionary. This dictionary will have the type, the variant, so within grass there's a few different types of grass tiles depending on like what directions are air and stuff like that. And then I'm also storing the position in here, and that's because this position as a string is not easily usable because you would have to split it by the semicolon, convert it to an integer and stuff like that. So leaving one in here that's actually as a tuple of integers is easier to work with and actually faster. So that's useful to leave there. We'll be using that later. And then this is just concatenating the dynamic location based on this iteration with a fixed position of 10. So this is going to be the positions of 3 through 12 on the X and then 10 on the Y. So this will be a horizontal line of grass tiles. All right, so let's copy this and we'll do it again, but we want a horizontal line now. So for that, we can delete this. There's a semicolon on the other side and do +stir I plus 5. And then instead of grass, we'll type stone. And then this position needs to be updated. The position here should match the one here. So we do 10, 5 plus I, or rather I plus 5. And then we can, actually this one's inconsistent, so we do 5 plus I over here. All right. So we now have our tiles, but we need a way to render them. In order to render our tiles, we'll need something to render. So we'll have to go over to our utils and create a function for loading multiple tiles at once. Because if you look over here in our data, and we go to images, tiles, let's say grass, there's a bunch of images here. We don't want to type all of those out. We want that to load automatically. In reality, you could create a function to just load every single image in that directory automatically, which is what I normally do in my games. But we'll just be handling a single folder for now, and then we'll just load all of those individual folders. All right, so we can create a def load images function. We'll give it a path. We do images equals that for image name, and then we'll have to import a new library here. We'll do import OS. So this is all we're going to do here is do os.list_dir. We'll take the base image path plus path, and then I'll pass here for now. So os.list_dir will take a path and give you all of the files that are in that path. So specifically here, if we ask for, say, images, tiles, and we do grass, it'll give us the 0 through 8 images. So this is a way to easily dynamically load images. So let's go ahead and say images append, and then we can actually use our other function here, load image, and we give it the path plus slash and then plus image name. So remember, this is the path to the folder, but not including the base image path. That's why we don't have to add it again here, because this also includes it. So yeah, this is path to the folder. We add a slash because we want to get something inside that folder, and then we do the image name, which is given by this function here. All right, so since this will return the loaded image, this images list will become a list of all of our loaded images. So we can just return that, and now we can use this to start loading some stuff. So let's go back over here into the game, and in our assets, we'll want to load a couple things. So we have several tile sets in here, or not several, but a few. Let's do decor, that's one of them. We'll do load images, tiles / decor. You could do this in a for loop if you wanted. Actually, we need to import that up here, also from utils. But yeah, we could do this as a for loop if you wanted, but since there's only 4 of them, I'm just going to copy paste. So we have grass, we have large, decor, and we have stone. All right. So let's take the grass, throw it over here, large decor, throw it over here, stone, throw it over here. All right. So if I do that, and then if I just do print self.assets, we can actually see all of our assets if I run the game. All right. So if you look in here, we have our assets. So you can see we have decor, and it's got a list of a bunch of assets. And these are just how Pygame represents these surfaces if you print them out. So it lists all of the surfaces we have and all of our different tile sets, like grass right there. All right, so now that we have those assets, we can start rendering our tile map. To do that, we do def render self surf, so that's our destination. And actually something else we want to take up here is probably the game. So we can do self.game. That way we can pull our assets. So if you remember correctly, I mentioned that we have these tiles and these tiles. These ones are on the grid. These are the only ones I filled out for now. I'll get into these when I do the level editor later, but I'm going to write the renderer for both right here. So let's start with the stuff on grid, which is what we have working right now. We have for location in self.tilemap. So when you iterate over a dictionary, you'll get all of the keys. So that'll be these values. So we'll get like 3 and 310, for example. But to get the actual tile, we'll have to look it up in the dictionary based on the key. So that'll be self.tilemap location, and that'll give us this part. All right, so from here, we can render it. So we can do surf.blit, and we'll do self.game.assets, and then this is where things get a bit tricky. We do tile type. So if you remember correctly, over here, we gave these things names. So in this dictionary, we have, I'll do this print here. In this dictionary, we have grass, and then it's a list. So if we go over here, if you remember, we have grass. So we want to say we're looking for those images of the grass category, and variant will be the index of the image we want to use from there. So from here, we can do another indexing on this assets thing. So this gets a little bit confusing. You can like print it out at this state if you want to see what you're looking at, but From here, we can do tile variant to index based on this and get the very specific image that we're looking for. From here, we can go ahead and handle the position for the rendering. So that's just going to be the position of the tile, which we have up here already. And then something you have to do here is you have to multiply by the tile size, because these coordinates are in terms of the grid. So the grid has tiles of a specific size, and to get this in terms of pixels, because that's how rendering works, we'll have to convert it using the tile size. So self.tile size, and then we do tile position 1 by self.tile size. All right, so that is a very long line of code, but it should cover all that we need for that rendering. Something else that I just remembered is that this might not work on Linux. This function right here behaves differently on different operating systems. I believe on Linux, the order of the files you get is different from Windows. On Windows, it's alphabetical. And it might be alphabetical on Linux and just in a different way, I forgot. But if you go over here, we're depending on the assumption that it'll load 0 as the first one and 8 as the last one. So that might not be the case. So what you have to do is if you just run this through sorted, it'll sort it for you, and then that makes it consistent between all operating systems. Something else you have to be careful about is that since we're depending on the file names here and it's alphabetical, 10 actually comes before 8 because it'll look at 1, 0 and it'll throw it either before or after the image number 1, because that's how it's sorted alphabetically. So the way you deal with that is you pad the front with zeros. So if you look at the entities here and say go to the idle animation, you can see I padded the front with zeros. That way 10 is no longer before 8. So that's how you can keep that consistent. This is abusing a little bit of a trick to keep our images in order here. Anyways, so back to the tile map. The last step for rendering is to handle the off-grid tiles. These ones are going to be the same tile data, but they're not going to be organized the same way. So for tile in self.offGrid tiles. So this will be, for example, we could actually just dump this one in here and say that's an example of what we could have for the off-grid tiles. So it's just, we have that same type of tile object in there. It's just a list instead. The one thing to note that's going to be different is that this position will be interpreted as pixels instead of a grid position. And that's because, well, the whole point of this is to be able to put things off of the grid, whereas the tile map is supposed to be on the grid. So the coordinate system is going to be a bit different, so we don't have to do that multiplication with the tile size. So we just do surf.blit, and then we can grab the same thing right here, and then it'll just be the tile position, since that's already in pixels for this set of tiles. All right, so we have our tile map, so let's go ahead and load it in. For that, we can just do from scripts.tilemap import tilemap, and then we can go over here and say our tile map is equal to that, and then just for the sake of it, we'll say that tile size is 16, even though that's already the default, just because for clarity. You could change this if you want. So next step is to render it. In our case, we want the tile map to be rendered behind the player, so we'll do self.tilemap.render, and then we want self.display is where it'll go. And something else I just thought about, speaking of layering, is that we probably want our off-grid tiles to be behind the grid tiles, because in our use case, the things that we're going to be placing off of the grid are mostly decorations, and the things that are going to be on the grid are mostly going to be tiles you can like run into and physically collide with. So because of that, the decorations are normally something that go in the back. So you usually want to render these first if you're using this technique. So we can go over here and throw them right there so that they get rendered first, and that means that these tiles you collide with are in front. You don't want to be walking and you see like some sort of decoration, it blocks the view of a tile and you just run into something for unknown reason. So that should be good enough for now. Let's run it and see what we get. We got an error because I forgot to pass in the game. So we do self, that'll pass in the game reference so that it has access to the assets. And there we go, we have our tile map. And we can see our tiles, which look nice. So now let's make it so that the player can fall, because right now we can only move right and left. So for that, we go over here. And since later on we'll create a player entity that will inherit from this physics entity, but because gravity will be universally applied, I'll apply it to this physics entity object instead of creating the player one. So for now, the player can still be a physics entity. All right, so let's go ahead and apply our gravity. So to do that, as I mentioned, you apply acceleration by modifying velocity. So our velocity is going to be self.velocity, and the y-axis of the velocity is the second value. So right here, normally you could just do plus equals, say 0.5 or something, but I'm going to use a different trick because there's this idea of terminal velocity in physics. So in physics, something will have a maximum velocity it can reach while it's falling, and that's called terminal velocity. You don't want to just fall a long distance and just accelerate to an infinity because you keep falling. So for that, you usually want to cap how fast you can fall after a certain point. You want it to kind of ease into that fall, but you also want a cap. So for that, we can use the min function, which is a built-in Python function. It'll take the lower of two values, or however many values you give it. Let's do 5. That'll be our maximum velocity downwards. Remember, since this isn't the normal coordinate system from math, we have positive y is down, not up. So that might be a bit misleading, but that's how it works. So this 5 represents a maximum velocity of 5 downwards. You can go more than 5 upwards, which would be like -10 or something. So that doesn't affect this. So we take 5 and then we do self.velocity 1 plus 0.1. So right here, we're modifying the velocity. And then if this modified velocity is less than 5, it'll take this part. So that's just effectively doing a self.velocity 1 plus equals 0.1 if that's the case. But in the event that this number is smaller, it'll take this one instead so that it can't go over 5. I'll use this technique a lot later on, but I figured I'd explain it now since it's a very useful technique. All right, so we have our velocity being updated. I'm actually going to drop this below the movement. And then now if we run the game, look at that, our player falls. But he falls through the floor. So now is the time for physics. This can be a bit tricky if you don't know the actual technique for doing these types of collisions. I remember I spent like a year or so on game development. Actually, I think maybe a couple years before I heard about this technique. And I actually just found it in some example code somewhere. I don't even remember where I got it from. But trying to write your own stuff for this from scratch is a bit tricky if you don't happen to know the technique for having consistent collisions. All right, so in order to handle collisions efficiently, what we'll want is a way to look up tiles. So for physics, in the case of the player, since it's not very large, you just kind of want the tiles that are nearby the player, and then you can run the collisions from there. You don't want to look up all of the tiles and test them all for collision with the player, because we know the player's position, and we can look up the tiles based on position. So there's no reason to try to test all of those collisions at once if we can just look up the like 9 tiles around the player. If the player were bigger and could collide with a larger area, you'd want to look up more tiles. So keep that in mind if you're doing your own stuff here. But in our case, we just need the 9 neighboring tiles and we can get some pretty good physics. So let's do neighbor offsets equals -1, 0. These are going to be the offsets from a given tile to get the 9 tiles around it and including it. So -1, -1, 0, -1, 1, -1, 1, 0, 0, 0, -1, 1, 0, 1, 1, 1. All right, so these are just all of the combinations or all the permutations of -1 through 1. Actually, this should be offsets, not offset. So now we can write an interesting function. We can do def tiles around self position. So you pass in a pixel position. So remember, the grid tiles are not in pixels, so we'll have to do a bit of a trick here. So we'll have to convert this pixel position into a grid position. To do that, we can do tile location equals int position 0 self.tile size. So if you don't know what this double slash is, it's integer division. So it'll chop off the remainder so that you don't get, for example, if you divide 3 by 2, you don't get 1.5. You would get 1. And you might be wondering, if we're doing integer division already, why do we need this int here? And that's because if one of these numbers is a float, it may round it to an integer, but it'll still have the .0 on the end, and that can cause some problems with the way we will do indexing in a moment. So we still have to convert it to an integer. And you might be wondering, okay, so if we're already converting it to an integer, why can't we just chop off that extra slash and do normal division and then convert it to an integer? Well, the problem there is that integer truncates. it does not do proper integer conversion the same way that double slash does. So for example, they handle negative numbers differently. Let me pull up a terminal so you can see this. So let's say you have 3 divided by 2, you get 1. Let's say you have int 3 divided by 2, you also get 1, so that's expected. But let's say you have negative 3 divided by 2, you get negative 2. You do int negative 3 divided by 2, you get negative 1. They have different results, and that's because they handle negative numbers differently. So int will pretty much just chop off, like if you did negative 3 divided by 2, it'll pretty much just chop off that 0.5, which is not a consistent behavior, because if you think about the number 0 through, actually negative 1, everything between not including negative 1 and 1, so let's say 0.9, that will go to 0. Negative 0.9, that will also go to 0. So that's an important distinction, and this is why you need to be very careful about converting things to integers when dealing with computer graphics. This is making the space of 0 almost the size, or sorry, it's the same space between like 1 and 3. In terms of pixels, I guess, you could say that the 2 pixels bordering 0 get brought into 1 or something like that. It causes some issues when you're dealing with this stuff. So especially when you're dealing with grids, you have to be very careful about how your stuff gets rounded. Anyways, back to what I was doing. So this mess of code will convert the pixel position into a grid position. So that's just the x-axis, so we have to do the y-axis now. And now that we have both, we have a nice tile location, and then we can do a for loop. So for offset in neighbor offsets, this is the thing I defined earlier, we can now generate all of the tiles that are around this pixel position given. So for this, we can do check location is, and then we compose a string, because that's how we did our keys here. String of tile location 0, and then we do plus offset 0. So we're adding all of these numbers to whatever this base location is, so that'll give the 9 tiles in that area. So we do that, and then we add our semicolon, because that's what splits our location. And then we can do it again, and we'll throw in that, which is the y-axis. All right, now that we have our string, we can do if check location is in self.tilemap. That just checks to make sure that there is a tile that happens to actually be there, because remember, in a tile map we can have a lot of empty space, and that's just denoted as there not being anything in the dictionary for that location. All right, if that location exists in the tile map, we can do, actually, I'll throw a pass right here right now, and then we can go up here and we'll do tiles equals this. This is the tiles we're returning, so we can do tiles.append. And then we can just grab the tile data by doing self.tilemap and then check the location. All right, so now we can return the tiles, and this will give us all of the tiles around that location. So I'm just gonna run this function so you can see the output here. So let's just do print self.player, actually no, self.tilemap.tiles around, and then we can do self.player.position. So that'll give us some interesting output here. You see that? So right when we passed to the ground, it started outputting this data here. So when we're in the air, it just gives us this. And then when we're near the tiles, it gives us this. So this doesn't mean we're touching those tiles, it just means we're near them. And this is where we can actually do the collisions, because that's a little bit slower than looking them up. All right, for the collisions, we gotta go back to tile map, and there's something else we gotta do, because we don't want to collide with all of the tiles. We want to be able to put stuff in the world that we can see, but we don't necessarily have physics for, so you can just like walk by a tree or something. So the next thing we have to do is add a function that'll filter the nearby tiles for things that have physics enabled. So let's do physics rex around. So we'll do another step in here to make the collisions easier, which is converting all of those tiles that have physics into pygame.rect. If you remember, that's what we did the collisions on, like, I don't know, an hour ago. So we can do rex equals this. This is the rectangles we're returning. And then we can use this function here to get all the nearby tiles. So we can do for tile in self dot, and then we do that, and get rid of that self. And now we're iterating over all of the nearby tiles. If there are none, this whole loop gets skipped to begin with. So we would just return this empty list of recs. So if tile type, and this is where we're going to get into something interesting, we need to add a list of things we want physics on. So physics tiles equals, and I'll say grass and stone. So if you don't know, even though curly braces are normally for dictionaries, if you don't do the key value pair thing, this is what's called a set. A set is used for a collection of values. Usually order is not important, but the big thing is that no duplicates are allowed, and actually looking up to see if a value is in a set is more efficient than looking up a value to see if it's in a list, for example. So this is actually slower than doing this if you're looking to see if a value is in there. So for something that's being run a lot, which is checking tile types, it's good to have a set there. And this is one of the techniques you can use to optimize things. And don't forget that we also have this code right here, which is also already a huge optimization. You can have as many tiles as you want, and the collisions will still run fast because it just looks up the nearby tiles. If you don't know, looking up a value in a dictionary is also very fast. You can have as many values as you want, and it still roughly takes the same amount of time to look up a value as long as you know the key. All right, so we want to check if our tile type is in the physics tiles. So if it's in physics tiles, that's very English, then we know that this tile that we have near us is a tile that we can collide with. So because of that, we now want to add something to our rects list. So we just do a dot append, and up here we're going to have to import Pygame so we can actually create a rect. We can do Pygame.rect, so a new rectangle. And remember, rects are just kind of a thing in memory unless you decide to draw them, but you can run collisions on them, you can draw them, you can do lots of stuff with them. So we'll create it with the x position being the tile's position on the x-axis, and you have to multiply it by the tile size to get the position in pixels, and then tile position on the y-axis, get the pixel position, and then we also need the tile size because this will be the size of the tile in width and height. And since they're square, it's going to be the same for both of them. All right, so that will add the new rectangle, so we can return these rects. And if I go over here, and if I take this back and then do physics rects around, instead of returning those tiles, it should return a bunch of rects when I pass through. All right, so you see these? These are the rects that I'm nearby. So the final step here is to run the actual collision detection and handle the collisions so that the player can't pass through. For that part, we'll go over to our entities, and we'll have to do a new step here. We're going to throw in the tile map. So tile map will become an argument, and we can go back to game, and in our update function right here, we can do self.tilemap so that that gets passed in correctly. All right, so now that we have access to our tile map in here, we can do our collision detection. If you remember from before, in order to do collisions, you have to have two rectangles. So the thing you're colliding with needs a rectangle, and the thing that's doing the colliding needs a rectangle. So let's give the physics entity a rect. So to do that, we want one generated dynamically because we don't want to go through the effort of updating it all the time. So we will create a function for generating it. Let's do return pygame.rect, and we'll do self.position 0, self.position 1, so that's the top left. And that's something important to note, is that we're using the position as the top left of the entity. If you remember, that's how surfaces are blended onto each other, it's by top left, and that's also how we're going to handle the physics here. So this position on the entity, you might think it's the center, but it's actually the top left of our entity. All right, so now that we need our size, which we already have, self.size 0, self.size 1, and that will be our rect. And the reason we want the function is because we're changing this position all the time, and we want to be able to get a fresh rect based on that new position whenever we need it. All right, so now with that rect, we can finally do our collisions. So let's split this in half here. We'll do entity rect equals self.rect, and then for rect in, and this is where the magic is, tilemap.physics rects around self.position. We want all those nearby tiles. If entity rect.collide rect with one of those tile rectangles, this means that we've add a collision. So now the next step is to handle this collision. So this is where the magic of splitting up our movement into two axes comes into play. You don't want to do them both at once. I have a whole video about this. It's pretty old, but it's still a really good video, I think, explaining in depth how this technique works. But the idea is that if you handle one axis at a time, say you move on just the x-axis, if you collide with a rect, because you know the player is a rect and the thing you collided with is a rect, and you know what your movement was, you can now resolve that collision by adjusting the player's position based on what was collided with. So in this case, let's say you're moving right, you collided with a tile, so this is where this thing comes into play. We could say if frame movement 0 is greater than 0, that means you're moving right. Let's say you're moving right, you collided with a tile. So there's a really simple solution for how you handle this. You make the right edge of the entity snap to the left edge of the tile. So that way they touch and then they get pushed back straight to the edge. So we just do entity rect.right equals rect.left. And we can do if frame movement 0 is less than 0, entity rect.left equals rect.right. Because let's say you're moving left, because remember negative x is left. If we're moving left and we collide, we want to set the left side of our entity to the right side of the tile. And the last thing you have to be careful of here is that we're modifying this rect's position. We're not modifying the player's position. So we have to go and update the player's position now based on this logic we did here. So if you want to do the actual math yourself, it gets more complicated. That's why we abstracted out to the rects. So we can do self.position 0 equals entity rect.x. So you might be wondering, if you can move around a rect like this, then why don't we use the rect to represent the position of the entity? So there's a slight issue with rects. If I import Pygame here, I can show you. You can do pygame.rect. So let's say you have 0, 0, and say 10 by 15.5. Rects only work with integers. So you can't have sub-pixel movements with rects. So depending on how fast something is moving, you might have problems with movement depending on whether or not you're abstracting for a rect or not. There are very few cases where it's okay to just have your position represented as purely an integer. When it renders, because we're using pixels and everything, it gets converted into an integer. But for example, if you move 0.5 pixels, here I can show you. Let's say r equals pygame.rect, you can do r.x plus equals 1. r.x is now 1, or you can just print it out. And now let's say this, r.x minus equals 0.5. That works fine, so r.x plus equals 0.5. Now you see the problem. We just added 0.5 and it didn't move. So let's add it 2 more times. It still didn't move, and this is where the problem is. So if you're using Pygame CE, which is that choice I mentioned at the beginning, there is something called an frect, which allows the rects to be floats, so you can still do collisions with them and handle positions. But since I'm trying to make this tutorial work for both versions of Pygame, I have to create my own position variable here. That's why we do all of this. It's a bit tedious, but that's how it is. So if we were actually just purely doing a Pygame CE tutorial, I could make this a couple steps simpler and take out the position thing, but I'm not doing that, so it's a bit more complicated. All right, so we've done the collisions for the x-axis, and now we do the y-axis. And this is the whole point of separating out the movement here, because you handle the collision twice per frame, so that you can handle the collisions based on whether or not that collision was from moving right and left or up and down, because it gets a lot more tricky if you try to do both of them at once. All right, so let's just copy this over, and we do the same thing. The only difference is this is now the y-axis. So this now becomes the bottom and top and top and bottom. So if you're curious about what these attributes actually return, this is just a single integer representing the x or y axis, depending on whether or not you're doing top, bottom, or right and left. So it'll be like a position on the x-axis or a position on the y-axis. All right, so now with those two collisions done, we have our physics. So let's go ahead and run this and see if it works. And look at that, we're standing on the ground. And I can move around, and I can run into this wall, and I can't pass through it. So now there's a slight problem. You see, I dropped off very quickly there. I didn't slowly accelerate into a fall like it should. So the other thing we have to keep track of is the fact that our velocity here reached 5, but there's nothing to ever bring it back down. Normally when you hit the ground, your velocity should be updated to 0. It may not be able to move through the tiles because of our physics, but that velocity is still sitting there at 5. So let's add something to keep track of what types of collisions we've had. So I'll go up here and add a self.collisions dictionary, and we'll do up, false, down, false, right, false, left, false. So this is a little nice trick you can use to keep track of which directions you've had a collision. And we can use it in here and in other locations to see what directions an entity just collided with. This will be useful for things like wall jumping and stuff later. So for our collisions here, we just have to go into here, and when we actually resolve these collisions, we can update our collisions. So self.collisions right equals true. And then this one is going to be left. And this one will be down. And the last one is up. All right, so we have our 4 directions. And something important to note is that we're resetting it every frame. Every single time this update function is called, this will be reset. So it'll be 1 frame you get where it says true after a collision. But if you're just continuously colliding, like you're holding right and you're constantly running into the wall, it'll always be true. But if you're running into a wall and you lift your finger off the right key, it will no longer say true because you're just standing next to the wall, not actively running into it. All right, so from here we can do if self.collisions down or self.collisions up. This is where we want to reset our velocity. So self.velocity 1 equals 0. So you notice I did it on down or up, and that's because if you run into the ground, it should stop you. If you are going up and you hit the roof, it should stop you. You could also do the x-axis too, but we're not using that velocity yet. We're only using the y velocity for now. So now I can run around here, and if I fall off the edge, it slowly accelerates. So let's go through here and add one more thing. It would be nice if we could jump, and this is where the magic of this whole physics-based system comes in. So we can do if event.key is pygame.k_up. We can do pygame or self.player.velocity 1 equals -3. So all we have to do is override that vertical velocity and set it to a negative number so that the velocity is pointing upwards, and suddenly the player is just moving upwards, and then the gravity will pull it back down. So it's a nice smooth jump. All right, so if we run this code, and if I press up, you can see I go up and down. So it's a nice arc. And it's very responsive as well. This is, I think, the best way to do jumping. There are some people that try to like model it as some sort of formula or something, but overall I think this just works really well. And this is a technique that I always use. All right, so now that we have jumping, we can test a couple other things. So right now we have infinite jumps. Later we'll work on making that limited, but for now we have infinite jumps. The last thing we need to test is to make sure that if I hit my head, it stops me properly. So if I go up here, you can see I instantaneously bounce off the roof. I don't run into it and stick. So that should be pretty much everything for the physics. If you see, I can just run around and this works pretty much exactly as you'd expect, which is great. So we have a game where the player can jump and run around and run into stuff, but the next thing that you would often see in platformers is a camera that can move around. So let's get into that. The idea of a camera when it comes to lower level computer graphics is really just an illusion. Instead of moving a camera around, you're really just moving everything else. Let's say you wanted to move the camera right. If you moved everything in the world to the left, you would see the same thing. So this idea of a camera isn't really real. You can abstract your code that does move things around into like a camera object, and that's sort of what we'll be doing, and that's how you can sort of get something that's easy to work with so you can move the camera around. All right, so to do this, I use this idea of a scroll variable. You can think of this as like the camera's location. So self.scroll equals 0, 0. So let's start the camera at the position 0, 0. The next thing we'll want to do is actually make it so that this camera position gets applied. To apply this camera position, we need to start adding offset variables to everything that renders. So right here, let's do offset equals scroll. And this is how much we're going to move what we're rendering, because as I mentioned, the idea of moving a camera is just moving everything else. So we'll add this offset for rendering based on where the camera is. And then we can add this, actually it should be self.scroll. We can add this to all of our rendering stuff, which is just, I believe, these two things. So our tile map and our player. Now, if we go over to tile map, we go into render, we can say offset equals, and we can give it a default value in case we don't provide it, but we did, so whatever. But over here, we're going to want to apply this offset. So we do minus offset 0, tile position 1 minus offset 1. You'll notice I broke up this tuple that was here, or it was originally just the position, but I had to break it up into its elements so that I could adjust it. If we were using Pygame's vector tools, you could just add it or something. Something else to note is that I'm actually using subtraction here. Instead of adding the offset, which is a bit more intuitive, I'm subtracting it, because when you actually are working with the camera, if you remember I said you move the camera to the right, everything on the screen effectively moves to the left. So if you want to deal with the camera in world coordinates, the offset should be applied negatively. Alright, so now we have to do that over here. So we can go minus offset 0, minus offset 1. Okay, now that we have offsets in here, let's go over to the player. And in here, take the offset parameter. And then we also have to output it here. Offset 0, self.position 1, minus offset 1. Okay, now that we have that, if we run the game, it shouldn't crash, and we see the exact same thing. The next step is to make it so that we actually are moving our camera. To do that, we can do something as simple as self.scroll 0 plus equals 1, and then we can run the game again, and you can see the camera's moving to the right. So now let's do something where the camera focuses on the player. We're going to use an interesting technique here. We don't want the camera to just move linearly to the player. You want it to kind of slow down as it gets closer to the player, so it's a more smooth motion. And it should speed up the further away the player is from where the camera is. So let's do scroll 0 plus equals, well, self.scroll, and then we can do self.player.rect.center x, and then this is where things get a little bit tricky. Minus self.display.getWidth divided by 2. So this camera position is really the top left. So if you were to actually put the camera directly onto the player's location, the player would end up in the top left of the screen, and we don't want that. We want the player to be in the center of the screen. So what we have to do is we have to subtract part of the screen size so that the camera is positioned in a way where the center of what you can see is on the player. So that's what this is for. And then the next step of this formula is to subtract self.scroll 0. So if you go and do the math on this, we're taking where we want the camera to be, we're subtracting what we have, and then this whole thing is being added to the scroll. So what we're doing here is just finding how far away the camera is from where we want it to be, and then we're adding it to the scroll. So if you think about it, this is just a glorified way of setting the camera to where we want it to be. But there's a reason why I wrote this as plus equals, and we have this in parentheses here. So there's this fun trick you can do, where if you just divide the increment, because this is how far off we are, if we divide by 30, it now will take 1/30th of whatever distance there is remaining to the center and apply that instead of the whole thing. So the further the player is, the faster it will move. And as it gets closer, it'll slow down because that distance shrinks. All right, so let's take this and do this for the y-axis as well. So it would go center y and get height and scroll 1. And there's this one minor detail we'll have to deal with here. I think I might be able to demonstrate what the issue is. You might be able to see, you might not. It's a difference of a pixel. So let's run this and see what happens. So, oh yes, you can see it. So look at the player. I'm like jittering around a bit. So if I jump especially, you can see it's jittering with the floor. The player was bouncing up and down. And that's because the player's position is a float. It's not a whole number. And because the scroll is also not a whole number, when you round things so that you can get the pixel locations of everything, those fractions can add up and make things inconsistent depending on the subpixel movement of the camera. And we don't want that. We want the subpixel positions to not really come through in the placement of entities, because we want things to be nice and smooth for a pixel art game. If you're not doing pixel art, maybe this wouldn't be as much of an issue, but for pixel art especially, you should deal with that jittery issue. So to fix that, we just take a variable called render scroll, and we can assign it to the integer of self.scroll 0 and self.scroll 1. So it just takes whatever the scroll is and converts these two numbers to integers. If you remember before, I mentioned there was an issue with using int on pixel locations. That's not as much of an issue with the camera, because if the camera's off by 1 pixel, it's not a huge issue. If something's off by 1 tile, or depending on how things are moving, if it's off by 1 pixel, it could be an issue, but for the camera, it's not an issue. So we don't have to worry about trying to deal with the weird way the int behaves. Anyways, so now that we have this integer version of the scroll position, we can use that instead of self.scroll. And because now the scroll won't have its own decimal component, the only thing that will have a decimal component is the player. So you won't get any of that subpixel movement showing through as you show the camera, because you have to have 2 elements with subpixel parts to their coordinates for that to work, or for that to cause issues. Anyways, so if we run this again, that jitter should be gone. Now you'll notice that the camera gets a little bit choppy as it gets closer to its target. There's not much you can do about that, because the camera's position is in pixels and everything's rendered in pixels. So since our pixels are larger, since this is a pixel art game, if we want to keep things consistent, it gets a little bit choppy. Now there are some games where they'll have like pixel art artwork, but everything moves around with subpixel movements, and that's something you could use to get the movement of the camera to be a bit smoother. But I like to stick to pure pixels. I'm a bit of a Puritan when it comes to my pixel art, so that's just how I like it. Anyways, our sky is looking a bit flat, so let's add a background there. If you remember, we have our background.png here, which is a nice sky background with some patterns on it. And let's go ahead and load that in. So we can do background, load image, background.png. And now, instead of filling the screen with this color, we can do a .blit, and we can take our self.asset background, and we can put that at 0, 0. So since this background is the size of the screen, that pretty much does the job of wiping the screen for every frame. Before we were filling it with one solid color, now the screen basically gets reset to whatever this background is, because this will draw over everything that was there before. Now if we run the game again, we now have our background, but our sky is still looking a little bit empty, so why don't we add some clouds? So this is where things are going to start getting a little bit hectic. Let's go ahead and go into our scripts here and create a new script called clouds, and let's import random, because I know we will be using that. Let's start by creating our cloud class. So class cloud, we need an initialization function. So a cloud will have a position, and then we'll have some kind of variant, but in our case, we'll just pass the image that we're using. And then a cloud should have a speed that it's moving at, and then a depth for how deep it is into the sky, I guess. All right, so we can do self.position equals list position. If you remember, we want to take the list of that position, so we do with tuples and copying and all that. And then we can take the image. We don't want to copy this image because we're not modifying this image in the cloud, so we can have them all pointing to the same source image so that we don't waste memory. All right, so for the speed, that will be the speed. And then one last one is the depth, which is the depth. All right, so when we update our cloud, we just have to do one thing. The cloud just has to move a little bit. So let's move the cloud based on its speed. And then let's create a render function. So self, let's say our destination surface, and this will need an offset too, because remember now we're working with the camera, so we need to start taking offsets into pretty much everything we render, unless it's like the user interface, which we won't have for this project. All right, so we need to calculate a render position. We'll do self.position 0 minus offset 0 by self.depth. So instead of just applying this offset straight up, we're going to use a trick where we multiply it by the depth. That means that if the depth is like 0.5 and the camera moves like 5 pixels to the right, this cloud will only move 2.5 pixels to the left, whereas all the terrain in the front is moving 5 pixels to the left. And that will create a nice parallax effect. And this is probably the easiest way to implement that, is just multiplying your camera. For this, we'll want all of our depths to be less than or equal to 1. In reality, we're actually going to go even lower than that, so that they move slowly in the background. All right, so self.position1 minus offset 1 by self.depth. And then that should cover our render position. So now we need to actually render it. So surf.blit, that's our destination surface. Self.image, that's the image for the cloud. And then we do the render position 0, and this is where some other magic comes in. If you notice here, our position just keeps on incrementing. We don't have any code for removing our clouds or adding new ones. I'm going to use a trick where you just create like a set amount of clouds and they just loop around. And to do anything that loops with computer graphics, usually you want to be using the modulo operator, because when you divide something by another number and take the remainder, you're effectively just creating a loop of numbers. So for example, if your modulo is 10 and you have your number is 5, you'll get 5 as an output. If your modulo is 10 and your number is 12, you'll get 2 as an output. So you can increment up all the way to 9, but once it hits 10, it'll go back to 0, which is really nice for making things loop. We have to do some offset stuff because of the way the images are positioned. So let's go ahead and do modulo surf.getWidth. So that's the size of the display. And we'll actually want to add some width here because you don't want the cloud to be looping as soon as it hits the edge. You need to have the extra space for it to go off the screen. So you need extra space for looping based on however big our cloud is. Otherwise, you'll see it teleport before it's actually fully off screen. Or the other thing you could end up seeing is that it suddenly appears on the left side of the screen instead of rolling onto that position. All right, so for this, we'll add self.image.getWidth. And then we'll want to subtract the width again. And that will just handle the way that images are placed on the top left, and we have to do some adjustments for the edge of the screen and for the wrapping. So now we have to do the Y component. So we can just copy this whole thing, go to the right, paste it. We can say render position 1, get height, get height, get height. All right, so now that's our mess of a rendering function done. Now we need to create our clouds class, which is going to store all of our clouds. So self cloud images, and then we want a count for how many clouds spawn. So self.clouds equals an empty list. That's where we will store all of our clouds. And then for I in range count, we'll want to spawn a bunch of clouds. So self.clouds, the append, and then we take the cloud object and instantiate it. And then this is where we pass in like a random position and our random image, speed, depth, everything. So this is going to get a little bit messy. We can do random.random by 99999. You might be thinking, that's way too many pixels, that's going to go way off the screen. But remember, we're looping it, so it doesn't matter how high that number is, it'll loop back to somewhere on the screen. All right, so now we can do random.random by 99999 again for the y-axis. And then we can get a random choice of our cloud image. And the next step is to get our speed, which is random.random by 0.05 plus 0.05. So that's starting with this number and going up to 0.1. So that's really slow. The idea is that, well, clouds are usually slow moving, at least in platformers. And now we can do our depth. So random.random by 0.6 plus 0.2. So we want a minimum multiplication for the camera's position to be 0.2. So that will be the camera is moving the foreground 5 times faster than the background, going all the way up to 0.6 plus 0.2, which is 0.8. So that's 25% faster for the foreground than the closest cloud. All right. So with that spawning stuff down, there's not much left to do. We can do self.clouds.sort key equals lambda x.depth. So this is a bit of some advanced code, I would say. What we're doing here is we're sorting all of our clouds here. And when you pass the key function for the sort function, it determines how you sort things, which usually you use for objects. In our case, our clouds are not naturally sortable. Python wouldn't really know what to do with them, so we have to tell it how to sort it. So what we're saying is just take the object and then sort it by its depth. So by doing that, the clouds that are closest to the camera are going to be pushed to the front for our rendering. You don't want the stuff that's moving slow in the far background to appear in front of the faster moving stuff in the front. So you got to get your layering right with this, and sort will automatically take care of that for us. All right, so just a couple more things. We need our update function for the clouds, and that's as simple as for cloud in self.clouds cloud.update. And then we need our render function. So self surf offset equals 0, 0, and then for cloud in self.clouds cloud.render surf, and you just pass the arguments along. All right, so there are our clouds. So the last step here is to import them and actually use them in the game. So we do from scripts.clouds import clouds, and then we can go over to here and say self.clouds equals cloud, and we need to pass it the self.assets clouds. So those are going to be the images for the clouds, which we need to define here. So we can do clouds load images, and this will be under data, or no, not data, what is it? It's going to be data images clouds. So we're looking for just clouds, I believe, and that should load those two images as a list. And then now with our clouds here, we can go ahead and say how many we want, and then we'll just say count equals 16 for clarity. And we can go down here into our update function, and we want to make sure that our clouds render before the tiles, so we go and do that right here. So self.clouds.update, that'll just move all of them, and then we need our render function for the clouds, and we want to render onto the display and give it the offset of the camera. All right, so now if we run the game, behold, we have our clouds, and look at how they're moving slowly, which is nice. And you can see, if you look carefully, they're actually looping around, and you can tell that. And if I move fast enough, you can see that there's a bit of a parallax effect going on. So some clouds are clearly in the front, and some of them are in the back. And they all move slower than the ground in the front, which creates a really nice effect. So that's pretty much it for parallax. It's a really simple concept, but it looks really nice as well. While we may have implemented a nice tile system already, typically if you're working in some larger environments, you will want to optimize this a bit. Currently, if you look at our setup here, we render every single tile that we have onto the screen. We don't want to do that. It's much faster if we can efficiently determine which tiles should be on the screen, and then only show those tiles. So one of the conveniences of the way we had our tile set up is that it's in a dictionary, which means we can look up the values. If we know where the camera is, we can calculate all the possible positions that could be on screen for the tile map. So that would be these positions right here, where we're defining them as like the string of the coordinates separated by a semicolon. So the idea is to figure out what the essentially top left tile of the screen should be, and then calculate all of those strings going down to the bottom right, and everything in between. And then we look up those locations, and if there is a tile, then we render it. So doing this, because dictionaries, if you have the key to find a value, because they have a runtime that's above 1, if you don't know what that means, that's not a huge deal, but it just means that no matter how much data you have, it's roughly the same amount of time to look up the value, which means you could have millions of tiles and still look up tiles very efficiently. So we're going to need 2 for loops here, one for the x-axis and one for the y-axis. So I'm just going to comment this out for now because we're going to replace it. So we want for x in range, and then we'll take offset 0, self.tile size, offset 0 plus surf.getWidth, and then divided by self.tile size, and then we'll add a +1 here. So what we're doing here is we're taking the range, so that's all the numbers in between, and then we're dividing the offset here of the camera by the tile size. So that will find what the top left tile's X position would be. Because remember, the offset here is in pixels, and our tile system is in the tile coordinates, which is just the normal coordinates divided by the tile size. And then we can take our offset 0, so same thing, and then add the display width. And by that, we find the right edge of the screen. And then we divide it by the tile size again, and that gives us the tile coordinates of the right edge. But there is an off by 1 error because of the way the coordinates work, where you need to add 1 here to get everything. So that's just adding 1 extra tile on the right side that we need to check. Alright, so now we can just do the same thing for the y-axis actually. So that would be offset 1 because that's the y-axis. And then instead of get width, it's get height. And then everything else stays the same. Now, from here, we can calculate, or actually we can change that to y, we can calculate our location string. So string x plus semicolon string y, and then we can do if location in self.tilemap, and then we can take our tile, so tile equals self.tilemap location. Alright, so now that we have our tile, we can render our tile. In fact, actually I just noticed there's a mistake here. This off-grid tile stuff is what we want to keep. It's this stuff below that we're replacing. Oops. So I'm going to move this back up over here, and then it's this that we're replacing down here. So we want to get rid of this, and this line right here can be reused to render our tile. So we can just drop it right here. And then let's just get rid of this now. So we're using the same code where we just take the tile, so it'll take the position and the tile type and stuff to get like the image and where it should go so that we can blend it. And that's all coming from the same thing because this is the equivalent of what we had before. So now that we have that, we should be able to run it and things should be the same. At least they should look the same. So yeah, you can see we have our player jumping around and everything, and the map works as expected. So you can't really see a difference here, but if you were dealing with very large worlds, you would notice a very big performance difference. And actually, even with medium worlds, if you're actually logging it, you would be able to tell. Something interesting to note, though, is that in this particular example, this is actually going to be slower than what code we had before. And that's because there's a lot of air around, and we have to look up the tile locations even if it is air. So that takes some extra calculations, whereas before we just iterated over everything. But as soon as the number of tiles, well, not necessarily as soon as, because there's a bit more overhead in doing all these calculations here, but roughly around the time when the number of tiles in the world is greater than the number of tile coordinates that would be capable of appearing on screen, that's roughly around when this will start to benefit you. And that will happen in a lot of cases. So you might think, okay, this is great, but we also have this for loop right here where we're going over every single tile. Well, this one's a bit more complicated to fix because this one, well, right now we even implemented it out as a list. There's other ways you can structure your data for this stuff to make it efficient. So if you have off-grid tiles, you're going to have to implement some extra system here to optimize the rendering. But that only needs to be done for very large worlds, because typically if you have these off-grid tiles, and remember we actually don't have any yet, but we will have them later, but if you have off-grid tiles, usually you don't have that many of them because they're usually just kind of some decorations here and there. Most of your tiles are normally going to be on the grid unless you're doing some really fancy stuff. So you can get away with a lot more when it comes to the off-grid tiles before you have to start optimizing them, which is why for this project I'm not going to optimize them. For many level-based things where you're making your levels by hand and it's not like an infinite world, you usually don't end up having to optimize your off-grid tiles. But if you do an infinite world where there's automatically generated off-grid tiles, you're going to need to implement a system for this to optimize it. And that system could be a set of quads. So you separate your off-grid tiles into quads, and then each quad will be a list of all the tiles in it. And it's sort of like the tiles we have now, except instead of mapping a tile to a location, you would map a list of off-grid tiles to that location. And then your quads would probably be bigger than your actual tile size. So you would maybe have quads that are 4 times larger in each dimension than your tiles. So that would be like 16 tiles could fit in one of those quads. But that is more of an advanced topic, and it gets even more complicated if you want to deal with stuff that's moving around, because then you have to switch which quad your off-grid tiles are stored in. But overall, it's the same principle, it's just you have to deal with all these different edge cases and handle things slightly differently. So that's something you could do in your own time if you're interested in that type of thing. Alright, so that's pretty much it for optimizing your tile map. This is one of the biggest optimizations you can do for games like this, so I thought it was important to show you how you can do it here. If you're curious about how to optimize things more in general, it's very common to see solutions to most game development related optimization problems, at least at this level. You'll see that most of them involve just using dictionaries because they have really good lookup times and you can throw as much data in there as you want. So a lot of these problems are just the issue of how can you organize your data in such a way that the basic operations that you're doing don't take as much performance. And dictionaries just end up being the solution to that most of the time, or at least part of the solution. Sometimes you're dealing with stuff like caching, where you'll want to pre-generate something and then you store it inside a dictionary so you can look it up later and then use that. But even then you're also still using dictionaries, so it's funny. Alright, so now that we have our tile system optimized, I think it's time to get into something that a lot of people would think that Pygame has supported by default, but it actually doesn't, and that is animations. This is, to me, one of the big things that differentiates something like Pygame from a game engine, is that there's no built-in animation support. If you want to animate something, you have to write your own animation system. And that's one of the things, among others. So some of the other things that differentiate it would be the fact you have to write your own physics or your own tile system. And those are just kind of some of the basic things that people expect in game engines, although there is no formal definition for game engine. So because of all those things that I just mentioned, though, Pygame's about as far as you can get from a game engine. So we do have to keep going down this path of doing things ourselves, which is nice on some level because you get a lot more control over it. And then another way it's nice is that it gives you more experience dealing with lower level problems. In game engines, it's more like, what system that's already made can I use to solve this problem? So lots of people will have to Google very specific problems and find very specific solutions, whereas when you're working at this level, every solution is more general. So for some people, and this was the situation for me when I first got started, I actually found it much easier to make all these solutions myself than to try to figure out how to use all these pre-made things that come with engines. The other side effect is that it's a much more general problem-solving skill that you're developing by solving these types of problems. So typically, you'll find that if you're trying to do work as a software engineer, you'll get a lot better experience working on this type of level than if you were to try to use a game engine like Unity or something. And then once you have these systems already made, you can start writing your own frameworks and stuff to get to a point where you can actually work faster on certain types of projects than people using engines, which is really cool. Alright, so let's get into animations. The first thing we'll need is an actual animation class. So we need some way to represent an animation as an object. So to do that, in my utils script here, I'm going to create a animation class. So def init, this is basic stuff. So we want to take in a list of images that we want to animate. So we'll do images. And then we also want to say image duration. So this is basically how many frames we want each image in this animation to show for. And the last argument I'm going to add is loop. So loop equals true. So by default, we want our animation to loop. So let's just bind all these parameters. So self.images equals images, self.loop equals loop, self.image duration equals, whoa, imager, and then self.done, self.done equals false. That will be set to true if you're not looping and it reaches the end, and then we have self.frame equals 0. And that will just keep track of where we are in our animation. So this is one of the most primitive types of animation setups that you can make. We're restricting ourselves to giving each frame the same duration across the animation. If we don't want to do that, we could set up a system where each frame has an assigned duration. You go and do all the math and try to figure out when to move to the next frame and stuff like that. And you can add all sorts of other rules to your animation. If you actually look at some of my games, you can find the animation code and it gets a lot more complicated than this. But this is a very simple one. So the idea is to just take all of your images and then just render your images based on your frame, and then that frame increases over time. And then we also loop it. And that's enough to get us a nice animation. All right. So one of the first things we'll want to do here is we want to be able to copy our animation because if you notice, we're taking in our images and we have all of these, or specifically these two values that are specific to an individual animation. So the way I'm going to set this up, and this is, some people might say this is bad code, some people might say it's good code. For this use case, I think it's pretty good because it's a simple solution. But the way this is going to work is that we create an animation for each animation in the files, and then we have it somewhere that's easy to reach. And then every time something wants to use that animation, it will copy its own instance of the animation. So something important to note is that the way Python works is that if you have a list and you assigned something else to that same list, or even an object, it's just any object in general that's not like a primitive value, it will be a reference to it instead of actually copying it. So let me demonstrate here. Let's do def copy self, return animation. So that's just making another one of itself. And we pass it self.images, self.image durations, or duration, self.loop. So I'm passing in the images that it already has, the same duration in the loop. So it's all the same values, so it'll generate pretty much an exact copy of itself. But like I was saying, because we're passing in images here, it's not actually making a copy of the images. You're just getting the images, the same list of images. So if you modify it in one of them, it will affect both. So that's something to be careful about, but in our case, that's actually to our benefit because we can copy this as much as we want. And then all those images don't take extra memory because they're all looking at the same thing. All right, so with that copy done, we now need a way to render our animation. So let's do def image self, and instead of actually rendering it to a surface and like having a render function, I'm just going to make it so that you can get the current image of the animation, because that's a little bit more flexible because we can use that image however we like instead of being in a situation where we have to give it a surface to render to. So for this function, we'll just return self.images and we'll do int self.frame divided by self.image duration. So we're dividing our frame by how long each image is supposed to show for. So frame here could, I guess, be interpreted to mean a couple different things. So it could be frame of the animation, or it could be frame of the game. So in this situation, we're going to be using it as frame of the game. I think in some of my projects, I use it the other way around. But in this case, we'll increment our frame value every single frame of the game. And then every single time it crosses this threshold here, this whole value, since it's truncated to an integer, will go up by 1. And that will be the index used to select which image we show. So this will just give us whatever image we should have for the frame that we are on. Now we can do def update self, and we need to actually increment our frame here. So if self.loop, we want to do it differently if we have a loop versus if we don't. So this is not as simple as self.frame plus equals 1, because you'll run into a problem where let's say our frame goes past the end of the animation. You'll get an index error on our images list because you're trying to access an image past the end of the animation. So we have to make sure that this loops properly, and then also for if the loop is not enabled, it needs to stop at the end. So here's how this is going to work. We'll do self.frame plus 1, so that's the same thing as plus equals 1, but we want to add an extra step here in this calculation. So we're going to do modulo, so that's the remainder of self.image duration by len self.images. So this will force our frame to loop around once it reaches the end. Because remember, I mentioned before that pretty much anytime you want to loop anything, usually you're going to end up using a modulo, because the remainder is effectively creating a loop. Alright, so like I said, it goes to whatever the maximum frame is for animation, which is calculated here, and then it just loops around. And then we'll also want to do, if we don't have a loop, so that'll be else, and we do self.frame equals min self.frame plus 1. That's the same plus 1 thing, but we have a min here this time. So we don't want it to go past the end of the animation. So min takes in 2 values and then returns the lower of the 2. So that'll be that we define what our end of animation is right here, and if for some reason this value is greater, it will return whatever the end is. So self.image duration, and we did this before, by len self.images. Now the one thing we have to be careful about is just being off by 1, because technically, let's think about it like this. So let's say you have an image duration of 1 and you have 3 images. So you say, okay, our last image is number 3, and this math will give us a maximum value of number 3. But lists are indexed starting from 0. So the index 3 does not exist. Because of that, you have to do -1. And you might be thinking, well, wait, we didn't have to do that up here. And that's because of how modulo works. If you take the remainder of, let's say, 3 divided by 3, you get 0. So if our end here, let's say our last frame is frame 3 for some reason, then it'll go 0, 1, 2, and then loop back to 0, because you can't have a remainder that's equal to whatever you're dividing by. So remainders actually naturally deal with that issue. We just have to account for it here because this is a different system. All right. And actually, if you're curious about why arrays start at 0, that's actually one of the reasons why it's convenient, at least in game development. There's a whole load of reasons why it's better for them to start at 0, but this is one of the ones where it's convenient, is just being able to do this here. All right, so we do if self.frame is greater than or equal to self.image duration by len self.images -1. So this is just doing that comparison with this value right here. And you could do is equal to. I don't like to do that because this is a broader condition. If we made a mistake and maybe we went back and changed this for some reason, this will not just suddenly break because of that. So I prefer to, when possible, just do the broader condition, if it makes sense. So yeah, we're just saying if the frame is greater than this, we can do self.done equals true. Although technically if it's greater, we'll get an index error down here, but just to be safe. So this will set done to true when it's actually done, and the frame can't go past the end, which is just what we want. All right, so we have our animation class. So now we need to be able to load our animation. So for that, we go over to game, and we need to find our animations. So if you go over here into data, we have images, we have entities, we have player. This is a lot of files. But then here we have all of our player animations. We have like idle. And then this is like 21 images. We've got jump, which is a single frame. So you might think of an animation as multiple images, but in this case, we're going to generalize it so that the player is described as having a state that is an animation. So even if when we're jumping we don't want to show multiple frames, we just load the animation of that one frame that we want to show, and we say, okay, we're on this animation, and that's how we'll implement that later. So we also have run, 7 frames, slide, 0 frames, wall slide, 0, well, it's actually 1 frame, not 0. But we have all those animations, we need to load them in. So you could write something fancy to load all these in automatically, but for this, it's easier, well, quicker, just for the scope. If you're creating a bigger game, I would actually write something to load this better, but for this tutorial, I'm going to do it by hand. So we'll do player/idle equals, and then we'll actually have to go up here, and in utils, we'll want animation. We'll do animation of load images. Remember, the first parameter for animation is the set of images we want an animation of. So we can just pass in what images we're loading here. We can do entities slash player slash idle, and then we'll set our image duration to 6 because I mean it's an idle animation. We want the animation to probably go a little bit slower because it's just kind of that the player is inactive and just kind of bouncing around or whatever. All right, so we have our idle animation. Now we need our run animation, and then this is just the same thing. You grab this, swap all those, and then I'm going to set the image duration to 4 because it's a running animation, so you're running, it makes sense for it to cycle a bit faster. A lot of this depends on how you actually drew everything. This is not a hard rule, it's just a number that makes sense for whatever your assets are, and in my case these are the numbers that make sense. You can play around with it if you don't like the durations. For all the remaining ones, I'll use the default of 5 because most of these don't even have multiple frames. So we have jump, slide, and wall slide. All right, so we should have our animations loaded here. We can do print self.assets, and we can see what we have. All right, so if we look down here, here's our stuff here, and you look, we have like player jump, and here's our animation object, and run, and idle, and stuff. And now the last step here is to actually use these animations to render something. So for that, we need to go over to our entities here, and we need to add a few new things. So we'll do self.action equals a blank string, self.anim offset equals, and then this is going to be a bit of a hack in animations because, say, the object that you're animating will have varying dimensions. Usually the way you do this is you add padding to the edges of your images so that you have space to animate the changing sizes of your whatever object you're animating. So for example, if I go over here and I go entities, player, run, let's look at 0. It's hard to see here. Right here, look at, there's all the space to the sides. And then if you look at, I don't know, maybe, oh, here's a good one. See, look, now this foot's sticking out a lot, so we need some of that space on the side. But if you remember, this player image does not have that padding. And if you actually go back to, let me close all this. If you go back, where is it, to our game here, our player's dimensions are smaller than those images we have. So a trick you can use is to render your images with an offset to account for that padding, so that our animations overflow outside of what would normally be the hitbox for the player. Normally you would have changed this offset for each entity. In our case, I think just setting it to -3 should cover everything. This is the value that the player needs. We can inherit from this and override it later if we wanted to use something different. But this is just the number that we're adding to wherever we intend to render the image, which will just offset where it's going to be rendered. All right. So we also want self.flip, and that's because the player should be able to look right or look left. We only have our animations facing in one direction, so we need to be able to just flip our images, which I'll show you later. Self.setAction idle. So this is the function we're going to have to do right here. We need to be able to set which animation we're currently using. So to do that, we need to create our function here. We'll call it DefSetAction. Self action, and these are just the string names of our actions. So if you remember, the player has the idle, run, slide, wall slide, jump animations. So it's just the string of those names, and then it will find the animation for that. So if action does not equal self.action, so we only want to do this if the action has changed from what we already have saved. Self.action equals action, so that's just updating it, and then we update our animation here. Equals self.assets self.etype, so that's the type of the entity. So it'll look for player slash, and then self.action, so it'll look for player slash run, for example. And then we want to copy that. That's, remember, our animations up here are in our assets, and they're these animation objects which we had the copy function for. We're just calling that copy function, which is creating a new instance of that animation. And this is why we need this case here to prevent it from being called if you set the action multiple times, because it's more convenient, I have found, to be able to just say this is the current action each frame, then to specifically determine when it should be changing. And then what we do in here is just say, check if it has actually changed because of this function call, or if it should change because of this function call. And if what we're setting it to is different from what we had, then that's when we want to grab the new animation, because the way it's going to work is we're going to say every single frame while we're running, we're going to say set action run. And if this were called every single frame, then if you remember over back here, we set frame equal to 0, and this will happen whenever you copy it as well. So it would be permanently stuck at the 0th frame. So this animation can only be created when you switch to the animation. All right, so now we need to be able to actually render our animation. So we go down to the render function here. And remember, we had this hack here where we just use the player. We don't want to use that anymore. So what we'll do instead, I'll comment this out for now, we'll do surf.blit pygame.transform.flip self.animation.image self.flip false. So this is just handling the flip part. So we have the flip attribute here that we created up here. We'll be updating this in the update function. And then we're using Pygame.transform.flip. So this is just, first of all, taking the output of whatever animation we have. This is where we actually get the current frame of our animation. And this is why I mentioned that I think it's better in our use case to just take the image of the animation rather than creating a render function. And that's because we might want to do something like this, where we flip our image before we render it. So we flip our image, and this is the x-axis flip, and this is a y-axis flip. So we don't want to like flip it top over bottom. That there's no use for that in platformers for the most part. Like for entities, usually it's like facing right or facing left. You don't face up and down. Some entities you might do that, but for most of them this will be sufficient. All right, so this function here will output the flipped image that's appropriate, and then we can work on our position here. So for our rendering position, we'll do self.position 0 minus offset 0. So that's the camera offset. But then we also have that other offset, which is the animation offset. So self.anim offset 0. And then we do the same thing for the y-axis, which is self.position 1 minus offset 1 plus self.animation offset 1. So that's a bit of a long line, but there's all these different offsets to account for. But they mean different things and they have different uses, which is important. All right, so let's go ahead and delete this line. And that's our new render function there. The next thing is we'll need to be able to update our animation, and that's simple. We just go over here, and this is the update function right here. We do self.animation.update. All right, there's just one more step that we could do right here in this object, and that will be the flip. So we'll do if movement 0 is greater than 0, self.flip equals false. If movement 0 is less than 0, self.flip equals true. So if you remember, our assets are facing right. It would be the inverse if they were facing the other way around, where our assets are facing right. So if you're moving right, which is what this case is, we set flip to false because we don't want to flip our image because it's already facing right. But if you're facing left, or well, you're moving left, our images are facing right, so we have to flip it, and that's why we say flip equals true. All right, so that should be everything for this class here. I'm actually going to create a new one, and this is where we get into a bit of the fancier stuff. We're going to create a player class. So we do class player, and we will inherit from the physics entity, and we'll do def init self, and I'll take a reference to the assets because it'll need that. Position, size, and we'll do super.init. So this is just calling the init function from the physics entity. Actually, wait, we don't want to reference to the assets. We need a reference to the game. And also the mistake over here that I made. And the reason this is happening is because in my reference code, I didn't do the full object-oriented stuff the same way I'm doing it here, but that's not super important. Anyways, so the mistake here is this needs to be self.game.assets. So we're here, this is .assets. All right, so anytime there's .assets, actually that's the only one, so that should fix it. But yeah, so we pass in to the initialization function for the physics entity. We pass in game, position, size. Actually, and there's one extra thing. It's game, position, size, but then we have our entity type. And because we're dealing with our player here, we know that the type is going to be player. And actually, wait, I know another mistake here. So that should be self.type. But anyways, so we're passing in our type that's used here to look up our animations, and we know that that's going to be the player for our player. So we just pass it in here. We don't have to put it in as an argument there. We could if we wanted, and there are use cases for that, but this is fine for now. So now we need an update function for our player. Self tile map movement equals 0, 0. And we want to use the default update function tile map movement equals movement. And then this is where we get into some of the magic. So we want an extra attribute for our player here. We'll do self.air time equals 0, and this will just keep track of how long we've been in the air. So self.air time plus equals 1. And the objective here, the reason why we're inheriting and adding our own code here is because each entity, well, not necessarily each entity, but different types of entities will have different animation logic. So we're writing the animation logic for our player. And that's why we separate it with inheritance here. All right, so we do if self.collisions down self.air time equals 0. And then if self.air time is greater than 4, we'll do self.set action jump. So if you're in the air for a while, you want to show the jump animation. All right, and then elif movement 0 does not equal 0, self.set action run. So if the x-axis of our movement is not equal to 0, that means we're moving horizontally, which means we're running. So, but if you think about it, if you're in the air, you probably want to override the run because you don't want the player to be showing an animation of running in the air. You probably want to override run with jump. That needs to be higher priority. So by doing if and then elif here, we're saying this one right here is the highest priority. And then if this is not the case, then we can move on to this one and say, okay, are we running? And then if not, if we're not jumping and we're not running, we're probably idle. Self.set action idle. All right, so we have 3 animations. Those other ones are for extra things. We'll get to that later. But we have our 3 animations implemented. So the last step here is to actually use our player class. So we're going to go over to game here, and we're going to take from our entities and go player. And when we create a player, we want to do player and remove that. And now we're instantiating a player, which is inheriting from the physics entity instead. All right, so if we run our game now, I still have that print statement. So you can see there's an idle animation of me just standing there. And if I run around, you can see there's a running animation. If I jump, you get the jumping animation or the jumping frame. So that's how you do animation. It's a pretty simple concept, but there's a lot of random stages to the implementation. Animation is all about just showing different images at different times, so it's fundamentally not that complicated. It's just that it's nice to have different levels of abstraction that make things easier to work with. Because in the future, if you want to add another entity, you pretty much just have to load in the assets and you say, well, create another object like this, and then you write the custom logic right here and you're done. And also I forgot the extra thing I didn't really point out was that you can face right, you can face left, and that's based on where you're moving, which is nice. All right, let me just remove this last print statement here. And we're done with animations. Woohoo. With our animations done and our tile system optimized, you might be thinking that our world here is looking a little bit empty with these 2, I guess, slabs or whatever of tiles. So it's time that we start to fill out our world. But placing tiles by hand or by just coding up the individual tile placements is pretty tedious. So oftentimes it's a lot better to use a level editor. For some games you'll write a map generator or something like that, so that it's all dynamically generated, but for most games you're going to need to touch a level editor at some point. There are plenty of good level editors out there, but a lot of them are lacking in flexibility in certain areas, so I prefer to write my own. And additionally, there's a lot of random things that are going to come up if we do write our own editor, which we will be, that are unique topics in themselves that are useful to know about. So for example, by default, this game I'm working on won't have any mouse input, so working on a level editor will make it so that you can learn about that here in this tutorial. So when you think about a new, project, one of the important things to think about are inputs and outputs. So in a level editor, you're inputting your keyboard and mouse input to create a level, and then the output is some sort of file that represents your map. It's also worth noting that if you want to be able to edit a previously made map, you also need to be able to load that map back in. So that means that one of the core features that our level editor is going to be dependent on is the ability to be able to save and load map files. So you might be wondering, how do we save our maps? One primitive technique, which I think I alluded to earlier, is to just have a grid of numbers, for example, where you could just do 0 for air and 1 for ground or something like that. That's pretty much the most primitive you can get. What we'll be using is something called JSON. It's a file format for storing objects that basically fit into the format for how Python stores dictionaries and lists and values and strings and stuff like that. So it can't store things like objects or classes, but if we encode it into things it can understand, and that's like the dictionaries, lists, and stuff like that, then we're able to store it and then load it back in. So one of the major differences between Python's dictionaries and lists and JSON is that JSON has no support for tuples, and all of the keys for dictionaries must be strings. And if you remember back here, I think I mentioned that, for example, for this location thing, it would have been easier if we could have just taken the tuple of X and Y, because you can actually use that as a key for a dictionary. But for saving files, you can't have that as your key because it will be interpreted as a list, and then that can't be easily converted into a string, and then you run all sorts of other problems. So we have to sort like a string like this. In higher level use cases, so what I actually use is I created my own function for saving and loading stuff like this, where it's built on JSON, but then I added support for tuples. That's a bit of an extreme case, but that's a direction you could take this in if you wanted to do that. Anyway, so for what we'll be using here, this format's fine, just the string, semicolon, string. If you're wondering where JSON comes from, JSON actually stands for JavaScript Object Notation. It was originally made for JavaScript and dealing with JavaScript objects, so it's naturally meant to represent objects, so it works well with tile maps. If you work with actual level editors, you'll find that you can actually export to JSON usually. Either that or it will have its own custom file type. And by the way, while I will be making a level editor to show you some useful features with Pygame, don't feel like you have to be using your own level editor. After this tutorial, you could go out and get a normal level editor, and then you can just write a way to interpret that into a tile map. So you would take this tile map object here, and you'd probably have like a load function. You take whatever that level editor is outputting, and you figure out how to convert it into what you need. Or you can build your tile map system around whatever the level editor provides. But in my case, I can make things work very nicely if I just write my own. So to get started with our level editor, we'll probably want to make another script here, and I'm just going to go new file, and I'll call it editor.py. And then I can go over to game. I'm just going to copy this whole thing, and then I can go back to editor, paste this in. Instead of calling it game, I'm going to call it editor. I'll go down here, call this editor, and then let's trim down what we're actually using here. So we won't need load image. We will need load images, and we will need a tile map, but we won't need like players or entities because this is for tiles. We don't need the clouds, obviously. And then let's add a constant here called render scale, which will determine just how much we're multiplying the size of each pixel. So let's change the name here to editor, and then let's go over here and let's trim down all these assets. We don't need most of these. We just need the ones we're making our world with. So for this here, I'm going to take this movement thing, and we will be using this surprisingly because you'll want to be able to move your camera around. So we'll do false, false, false. Instead of moving right and left, you're going to be able to move the whole camera instead of a player in all 4 directions. That's why we need 4 values here. All right, so let's remove some of this stuff. We do need our tile map, in fact, because we're making a level editor, so we can keep that. We'll also want to keep the scroll because, well, we're going to be having a camera that we move around still, so we need to keep that. And let's go and trim down this stuff over here. So we don't need a whole lot here. We can just delete all that and change the background to black. And then there's a couple things right here we can use. So let's remove these, and let's say if event.key is pygame.kup, self.movement2 equals true. And then we can go over here and say k down and say movement 3 equals true. So now we can copy all this, go over here, paste, and then switch these trues to falses. And then this will automatically update our movement thing here, so we can start moving around with that. But we don't have anything to see yet, so there's nothing here. So let's just run this real quick and make sure that it works. Oh, we actually don't. This is not supposed to be bullet, that's supposed to be fill. Alright, so we have our editor. It's just completely blank though, because, well, we don't have anything to show yet. So the first thing we're going to need is the ability to select our tiles. So normally I would create an interface where you can click the tile you want to use, but because I'm trying to keep this simple, I'm going to make it so you just press buttons to change which ones you're using. So let's say self.tilelist equals list assets. So, or self.assets. This will convert our assets into just a list of these values, because if you run list on a dictionary, it just gives you the keys. So it's giving me decor, grass, large decor, stone, etc. So that'll give us the 4 values there, and then let's do tile group, or self.tilegroup equals 0, self.tilevariant equals 0. So with these 2 variables here, we'll be saying which group are we using. So we're using grass, decor, etc. And then the tile variant will be which tile in that group are we using. So we'll have different buttons for changing between the group and the variants, and that way we can rotate through our different tiles in a more efficient manner. Alright, so let's go ahead and write something for showing which tile we have selected. So in our for loop here, we will need to calculate what our current tile is. So let's do current tile image equals self.assets. We'll do self.tilelist, self.tilegroup. So this is going to be one of the more messy indexing situations again. And then self.tilevariant. And we'll want to copy it because we'll want to show it with an alpha. So current tile image set alpha 100. So what that'll do is it'll set it so that this image is partially transparent. If you set it to 0, it will be fully transparent. If you set it to 255, it'll be fully opaque. So we want it to be a fair bit transparent because we want to be able to see what's behind it. This is supposed to just be a HUD thing so we can see what we're doing. So we can do self.display.blit, and then we'll say current tile image, and then we'll put it at 5.5. Alright, so if we run the editor now, you can see that we have a tile up here. So that's just our grass decor, because coincidentally decor is the first value of our dictionary here. So with that, we can now see which tile we have selected. And if you're confused about this right here, you can kind of just dissect it. You can print out the different stages of it. So you can like take this part here, you can print that out. You can take this part, you can print it out, and you can take this whole thing and print it out and see what's going on. But what we're doing is we're taking from our list of tiles, we're using the index that is our group. So this will be an integer that represents the index. And then we're selecting from our assets that group, and then we're grabbing this tile variant, which is another index. Alright, so now we need to be able to switch which tile we have selected. And this is where I'm going to introduce something new. So we have if event.type is pygame.mouse button down, if event.button is 1, clicking equals true. So we're doing a couple of new things here. So first of all, mouse button down, that's a new event type. So remember, we've been using key down and key up. Mouse button down is when you press down on a mouse button. So, or it's not necessarily that, because it's more like when you activate a mouse button, because it also can trigger on your scroll wheel, which we'll get to later. Actually, wait, sorry, for this clicking thing, we'll need self.clicking equals true, and then, or false rather. And then we'll put it to true here, there we go. But so mouse button 1, that's your left click. So we'll set clicking to true there. Now you might be thinking, well, if left click is mouse button 1, is right click mouse button 2? In fact, it's not. You're looking for 3. and we'll set self.right-clicking equals true. And then I'll throw that up here. We can go false. All right, so if right-clicking is 3, what is 2? Well, you could look up in the Pygame documentation to see, but for 2, it's actually when you press down on your mouse wheel. So there's a couple more that we're actually going to be using here. We need to be using 4 and 5, and 4 is when you scroll your mouse wheel up, and 5 is down. I think it might be the other way around. I always get this mixed up, but I think 4 is up. So let's do if event.button is 4. Let's say tile variant, self.tile variant. Actually, let's do group here. Tile group equals self.tile group -1, and this is using that modulo trick I was talking about earlier, where you can get something to loop by using modulo, and we're going to subtract our tile group here, and we'll be modding it by length of tile list, so or self.tile list. So when you reach the end of that list, it'll just loop around to 0. And then if you go less than 0, it'll go to the end of the list. So that's convenient. That way we're forcing our index to be in the bounds of what groups we can even select. So now we can take this and then also go do 5, which I believe to be is scrolling down. So we do +1 to scroll down, and then mod it by the same amount, and that will also loop. So now we can select which tile group we're using by using our mouse buttons here. So if I run the editor and I scroll up, you can see the tiles are changing on the top left. So these are our different groups. So we have our grass, our decor, our stone, and our other decor. So we can now scroll between groups, but we need to add something so we can scroll between variants. So to do that, let's go ahead and add self.shift. I'm going to use kind of a key combination for this, and I'll say if event.key is KL shift. Note that I'm not doing right shift here. Shift equals true. You could add right shift too if you wanted, but I'm not worrying about that right now. So now this shift variable will toggle based on whether or not we're pressing shift. So what we can do over here is we can say if shift or self.shift, we do this. Otherwise, we do that. And then what we can do here is we can swap the tile group with the variant. So we say tile variant. So if you're pressing shift, we'll scroll through the variant. And if we're pressing or not pressing shift, it'll scroll through the group. So we do this. But the one thing we do have to change here is that the thing we're modding by can't be the tile list again. It needs to be the number of variants that we have instead of the number of groups that we have. So to get that, it's kind of based on this thing up here. So we just do the length of self.assets, self.tilelist, self.tile group, and then that will give us the number of variants. All right, so we can take these, and if we run it again, I can scroll as I did before and go through the different variants. But if I go to, like, say grass here and I press shift and start scrolling down, you'll see all the, or sorry, this scrolling without shift goes through the different groups, and then if I press shift, it'll go through the different variants within the group. Something I just noticed I forgot though is that you want to make sure that if you change the group, you set the variant to 0. Otherwise, you could run into some index errors. So we'll want to do 0 here. And it makes sense. If you change which group you're looking at, it makes sense to go to the first item in that group. So if I go to grass here, go to like a variant down here, and then I go to the next thing, it'll go to the very first variant of that group. All right, so we now have our tile selection working. So now's the fun part. We need to be able to place stuff. So if you notice, I already wrote some stuff for clicking. We do need to do a couple things to finish this off. We need if event.type is pygame.mousebuttonup. And we can do if event.button is 1, self.clicking equals false. If event.button is 3, self.right-clicking equals false. So now these clicking variables will be updated based on whatever our mouse state is. So let's go over here. And this is where we need to start rendering our tiles and doing all of that magic. So let's start by rendering our tile map, which we can do right over here. We can say self.tilemap.render, self.display, and then we can give it our offset, which We need to set up this render scroll thing again. If you remember, we need to convert our scroll here into an integer thing. So we can do render scroll equals the int of scroll or self.scroll 0, and then int self.scroll 1. All right. So we have this render scroll thing, which is the truncated version of our scroll. We throw it in as our offset there, and our tile map can render. We can run this, and actually, in fact, I forgot about something. We have this code right here that automatically populates our tile map, which is fine. So we can see that there is something there now. But we want to be able to place tiles. So to do that, let's go down to here, and let's say mouse position equals pygame.mouse.getPosition. So this is a new thing as well. So this will give you the pixel coordinates of your mouse with respect to the window. So if your mouse is in the top left of the window, it'll give you 0, 0. So what you can do with this is you can use this to figure out where your tiles should go when you're clicking. Something you do need to be careful about is that we're actually scaling our image up here so that our pixels are actually 2 pixels now. So we actually have to scale down our mouse position to get the correct coordinates. So we can do m position equals m position 0 divided by render scale. And that's why I wrote this constant beforehand. And then we do m position 1 divided by render scale. So that's what that constant right up here is for. That's so that we can divide right here and get the correct mouse coordinates. All right. So with that, we can say tile position equals, so this is going to be what our mouse's position is in terms of the tile coordinates. So we've done this before, but with other things. So we'll want to say int of the mouse position plus the scroll, and then we can divide by the tile map size. And then, actually these need to be self again. Then we can do mouse position 1 plus self.scroll1 divided by self.tilemap.tile size. And that will give us the coordinates of our mouse in terms of the tile system. So with this, we can say if self.clicking self.tilemap.tilemap, and then this is where we're assigning our new tile here. We can go string of tile position 0 plus, and this is the weird string thing we have to do, tile position 1 equals type, and we'll want to say self.tilelist and then self.tilegroup. So this is converting our index selection into the string name for the group. And then we need to take our variant, which will be the self.tile variant. Fortunately for us, this one is just an integer, the way that we store our tiles, so that makes things easier. And then for the position, we can do the tile position. All right. So with that, we should be able to place tiles now. So here I've got my grass decor thing, and if I switch over to actual grass, then I can place that by left clicking, and I can place rocks and stone, and I can change the variance. So that's all nice and all, but we need to be able to delete tiles as well. So for that, we can do if self.right clicking. We'll do tile location equals, and this is just a string lookup, so don't confuse it with this. I use position and location interchangeably, but they do mean separate things here. Not because of the name of the variables, but I'm using them for something different. So we do tile position 0, and then string tile position 1, if tile location in tilemap.tilemap, or self.tilemap.tilemap. That means that this location that we're hovering exists, or the place that we're right-clicking exists. And if it does exist, then we can do del self.tilemap tile location. So with that, I can run the editor, and I can, oh, it crashes. And I need one more tile map there, because we need the tile map attribute of the tile map object. So now if I right-click, we can delete all these tiles that are already there. And while we're at it, since we can now place tiles, let's go ahead and remove this code here that adds in tiles by default. All right, so with that removed, we can go back to our editor here, and if we run it, our pre-placed tiles are no longer there. So there's a couple extra things we need to be able to do. So first of all, it would be nice if we could see kind of roughly where the next tile would be placed. So to do that, we can say right here, self.display.blit, and then we'll do current tile image. And we want to show it at the tile position 0 by tile map.tile size, or self again, minus self.scroll 0, self.tile position 1 by self.tile map.tile size minus self.scroll 1. All right, so what that's doing is it's taking the, or actually that doesn't need to be self. It's taking the tile position we just calculated here, and then converting it back into pixel coordinates by multiplying it by the tile size. And then we're adjusting that position based on the camera for rendering. Because if you remember, we added scroll right here, so we need to remove it right here because we're going to show an overlay of where the next tile is going to go. All right, so if you're confused about why we're going through all this extra effort instead of using the mouse position to show this indicator, it's because we want it to be aligned to the grid. And the part that does the aligning is right here on this division. That will force it to be aligned, and then we scale it back up into pixels, and then it will be snapped to the grid, which is convenient. All right, so with this, if we run this, we can see where our next tile is going, which is very nice. So if I go right here, I can go down into a tree, and you can see, look at that, I can see where my trees are going before I even place them. So now we did all the stuff with scroll, but it would be nice if we could move our camera. So to do that, we just used some of the simple tricks we had before. We can say self.scroll 0 plus equals self.movement 1 minus self.movement 0, and we'll multiply by 2 just to make it move faster. And then we'll do 3 and 2 for here for the y-axis. If you remember, this is if you're holding down right, minus if you're holding down left, and this is down and up. So all of this adds up to figure out how much you should be moving your camera by here. And then we just multiply it by 2. So that will move our camera based on our keyboard input here. So if I do, you can actually see it without me even placing anything because the grid's moving around. I can move around and things are moving, which is nice. So if I draw these things, I can move around and look at things, which is convenient. All right, so the next thing I'll want to do here is probably, it would be nice if instead of using these, we could use WSD because we're drawing with our mouse. So let's do KA because that's left, KD, KW, KS. And then we'll have KA again, KD, KW, KS. So now we can move around with WASD, which is much nicer. All right, so now that we can move our camera around and we can place tiles, the next thing is to be able to place things that are not on the grid. Because if you remember from the beginning of the tutorial, from what I showed you for what we're making, there were a lot of tiles that were not on the grid. And we did all that code that I mentioned that we weren't using quite yet for rendering tiles that aren't on the grid. So let's add a variable here. Let's call it self.onGrid equals true. And then let's go over to here and let's say if event.key is pygame.kg, and then that will be not self.onGrid. So what we're doing here is we're making it so that this variable here represents whether or not we want to be drawing tiles on the grid or not. And then if you press G, it'll switch it. So if you just set something or a boolean to the not of itself, that just flips it, whatever it is. So we can now start writing some rules for how things will be placed depending on whether or not we're on the grid. So the first thing we got to do is update our indicator, because our indicator assumes we're snapping to the grid, which only happens if you're rendering on the grid. So if self.onGrid, we do this. But if we're not on the grid, we do, and this is the simpler version that you might have thought of at first, self.display.blit, and then we take the current tile image and we just throw in the mouse position, and then we don't have to do all of this crazy math to figure out what the snap grid position should be. All right, so if we run this now, I could just play some stuff, and then let's pull out the tree, I guess. So you can see the tree snapping around. If I press G, it becomes smooth. But it's still placing on the grid. We need to make it so that we can place off the grid. So for that, we need to modify this code right here. So we do if clicking, and in fact, we need to do if clicking and self.onGrid, we do this. Now, we don't want to place a tile every single frame off grid just because we're clicking, because there's no grid value that we're overwriting. Instead, it would just place 64 tiles per second, or not 64, 60 tiles per second because we're running at 60 FPS down here. So we don't want that. We want it to be, because off-grid stuff is not snapped to anything and we're not overriding anything, we want it to be able to just place a tile when we click and just press down that button. We don't want it to be placing non-stop. So you would click for each tile you want to place. It's just the easier way to do things. So for that, we don't need an extra variable or something to keep track of that input. We can just go right in here to the clicking thing for mouse down on 1, and we can write it here for placing. So we can say if not self.onGrid, we can say self.tilemap.offGrid tiles, and that's that list we had before, that append, and we'll say type is tile list, and this is pretty much the same stuff from before. So self.tilelist, self.tilegroup, and then we want the variant, which we know is just the self.tile variant. And then the position will be just the mouse position 0 plus the scroll self.scroll 0, mouse position 1 plus self.scroll 1. And if you're wondering why we're adding the scroll to our mouse here, and we did a similar thing with placing stuff on the grid as well, the reason is that from the camera's perspective, the top left is 0, 0. But in the world's perspective, let's say that your camera's 100 pixels to the right, and you place it at the coordinate 0, 0 in your window. Well, the coordinates in the world for what 0, 0 on your window is becomes whatever the coordinates for the camera were. So we actually have to add the coordinates of the camera to convert from the display space, so where you're clicking on the window, back into the world space. So if you remember from the tile rendering, it's actually the other way around, where you have to convert the world space into window space by subtracting the scroll. So it's just doing the same thing and you're just flipping it. So we should now be able to place our tiles that are off grid. So if I press G, I can left click and I can place stuff that's not on the grid. So if I draw these right here, you can see those flowers were not aligned, which is nice. But now we can remove all of those flowers that are on the grid, but we can't remove the ones that are off the grid. So we need to be able to add that too. And for that, this is where things get a little bit messy. This is the unoptimized way to do it, but for level editor, it's probably not going to be a huge issue. If you're lagging a little bit when you're using your level editor, it's not a huge deal. You should be more concerned if your player's lagging from playing the game. So we can do some bad code in here. So we'll say for a tile in self.tilemap.offGridTiles.copy. And the reason we're copying here is because we're going to delete if this tile is touching our mouse. So we don't want to mess up our iteration. So we just take a copy of the list so that we don't get the reference. So we can calculate our image. For our tile here, we can do tile image equals assets self.tile type tile variant. So this is like when we were rendering the tiles. So we need this image to be able to compute what the bounding box or the hitbox of this off-grid tile should be, because the trees are a lot bigger than the normal tiles. So we want to take the image to figure out how big of a hitbox it should have for deletion. So we can now calculate that hitbox. We can do tile r equals pygame.rect, and we'll say tile position 0 minus scroll or self.scroll 0. And remember, this is because we're converting our tiles or world space into display space because we're about to try to collide it with the mouse. So we can do tile position 1, and you could actually do this the other way around, where instead of subtracting the scroll here, you could actually add it to the mouse's position to do these collisions. But we can do it either way, and I'm just choosing to do it this way. So we'll get the width of our image, and that will be the width of our rectangle here. Tile image.get height, and we can do it for the height. And now we have all of our 4 parameters for our rect, and we can do if tile r.collide point. I don't believe I've shown you this yet. So with rects, you can collide with other rects, or you can collide with a point. So instead of passing in a rect now, we could just pass in a point and it'll tell us if it's colliding. So in this case, we'll just throw in our mouse position and say, is this tile colliding with our mouse? And we can say if it is, well, we can do self.tilemap.tile, or actually no, off-grid tiles.remove, and then we want to remove this current tile. So with that, we should be able to remove our off-grid tiles now. So here's some on-grid ones, and then let's place some off-grid ones. So let's do that. So we can remove the on-grid ones and the off-grid ones now, which is nice. So that's pretty much the basic functionality for a level editor. The next step is the thing I was talking about at the beginning, and that's the loading and saving part. So for this, we'll actually have to go back to our tile map code here, and we have to add some new functions. So we need a load function and a save function. Let's do save first, because you can't load anything until we've actually saved something that we can load. So let's do save. We'll take self, and we'll take a path to save to. And then we just do f equals open path w. So this is just normal file handling in Python if you haven't done it before. I'm going to import a new library up here. We're going to do import JSON. So this is the format I was talking about before. So fortunately in Python, there's a module that makes this really easy to work with. So all we have to do, and this is super simple, json.dump. And then we want to throw in a couple things. So we'll say the tile map, and this is like a dictionary, remember? So we need to split up our information here. So we have a tile map, which is all this tile data on the grid. So we'll do self.tilemap, and then we'll do tile size, which is the size of the grid, and then off grid. So this is all the off grid tiles. So self.offGrid tiles. And then this dump function, as you can actually see here, VS Code is telling me, it takes the object we want to dump and then the file pointer. So that will be just F. So we told Python open this file, and then we're telling it to dump this object right here into this file, and it will convert it into JSON for us. Now if we do f.close, it'll save it. So if I go over to my editor here and let's say create a new key binding, let's do event.key is pygame.k, and I really like to use O for this because I think O is output. We are already using S for moving the camera down, and I don't want to do like Control S because then I have to go add the control key. So I like O. It's also far off to the right, so you're not going to accidentally press it. So self.tilemap.save, and let's just call it map.json. Remember, the parameter we give it is the path that we're saving to. So now if I run the editor, and let's just place a basic setup here. So let's just place some tiles, do this. So we've placed some tiles, and let's do some off-grid ones too. So let's find our tree, and we'll place it off-grid. Look at that. We got some trees. And then we can go and place some of this, these flowers here. So if I press O, you can see over here on the left that I had a file pop up, and this is the file we just saved. So this is kind of hard to read like this. I actually don't know how to turn on the wrapping on VS Code. Presumably there is a way to make this wrap, but we have all of this data here. So we have tile map, remember that's where we dumped all our tiles, and you can see this is the key, this is the type, the grass, variant, position, or variant position, and it just looks like it's just a Python dictionary and list, like I was mentioning. So it's almost one-to-one. Like I said, it gets rid of tuples, so these were tuples for us before, I believe, but they've been converted into lists. But aside from that, it's pretty much one-to-one. And you can see over here, and this is the off-grid stuff. You can see I placed stuff at half pixels. That could cause problems. I think we should be fine because of the way we're converting our scroll to integers though. So you might want to be careful with that and like truncate your positions for the off-grid stuff if you're doing certain types of operations. It's just something to think about if you start running into issues with like collisions or something, or jitteriness in rendering. But in our case, I'm pretty sure it's fine. All right, so now that we've saved our map, it would be nice if we could load it. I won't create a load key binding because if you create a load key binding, then the expectation is that you can browse files and select something. I actually have that in my level editors that I actually use, but it's not super important. You could implement it with Tkinter, and that's how I do it, but I don't really want to get into that because that's not Pygame, that's something else. So you would hook that up with Pygame to do the file loading, but for our case, we'll just assume that we're loading from a certain path. So the way we'll do this is we'll go over to here and we'll say self.tilemap.load, and we'll have to fill this function later, and we'll say map.json. So if that file exists, it'll load it. So the next thing we'll have to do is say try except file not found error pass. So we only want to load the map if it exists. In our case, it does exist, but we need to create this load function now. So here's the other end of the nice stuff with JSON. Def load self path, and this is why I put all that effort into making sure that the data structure was easy to fit into this form, because this makes the saving and loading so much easier. We can do f equals open path, and instead of writing, we're going to read now, and then JSON.load, and you just pass in the file pointer, and then we can say our map data is equal to that, and then we just close our file. Oops. Now with our map data, we can start assigning things. We do self.tilemap equals map data, and this will come in basically as you see it right here. So it'll be like a dictionary with tilemap and everything. So we just do tilemap equals map data tilemap, and then we just go through here and we do tile size, and then we do off grid, and then that will be off grid tiles. And now if I run the tile map, or not the tile map, the editor, we see our thing is loaded back in that we saved before. But if I delete this file here and run it again, we get an empty thing to work with. So that's convenient, but you might be thinking, okay, we have this nice level editor and everything, but it's really tedious to take something like this and deal with all the different tile types you have to think about. So you have to go through here and switch your variants and do all that stuff, and then you go like this, and you just keep going like that, and you have to go through all these different tiles, and eventually you get most of what you're looking for, but it's very tedious to go through here and do this all properly. So instead of doing that, I'm going to implement something called auto tiling, where it can take all of the tiles that we have and figure out what variant each tile should become. So this is just an algorithm that we apply to all of our tiles, where it looks at all the neighbors and figures out what it should be. Another feature that I would normally add, but I don't want to get into because it doesn't really benefit you much to learn about it here, and it's a bit tedious, is to do flood filling. That's something that I have in all my level editors, but fortunately in our case we won't have to deal with too large of areas. We're mostly dealing with floating islands, as you'll see in the game later. So flood filling is not super important. Auto tiling, however, is. Fun fact, my first Steam game, Super Potato Bro, I made without auto tiling. I actually did have to go through all the different variants by hand and place them where they should go. It was super tedious. Alright, so let's go over to tile map here. And that's actually something interesting to note, is that my game Super Potato Bro was, I guess, technologically inferior in many aspects to this tutorial. So what you're learning from this tutorial is past what a decently performing game on Steam had, although that was in 2018, so 5 years ago. So in here in our tile map, we'll want to create our auto tile function. So we don't have any parameters for it. We just call the function and it should auto tile everything. So let's just do def auto tile self. And we just iterate through all of our tiles. We don't want to do the off-grid stuff because, I mean, how can you figure out the neighbors for an off-grid tile? But for the stuff on the grid, you can look at the actual proper neighbors. So we do for location in self.tilemap, tile equals self.tilemap location. So that's just the location string, and then we're using that to get the value. And then we can get neighbors equals set. So what we're going to do here is we're going to look through the different neighbors. So let's do for shift in, these are different offsets we're looking at. So 1, 0, that's one tile to the right. Negative 1, 0, that's one tile to the left. We'll do 0, negative 1, that's the tile above, and the tile below. So for that, we can now create a location that we're looking up. So we can do check location equals the string of the original tile's position on the x-axis plus shift, so what neighboring tile we're looking at, and then we can do plus the string of that same tile again, and we just do the y-axis plus shift. All right, should be shift 0 and shift 1. All right, with that, we now have our check location. We're going to do if check location in self.tilemap, and then we can now do stuff here because right when this pass is reached, that means that that neighbor exists. So it's time that we go and define what exactly we want to do with auto tiling. Oh wait, we actually have neighbor offsets here, but we're using a different set of neighbors because this one is for the tile collisions where you need the diagonals as well as just the actual edge bordering ones. We don't need the diagonals for auto tiling. You could do auto tiling the diagonals and add extra cases for that, but our tile set doesn't do diagonals, so we don't have to do that. Anyways, so we want to specify which tiles we want to auto tile. So we'll say auto tile types equals, and we'll do grass and stone. Funny enough, it's the exact same thing as the physics tiles, but if you wanted to separate them, you could. All right. The other thing we need is an auto tile map. So this is going to be the rules that we use for auto tiling. So this is going to be a little bit funky. We want to say that if we have certain neighbors, then we should have a certain variant of the tile set being used. So let's say, for example, tile variant 0. If you remember, that's the top left tile in the tile set, because it was the very first one selected in the editor when you go to that group. So it's the top left one. So the top left should be placed if there's a tile to your right and a tile below. So for example, if you want that, that would be the tuples of 1, 0, and 0, 1. So that would be to your right and below you. So if these are your neighbors, then we would want to say use tile 0. So that's how this auto tiling thing works. You could add extra rules as well. So you can add, like I mentioned, the diagonals. You could add that to your offsets down here. And you can add rules over here. So it's like if you have certain diagonals, you follow these specific rules. So you can go crazy with this, but we just need some simple stuff. Now, something you have to be careful about is that the way we're going to be doing this is we'll take the list here of these two things. And because you can't use the list as a key, well, you could do a tuple. But the problem with using a tuple like this is that what if, for example, your neighbors are these two, but it comes in a different order. If you do this, then that's not a value in this map. Well, this order will depend on what order you go through your neighbors right here. But the hacky way to make sure that you get the order correct is to just run a sort on it so that it'll come out in the same order every time. And that way you can actually look up the neighbors properly. So what we'll do here is we'll take this as a list and then we'll run sorted on the list. So that way this list will be the same order no matter if you write it as this or if you write it like that. So it will convert multiple different arrangements down into the same key. But you can't use a list as a key, so we have to make this into a tuple. So that's a bit of a hack, but it works. So there's a few or several other rules we have to do here. So we have to do, we'll go one at a time. So I'll just paste a bunch. Actually, I won't paste them all because it's easier to do them as neighbors. All right. So we'll do this one. So that means you have a tile on your right, below, and to the left. This is tile number 1. If you want to look through our images here, you can see how these are arranged. So we have grass, and you can go top left, middle, top right, right, bottom, bottom left, left, and then middle. So that's how that goes, and we just have to go through and write down all the rules here. So I'm going to go through this really quickly. You can figure out just by looking at these numbers what they should be, but it's not super important. You won't be learning anything new, so I'm just going to do this real quick. All right, so I wrote all these rules here, and this should be the rules for mapping out our auto tiling, and we can go back down to here and finish our auto tiling function. All right, so if the location is in our tile map, then let's say if self.tilemap check location type is tile type. So we want to make sure that the neighboring tile is the same type as the tile itself, or rather the same group or whatever. So we don't worry about if it's a different variant, but if it's a different type, we don't want to be auto tiling with it on the border. So like if you have a piece of grass and stone next to each other, you don't want them to kind of join in on the middle. It doesn't make much sense visually. They should have a border with each other. All right, so if it meets those conditions, we can say neighbors.add, and then we'll add in shift. So that's the neighbor rule that we had. And then we can convert this neighbors equals tuple sorted, and that's the thing we were doing before, so that it comes out in the same order as that set we had before. And then now we can say if tile type in auto tile types and neighbors in auto tile map, then we have a match, and we can do the variant equals the variant for that rule, which is auto tile map and not type. That's going to be neighbors. All right, so that's what we need for auto tiling. So now we just have to go back to editor and bind it to a key. So let's just go ahead, and I'll have to use the key T for this. Event.key is pygame.kt. So we do self.tilemap.autotile. And then if we run the editor, hopefully this works first try. We just place all these tiles right here, and then if I press T, it looks like it works. So it converted all of those mess of tiles into what we needed. So something to note is that if you, for example, do this, if you remember, we don't have a rule or even a tile in our tile set that can represent this. So you have to be careful about your shapes. If I press T here, there's no rule that meets that requirement. But if I add in a second strip there, it does exist as a rule. So you have to be careful about what types of things you're drawing with, unless you actually add those extra tile types, but we don't have them. Our tile sets are just the 9 tiles that form this shape. So we can't do anything where it's like one tile sticking out like that or something. So in fact, even just a tile by itself, we can't do that either. So you have to be careful about those things. That's just something you have to do in your level editor. If you want to do a more rule generation thing and then auto tile that, and you end up with stray tiles, then you'll probably want to update your tile set to support that, and then you'll change your auto tiling rules. But for our needs, this does what we need. We can create something like this, and then the grass shows up nicely. All right, so I'll make an example level here. I actually have pre-made maps, so that's what these are. You can look in here. And oh, why does VS Code show this one properly but not the others? That's funny. So this one, you can see, look at all this data. That's a map. But I'm going to demonstrate how you can do it first, and then I'll use those pre-made ones because you're not going to learn a whole lot from me just sitting here using the level editor for an hour. So let's just make a basic one just to show you. We can go create this, we'll do that. And actually we do need this now that I think about it, because there's extra stuff in that tile map that I haven't introduced yet. So we'll have to get to that later, but that's for the enemies and stuff. We'll get to that in a bit. So we can just create a basic map. We can do, oh, I don't want that. So I can like place the different types of flowers as well. And then I can go over to the stone and we can make that, and let's say that, and I can auto tile those. And then let's put in some off-grid tiles. Can put in some bushes and some trees, and then I believe where's the crate? Oh, it's over here, isn't it? Yeah, here's the crate. So I'll put down some crates as well, and let's put down one more rock. So that rock will go there, and then if I save that, I can do that, and then I can go back to game. And for now, I'll actually load the map from here instead of using the maps folder that has those actual maps, because we're not ready for that yet. So let's do self.tilemap.load, and we'll just say map.json. So that'll load whatever we just exported. So if we run the game, we now actually have a nice area to run around in. And it has trees and rocks and flowers and different types of decorations. So we have these nice little boxes and these islands to run around in. A whole lot nicer than those 2 slabs of land that we had before. So the game's starting to really come together here. And while that was quite of a detour to do level editing, there's lots of useful concepts that you're able to learn from that, which is why I decided to cover that. But also, now that you have your own level editor made, you can add your own custom features that fit your needs better than a standard level editor might. But remember, feel free to use a normal level editor if you wish as well. Just bear in mind what the requirements are for how you load different files and stuff like that into a game like this. Things were made a lot easier for us because I designed the game around how the level editor would work, and then I had both of those in mind when I really did everything here. So you can make things a lot easier for yourself by using something of your own, but some of the pre-built stuff is pretty good as well. So we've got two good looking trees right here, and it would be really nice if they had some animated particles for leaves that would fall from them and move around. It's about time for us to get into some actually nice looking visual effects for the game, and to do this we'll be using particles, as I've mentioned. Oftentimes particles refer to just still images that'll float around, usually pretty small ones at that, but in our case what we'll be doing is using animated particles where it's playing an animation, and then once the animation is complete they disappear. So they can be used for more than just like tiny little leaves that are floating around and stuff. We can use them for just playing animations if we want in a specific location. So the first thing we'll need if we want to have leaves falling from our trees is to know where to spawn these particles from. So to do this, we need to figure out where our trees are, and then kind of create a hitbox to spawn our leaves from. And as always with Pygame, you're pretty much doing this all yourself, so we'll have to create all of the code for generating that area and figuring out which locations can spawn leaves based on the areas that we have and stuff like that. So let's get into it. So in order to get the position of our trees, I think it's best to go to the tile map, and we'll add a new function here that can be used for a lot of things. So let's call our function extract self, and it'll take the argument ID pairs, and then keep equals false. So what this function will do is it will take a list of ID pairs. So this is, if you remember, our tiles are in a like tile type format along with a variant. So it's type and variant, and those go together to uniquely identify the tile type. So that's what I'm referring to when I say ID pairs. More specifically, an ID pair is one of those two combined. Now, the ID pairs is a list of those, and we'll check if a tile is in that list. And if it is, then we can return it. So what this function will do is it will take a bunch of types of tiles that we're looking for and tell us where they are and give us information about them in our map. And then if we want, is what this keep variable is for, we can have them removed from the map. So we're not going to need that yet because we do want to leave the trees hanging around in the map, but later when we do some other stuff, we might want to get rid of things. For example, if it's an entity spawn location, we might want to remove that from the map and then create an entity. Alright, so to do this, let's create a list and call it matches, and then we can iterate over our tiles in our off-grid tiles. Let's do this one first because it's easier. And then the reason we're copying here is because we might want to delete from this list if we're not keeping. So we'll do if, and we'll make the tuple here for the ID pair, tile type, tile variant in ID pairs. That means that we've found one of the ID pairs that we're looking for. Then we'll do matches.append, and then we'll say tile.copy. So just give it the tile information. Alright, now if we're not keeping our tile, then we want to remove it from our off-grid tiles. So that's pretty much the logic for that. Just look for the match, add it to the results, remove it if we don't want to keep it. And then we gotta do the same thing for the tile map. So we go through the locations, and then we say tile equals self.tile map location, and then we do the match. So tile type, tile variant, in ID pairs, matches.append, and then just another tile.copy. And then this is a little bit different. We'll have to do matches -1 position equals matches -1 position dot copy. So what we're doing here is we're going to change this position attribute, or not attribute, it's actually a key value pair in the tile dictionary, but we're changing the position for the tile that we're referencing because we want it to be in pixels. If you remember, the tile map is in tile coordinates for the grid, not in pixels. So we want to convert that. So to do that, we'll do matches -1 position 0 multiply, and we do self.tile size typos. All right, and then we do that for the y-axis as well. So that gives us the pixel coordinates for our position. The reason why we do copy here is the same as up here. We want to have a copy of the tile. We don't want to be working with the exact same thing. And then over here we copy again because copy is just surface level. If there's a list nested inside of something, it won't actually copy that. It'll have the same reference. So this is just making sure it's clean. There's a function called deep copy that we could have used that will do basically these two things in one line, but I don't want to really get into that. So basically we're just making a clean copy of the tile data, because what would happen if we didn't is if we modified that tile data after getting the results, it would modify the actual tile in the tile map when we don't want that. And then, like I said, we're converting it to pixels. So now we can do the if not keep. We do del self.tile map location, and then we can return our matches. So now that we have our function here, we can grab this and we can go over to the game, and then we can say print self.tilemap and then we extract, and then for our ID pairs, we'll use a list with just the single pair of large decor 2. So if we wanted to get another type of decor, we could just do like this and say 1, but this will work for now. So we say large decor 2, and that will just match with this one tile, and then it'll give us all of those results. So we want keep to be true because we don't want to remove the trees, and then that will give us the results of all of our matches here. So I run that, and then we can look down here and we see type large decor variant 2, and then here's the position we're looking for. So it's got all of this useful data, and then from this we can figure out where we can spawn our leaves. So I'm going to use a bit of a hack here. There are better ways to do this that are more general, but for the purpose of this project, I'm going to keep it simple and just kind of hard code a hitbox based on the location, because we only have one type of tile that can spawn leaves. So let's do something where we have self.leaf spawners equals that. And then we can do for tree, and this will be the tiles that we were returning before. We can do self.leaf spawners.append. And then for our hitbox, we'll do a pygame.rect, because if it's a rectangle, pygame.rect has a ton of useful functionality for that type of thing. So for that, we'll say for plus the tree's position on the x-axis, and then for plus the tree's position on the y-axis, 23 and 13. So you can go look at the dimensions of the tree image if you want. This is just taking the position of the tile and just kind of looking for the area of the tree image that it makes sense to spawn leaves. So we're actually offsetting it by 4 from the top left to the right, and then same thing down from the top left, because we don't want to start right in the top left because that's technically air. So this is just the rectangle that makes sense for that image. You can go look at it and just draw it out if you wanted. So we can now print out this list, self.leaf spawners. And remember, the rect is x, y, width, height. Anyways, so we can print out our leaf spawners, and we close again, and we have our 2 rects here representing our 2 trees. Since we have our rects where the leaves can spawn now, we could theoretically easily pick locations to spawn the leaves, but now we need to be able to actually have the particles that we're spawning. So to do that, let's go ahead and make a new script. We'll call it particle.py. And this is a pretty basic one. So we'll do class particle def init, and then it needs access to the game. And we can do self.game equals game. And then we want the particle type. We want the position. We want the velocity. We'll default that to 0, 0. We want the frame that we want it to start on. All right, so we can do self.type equals ptype, self.position equals list position. And remember, that list is just making a copy. All right, so, and then we can do self.velocity equals list velocity. And then self.animation equals self.game.assets. And then we'll take particle, and we'll have to load this in a moment, and then we'll take the particle type, and then we want a copy of that animation, and then self.animation.frame equals frame. All right, so that's the setup for our particle, because the particle needs to be able to move around, and it needs to have a velocity so that we can configure how it moves. And it has the animation, and that's really all you need. Well, also the type, obviously, but that's really all you need. Now we can just do def update self.position 0 plus equals the velocity. This is just the basic stuff, so we do the y-axis too. And then we need to do self.animation.update, and we'll do kill equals false if self.animation.notFrame done kill equals true. So our update function is going to do a couple things here. We'll return kill. It needs to determine when the particle needs to disappear, so that's what this kill variable is for. As soon as this update function returns true, that means that this particle needs to be removed. So we return true once the animation has finished playing, which was what we added before. This is a nice little utility attribute that we have for that. And we also have to update the animation in our update function and move the particle. So there's a couple things. If we wanted, we could add more behavior here as well, but it should be enough for now. And it's really important to remember the type of thing you're pulling from the assets here. Like for example, if this were a list of images, you'd probably have a problem, but we will be adding this in as an animation like we did for the player stuff. All right, so now we need one more function for a particle. We'll call it the render function. It needs a destination surface and an offset, and we'll take 0, 0, and we'll take image equals self.animation.image, and we just take that, and then we go surf.blit. We render our image onto the destination surf at the position we have, minus offset 0. And then this is something actually we're doing. I like to center my particles based on the center of the image instead of the top left. It just makes the behavior easier to work with and more aesthetically pleasing. So let's do minus image.getWidth, and then we divide that by 2. Now we can do self.position 1 and just do the whole thing for the y-axis. All right, so now we have the rendering coordinates for the x and the y-axis, and that should be sufficient for our rendering function. All right, so now we need to actually add our particle assets. And for that, we can go back to our assets thing right here and say particle/leaf. And that's the particle type we'll be using. If you remember, we said particle / and then the type, and we'll be using leaf here. So we'll create an animation of load images, and then we'll do entities, particle leaf, I believe. Let's check that. So we go data, images, we have particles. So this will be particles/leaf. So we have 2 types in here. We'll be using just leaf for now. In here there's 17 images. If you look in here, there's like different leaf images. Normally in my games I would have the ability to recolor these, but right now we'll just be playing the animation and that's it. So it'll play through those leaf frames, which will load here and then attach to the particle. And then we'll have our particle as we wanted. So now that we have the particle object, I think it's time that we add our particle collection. So we can say self.particles equals that list. And if you remember, we had that return kill thing in the particle code. So in our loop here, we need to keep track of that and see if we need to remove it. So we'll do for particle in particles.copy, and again we're doing the copy thing. We're doing the copy thing because we will be removing during iteration. So kill equals particle.update. So we're calling the particle.update, and then we're just checking if we need to kill it. So we can do if kill self.particles.remove particle, and that will handle that. We also want to render a particle, so particle.render, and then let's do self.display offset equals render scroll. All right, so we now have our collection of particles, and it should remove them as soon as the animation is played through. So now we just have to spawn our particles. So for that, let's look through our leaf spawners. So for rect in self.leaf spawners, if random.random, and this is going to be just a mess of numbers here, 49999 is less than rect.width by rect.height. I'm gonna go import random here because we don't have that. Import random, and then we also want our particle. So from scripts.particle import particle. So if you're unaware, random.random is just a random number between 0 and 1. It's a floating point number, so it could be like 0.25 or something. And then we're just multiplying it by this and then checking it to see if it's less than the pixel area of our rectangle. So this is a way where you could have the spawn rate for leaves be proportional to the amount of pixels that that hitbox covers, so that if you have like a bigger tree, it will spawn more leaves. And then this number right here is just to control the rate at which they spawn, because if you do this, it will spawn 100% of the time, like every single frame. So by multiplying it by that big number, it'll make it so it's not every frame. Anyways, if we've decided that this random odd chance has passed, then we can say our spawn position equals rect.x plus random.random by rect.width, and rect.y plus random.random by rect.height. And this is really one of the more interesting problems, I think, in this tutorial. It's just the spawning leaves problem. So there's a lot of random techniques you can pick up from here and different ways of solving problems. Of course, this doesn't generalize to that many different things. So there's just little things you could start thinking about here and there about how you would approach problems. Anyways, so we're taking the x of our rect and then adding the width multiplied by a random number from 0 to 1 times that. So that will give us any number that's within the bounds of the rect, because 1 times the width plus the left position will be the right position, and then 0 is the left. So anything in between is somewhere inside. And it's linearly distributed. So we can do self.particles.pend, and this is where we spawn our particles. We do particle, and we do self to pass along the game. We want the leaf particle, and then we'll give it our position. So that will be position, that which we just calculated. We'll do for velocity. All the leaves will have the same velocity. You could randomize this if you wanted, if you want variance, but I'm going to leave it at -1.3 or -0.1 and 0.3. That will mean it's going slightly to the left, but mostly down, but also very slowly. For the frame to start on, we'll say random.randint. If you don't know, this is a random number within, I think it's inclusive of the two numbers we give it. So we'll give it 0 to 20. So that will select just a random frame for it to start on. So that way we don't always start with the biggest leaves. Anyways, so that will spawn our particles, and then this will manage our particles. So if we did everything right, it should work now. Aha, so you can see there are leaves falling now. They're a little bit rare, but as a visual effect they should be. Oh, I do see we have a problem though. So first of all, our leaves are kind of decaying into the 1 pixel dot very quickly, and then second of all, the animation is looping and they're not disappearing. So to deal with that, we need to go over to our animation here, and if you remember, we have a couple of options here for animation. So first of all, we need to make them decay slower, so we'll do image duration equals 20. So 20 frames for each frame of the animation. It's confusing terminology, but whatever. And then we want to disable the looping, so we'll do loop equals false. So we run that again, and we have leaves that are decaying much slower. It looks much nicer, and we're looking at this one on the bottom left, and the one, it just disappeared. So our leaves are disappearing, that's good. They're decaying slowly, that's good. So looks very nice, but there's one more effect I want to go ahead and add over here. So if we go over here into the particle management, we can add some extra rules for our particle. We already have our update function, but we could do something else if we wanted. So we can say if particle.type is leaf, then we can say particle.position 0 plus equals math.sign particle.animation.frame by 0.035 by 0.3. All right, so we do need math. That's the math library that comes with Python. And that's just giving the sine function to us. So if you don't know what the sine function does, just think of a sine wave. So you know the curvy wave that goes up and down. You can just look up a picture if you want. And we're passing in just the animation's frame, so like the progress that we have in our animation. So if you know what the sine function does, it will give you a number between -1 and 1, and it will smoothly go between the two. If you were to plot it out, it would be a kind of a bit of a smooth curve. So it has a more natural pattern than just moving to the right at 1 pixel per second and moving to the left at 1 pixel per second. It will slow down as it gets to the edges. So what we're doing here is we're applying this random number that could be -1 or 1. Well, we're multiplying it by 0.3 to decrease the force of it. But we're applying that to the position. And because it's a number between -1 and 1, it actually sums up to 0 over time. So what this is doing in the short term is it's making the particle move back and forth, like right and left over time in just a smooth pattern. So this last part here, the 0.035 thing, is just to make sure that you don't go through a whole kind of loop of the sine function too fast. It's just to slow down how fast it goes left and right. And if you aren't aware, there's no limit to how big of a number you can put into the sine function. It will always give you a number between -1 and 1, so we don't have to worry about how far long that is. Anyways, if we were to run it again, we could see that our particles will move right and left now. So if you watch this particle closely, it'll like sway back and forth, right and left. So this is a technique I use for a lot of things. If you want natural animations for a variety of things, the sine wave is a really good way to get a natural look. You can layer it with some other stuff because technically it's a little bit too mathematically perfect, but it's more natural than the robotic multiplying, well, adding -1 or 1 technique. This is a lot smoother, but that's just a useful thing to keep in your toolbox. I recommend getting very comfortable with this function. If you just play around with it, you can get an idea of what it returns for different values, and you can get used to using it for things. Of course, it has tons of other applications in math as well, if you've taken trigonometry, but I won't get into that too much. So if we go back over here to the input code and take a look at our up arrow key, we'll see that we left it as you press up, the velocity of the player is just set to a negative number. So the effect of that is that if we run the game, you can just press up as much as you want and jump as much as you want. So normally in a game you wouldn't want this, maybe if you're playing Kirby, but for the most part, you don't want to be able to just jump to infinity. So what we'll be doing is we'll be adding some restrictions on jumping, and then also while we're at it, we'll add the wall slide effect so you can slide down a wall and then jump off of it. Alright, so let's get started with the easier part, which is the jumping aspect. So what I'm going to do is I'm going to go right here in this key up part and just swap this velocity change with player.jump, and then we'll fill out this jump function so that it handles the jump when the button's pressed. So we can just go over to our player here and we can add a new function. We'll go def jump self. We don't need any arguments. Alright, pass for now, and we need a couple of things added to the player to keep track of jumping. So we need self.jumps equals 1. The way I'll be doing this is that the player will have 1 jump, and a wall jump will consume that 1 jump, but if you run out of jumps and you're on a wall, you can still wall jump. So you can jump and then jump off of a wall, but if you fall and jump off of a wall, you can't jump again. That's just my preference for how this is implemented here. You could come up with all sorts of rules for how you want the jumping limits to work. If you want, you could just increase the maximum number of jumps to like 3 or something, so you can jump in the air 3 times. You can do all sorts of fun stuff. And I recommend you do play around with that if you want to get a good understanding of how this works. Anyways, so let's go over to this jump function. We'll need to keep track of this jumps attribute to determine whether or not jumps can be made. So let's do if self.jumps minus equals 1, self.velocity 1 equals -3, and self.error time equals 5. So we're doing a couple things here. First of all, we're reducing the jump count. So if our jump starts at 1 and we jump and reduce the number of jumps by 1, it'll go down to 0. And this statement will fail the next time you try to jump, because if jumps is 0, that evaluates to false, so you don't have any jumps left and you can't jump. Anyways, but it'll also modify the velocity, same as before, -3. And then while we're at it, we'll set the air time to 5. That's just to force it to automatically transition to the jump animation, because once the air time is above 4, it'll transition. Otherwise, you would have to wait like 4 frames, so you get a little bit of the running or idle animation before it actually switches to jump in the air, unless you have this line. Anyways, the next part is to actually restore your jumps after you've hit the ground, which is usually what you want to do, but I mean, you could make a mechanic where you have to maybe collect something in order to restore your jumps, and your jumps are a limited resource. But in our case, and with most games, you'll want to make it that when you touch the ground, you restore your jumps. So we'll do right here, when you collide with the floor, going downwards, you can do self.jumps equals 1. And if you wanted to have 2 jumps, you could just swap these 2 numbers for 2, and that would make it so that you always have 2 jumps after each touch with the ground. Alright, so that's the basics of keeping track of your jumps. If we go over to the game, and if I press up twice, you'll see that I can only jump once. If I press the key loud enough, you might be able to hear it. But yeah, well, now if we go back over to here, we can go ahead and start working on the wall slide. So to do this, we'll add a attribute for, wall slide, and set it to false. Now this is where things get a little bit messy, because not only do we have to deal with the actual movement mechanics of dealing with a wall slide and the jumping resource management of a wall slide, but we also have to deal with the animation aspect of the wall slide. So there's a lot of components going on here. So this is going to be a bit more complicated than just the number of jumps that you have. So let's start by saying every single frame will say the self.wall slide equals false. And the purpose of this is so that this variable will act as a single frame switch, or like, I don't know, a button where it fires off an event once you press it. That's sort of how this is set up. So once you set it to true during the frame, it'll be true for the rest of that frame. But then when it comes back to here on the next update, it'll be false. So this is a useful trick if you want to have something that that's sort of an event that fires off once. So now we'll write the part where we'll determine if wall slide should be set to true. So we'll do if self.collisions right, or self.collisions left, and self.airtime is greater than 4, self.wall slide equals true. So what we're saying here is if we hit the wall on either side and we're in the air, and this is the threshold that we're using to determine if we should be showing the jump animation, but if we're in the air and we're touching a wall, then we should be sliding on that wall. So since we're using this technique where we basically set it to true and then switch it back to false every single frame, then we're basically saying only for the frames where this holds true will this be true. What you could also do is you could throw an else right here and say self.wall slide equals false, but this works as well. Now we can do self.velocity 1 equals the minimum of self.velocity 1 and 0.5. So what we're doing here is we're capping the downward velocity at 0.5. Remember, the min function takes the lower of the 2 values, so if this number is lower than 0.5, it'll take it. If it's greater, it'll take 0.5, so that's just a 0.5 cap effectively. Now let's do if self.collisions right. So we need to break apart this statement here, because while this is the statement that determines if you're sliding on a wall, we need to break it down to determine which direction so that you can show the correct animation. Anyways, so we can just check if it's right, and if we know if it's not right, then it must be left, because that's how an OR statement works. Anyways, we can do self.flip equals false, and this is important for keeping our animation accurate, and then we can do else self.flip equals true. And remember, the base images for the player are facing right, which means that we want flip equals false when we're facing right, and then flip equals true for facing left. Anyways, now we want to do self.setAction wall slide. And now the purpose of this wall slide variable, because if you think about it, we have most of the code here for handling the effects of the wall slide. So we're updating the animation, we're handling the flip, we're restricting the velocity. So this variable right here is just for a couple of things. It's used to prevent the animation set right here from being overridden by these ones. So we can go if not self.wallSlide. Because if you're sliding on the wall, you don't want it to switch to whatever the normal animation would be. And because of this restriction right here, it would technically be either you're in the jumping animation or wall slide, because this is the first case. But we can just break it all out and say, if we're wall sliding, don't do any of the other animations. We want to show the wall slide animation, which is whatever it was previously set to. And then once that becomes false, which will be as soon as you're no longer touching the wall, then it'll let it switch to the other animations again, which should probably be jump. All right, so now that we have the animation side of things handled and the slowly sliding down the wall side of things handled, we can go ahead and work on the jumping part of the wall slide. So we want to make it so you can jump off the wall. So we'll do this by doing if self.wallSlide, and that's why we need this variable over here as well as an attribute. We'll do pass, and then this will become elif self.jumps, because we want to prioritize the wall slide first over the normal jumps. And then we'll say if self.flip and self.last movement 0 is less than 0. So what we're looking for is flip equals true, which means you're facing left, and your movement that you attempted to do is going to the left. Then self.velocity 0 equals 3.5. So that's going to add a velocity, almost like an impulse, pushing you to the right, which will push you away from the wall. And that's the jumping away from the wall part. So now the other part is the vertical component of the jump. So self.velocity 1 equals negative 2.5, and that will force you up. Same as the negative 3 here, except in a wall jump, you probably don't want to jump as high as a normal jump because you're also going to the side. Anyways, we'll do self.airTime equals 5 just to get the animation updated. And we can do self.jumps equals max 0, self.jumps minus 1. So we want the jump to be consumed if you have one remaining by the wall jump. But like I said before, you should still be able to wall jump if you don't have any jumps left, which is why there's no check for the number of jumps you have before it gets to this statement. And then something you have to be careful about is because we're doing if self.jumps and not if self.jumps is greater than 0, then we have to make sure that the number of jumps can't go below 0. And technically, if you can wall jump when you have 0 jumps left, and you subtract 1 jump from there, it would go to negative 1. So that's a bit of a tricky bug that you don't want to deal with. So we max these two values so that the minimum value is 0. And that will effectively just only reduce your jump if you have them left. So now we need to deal with the other direction. So elif not self.flip and self.last movement 0 is greater than 0. And then we just kind of copy all of this, and there's better ways to do this, but this is good enough for now. And you just swap that direction on the x-axis, and that covers everything. All right, so that is our jump code. The last thing I'm going to do, and this is just for convenience if you want to add something on top of this, is I'll add a return true if the jump actually occurs, so that you could hook off some events from this jump function. So you could go over here and say if self.player.jump. So if the jump actually went through, then you could do something else. So normally in my games, I might add in a special animation for that, but I think I'll leave this for now, and you can go add that yourself if you want. Anyways, let's go back over to our update function. If you notice, we modify our velocity here in 2 dimensions. So we have our code for the gravity that runs up here in the entity parent class for the player. It will force the player to fall downwards and then cap it at 5. So that will make it so that if you're jumping up, it'll pull you down, and you've seen that already. But if you notice, we don't actually have any code for normalizing the x-axis. So if you were to jump off of a wall and have your velocity set right here to like negative 3.5, it would stay at that number and you would just constantly be moving left. And we don't want that. So to deal with that, we'll need to add some normalization to the horizontal velocity. And that just means that we're going to be making it move towards 0 so that it eventually gets to 0 and you stop being forced in that direction. Similar to how gravity will pull you down. You can think of this like air resistance. That's sort of what it's like, except technically we're exaggerating it for the sake of gameplay. So we'll do if self.velocity 0 is greater than 0, self.velocity 0 equals the minimum of self.velocity 0 minus 0.1 and 0. So what we're saying, actually said this should be max. So what we're saying here is that we want to subtract 0.1 from the velocity every frame if it's greater than 0, and then stop it from going below 0. So you just want to stop at 0. And then that will make it so that it brings it towards 0 if it's greater than 0. So we have to deal with the other side now, which is if the velocity is negative. So all that is you just take this, you copy it down here, you switch this to a plus, and you switch this to a min. So that will make it so it'll take the two values and say which one is lower. So as soon as this number crosses 0 into the positive territory from these increases, it will get capped at 0. So that it can't actually go over. So this will just pull the number linearly towards 0, and that will give us the effect we're looking for. So if we go ahead and run our game now, we can run around, we can jump, and if we go over to a wall, we can slide down it slowly out, and we've got a crash here. So it appears that I have not added the last movement attribute. So that's just a simple concept. The idea is that you take whatever the previous movement was and do something based on that. So to add the last movement, we can just go over to our physics entity, and we can say self.lastMovement equals 0, 0, because remember this is what we're inheriting from as the player, so it'll have access to everything in here. And then we can go over here and then copy this down into this update function, which takes the movement, and then we can just drop it right here and say that the last movement equals the movement. And now we should have this last movement attribute to work off of for our jump mechanic. And something important to note is that this movement variable is keeping track of movement, which is the input to the update, not the actual movement that was executed upon. So if, for example, you're running into a wall, it'll keep track of the intent to move towards that wall and not just put it as like 0 on the x-axis because you hit the wall. And that helps us keep track of the fact that we're actually trying to push up against that wall. Now if we run over to our game and we run it and we jump into a wall and we try to wall jump, it works properly. So it bounces us away. Jump up, bounce off the wall. Works as intended. So you can jump once and then you can jump off a wall, or if I go up to here and then slide down the wall and jump, that's our only jump. So that's how we intended for it to work, and it's working as intended. So these two things will cover pretty much all that we were looking for in terms of movement, at least in the jumping sliding space. There's one more thing that we have left for movement. Let's go ahead and add the dashing mechanic to the game. This is not only a movement ability, but it's also how you do the combat in this game. The enemies will shoot at you while you as the player have to beat them by dashing through them. So it serves multiple purposes. For the effect, we'll have to move the player suddenly, and we'll also have to have some nice visual effect to go along with it. So what I'll use is a burst of particles. So let's start by loading in the particles that we want to use. Let's grab the particle leaf, let's copy that, and we'll say particle. And then for the image duration, we'll say 6 instead of 20, because this particle should not last nearly as long as the leaf. So if you look in our particles list, we do have this particle, which is just 4 images, and they're just circles. So I'm going to go ahead and close that though. So now that we have our particle animation loaded, we'll want to add the key binding for actually using the dash. So let's go down over to our keys here, and we'll do if event.key is pygame.kx, and that will be your key that we use to dash. We'll do player.dash or self.player.dash, and similar to the jump thing, that's something that we'll have to go ahead and add here. So let's go over to the player, and we'll go under the jump code, and we'll say def dash self. And this will be a pretty short function. We'll do if not self.dashing, which is what something else we'll need. Let's go up here and add it. Self.dashing equals 0. If not self.dashing, so self.dashing is 0, we can do if self.flip. So that's if you're facing left, self.dashing equals -60. And then we'll do else equals 60, and so that's if you're going right. So this dashing variable will keep track of how much we want to dash and in which direction. So 60 is how long we're going to dash for, and then this negative is for the direction. So you know how there's the idea that velocity is not only a speed, but also a direction? That's what we're using here. We're using that directional component to say which way we want to dash. So that's just a nice convenience that we can use. All right. So now we have to actually do something with this dashing variable. So we need to do something that says basically if it's not 0, then we need to apply the dashing effect. So for that, we can go up here into our update function. We can just go right here, I guess. It could go in a lot of different places here. So self.dashing is greater than 0. We'll do self.dashing equals max 0, self.dashing -1. And this should look familiar. That's the same thing we're doing right here. So this is just bringing it towards 0. So we need to manage our dashing value so that it just goes down towards 0 and that the effect can eventually end. So the other side of that's going to be the +1 with min. And then now we can do some other stuff. So what we'll say here is if the absolute of self.dashing is greater than 50, self.velocity 0 equals the absolute of self.dashing divided by self.dashing by 8. So what we're doing here is we're saying if we're in the first 10 frames of the dash, then we take this part, which is actually just, it's going to be 1 or -1, depending on which direction it is. So if you just divide the absolute by its own value, you'll get the direction of the scalar. So in our case, if it's a positive number, you'll get 1, -1 will be received when you have a negative number. And then that will just be multiplied by 8. So we're just modifying it based on the direction here. All right, so now we can do if self.dashing is 51, self.velocity 0 times equals 0.1. So what we're doing here is that at the end of these first 10 frames of our dash, we're going to severely cut down on our velocity. And this remaining velocity will be quickly just diminished by this code right here, which will reduce the velocity. So the purpose of this is to just kind of cause a sudden stop to the dash. If you saw it from earlier, you dash suddenly, and then you stop, but there's a little bit of velocity left over. And that's how we can achieve that. So you might be wondering, okay, that's the first 10 frames, what are the last 54? So this is also not only working as our code for applying the dash, but it's also working as our cooldown code. So when this number is less than 50, but still greater than 0, if you remember, in order to dash, dashing has to go down to 0. So this is actually working as a cooldown so that you can't dash as much as you want. So remember, this will eventually bring it to 0, but this is going to be 5/6 of a second before it goes completely to 0. So you have that little bit of time of a cooldown where you can't dash again. So you can't just dash as much as you want and basically fly around. So that's how we manage that. So I can run the game now and show you what this looks like. So I can run around, and if I press X, I can dash around, which is cool. Now it's time to add some visual effects to it. This just handles the movement component. And let's go over to entities here. Let's close this. If you remember, our physics entity up here has its own render function right here. So I want to make it so that when we dash, we turn invisible. And we just turn into kind of a stream of particles. So what we'll do is we'll take that render function and override it right here. We'll say def render, well, not override it. We're going to build on top of it. We'll take our surf and offset, and we'll do if the absolute of self.dashing is less than or equal to 50. So remember, this is accounting for both directions. You're saying if we're not in the first 10 frames of a dash, basically if the dash is on cooldown, or if it's just completely off of cooldown and we're not doing it at all, then we can go ahead and do super. So this is accessing the parent class and .render, and we'll pass in the surf and offset equals offset. So what we're doing here is we're kind of gating the rendering function of this physics entity, which we would normally be using, behind just an extra layer in the player that checks to see if we're dashing or not. And if we are dashing, then we don't want to actually render it, so it'll skip this, and it just won't show the player. All right, so that will make the player invisible. So the next part is the particles that I talked about earlier on. So for that, there's two sets of particles I want to do. So first, I want a burst of particles when you first start and when you end your dash. And then I want a stream of particles while you're dashing. So to do that, we can go ahead into our update function here. And right here, we can just add the code for particles. We can do self.game.particles.append. And this is where we can add a particle if we want. So for this, we need to actually have particles to work with. So let's go over up to the top and we'll say from scripts.particle import particle. And while we're at it, I'm also going to grab the math module because we're going to be doing some trigonometry here. All right, so let's go back now that we have our imports done. We can work on spawning our particles for this. So like I said, we want a stream of particles just as the player's dashing. So for this, we can do particle, and then we'll pass in self.game, and we'll say it's a type particle, and we want to spawn it from self.rect. And if we go up here, that's this function here that generates the rect for the player. And we want to take the center of the rect, so this will just be a tuple, just the x and y coordinates of the center of the player. And that will be our spawn location. And then we also need actually, let's split this up here. So we'll say velocity equals, or I'll say p velocity just to distinguish it. So p velocity equals the math.cosine of an angle times a speed. And then we want the math.sine of an angle times the speed. And for this, we'll go ahead and say angle equals random.random by math.pi by 2. And our speed will be random.random by 0.5 plus 0.5. And then now we can take this p velocity here and say velocity equals p velocity. And then we'll also want frame equals random.random 0 to 7. All right, so what we're doing here is we're taking the cosine of a random angle. So well, first of all, let me import random real quick. So let's go import random. We're taking a random angle. This will be random.random times math.pi times 2, if you know how radians work. This is just the full circle of angles in radians. Like a full circle is math.pi times 2. And this random.random is just selecting a random angle within that full circle. If, for example, you were to just take times 10 or something, you would get it unevenly distributed because there's certain sections of the circle that show up more in the numbers 0 to 10 in radians than others. That's why you want the exact amount of math.pi times 2. Technically, if you were to just put in a really big number, it would be almost the same, but this is the technically correct way to do it. Anyways. So this will just get a random angle in a, like, think of a circle, just pointing in a random direction. And then we'll take a random speed, and this will be just a random number between 0.5 and 1. Because remember, random.random, 0 to 1. So you take that, multiply it by 0.5, and add 0.5, and you get 0.5 to 1. All right, so for p velocity, we're taking the cosine of the angle times the speed, and the sine of the angle times the speed. The cosines for the x-axis and the sines for the y-axis. This is a little bit of trigonometry. So what this is doing is it's generating a velocity based on the angle. And this is how you move something in a direction, in any case, pretty much. At least in 2D. In 3D, it's a bit more complicated. But in 2D, you take the cosine of the angle you want to move, and you multiply it by the amount you want to move for the x-axis. And then for the y-axis, it's the sine. And if you've taken any trigonometry, you would know about the whole opposite and adjacent sides of a triangle and their associations with the functions of cosine and sine. So there's actually math behind here if you've looked into trigonometry for how this all works, but it can get a lot more complicated than it needs to be. So you can actually just pretty much memorize this one statement right here, or this one formula, and this will get you through most of the trigonometry you need for games, in fact. I have a video about this topic as well if you want to get into it a bit, but this will cover most of what you need. The other half of what you need is using arctangent 2 to turn an x and y coordinate into an angle. So it's just the conversions between angles and Cartesian coordinates that represent vectors. Anyways, so you might be wondering, why would I go through all the effort to do all this trigonometry to generate a random direction to create our particle velocity with, instead of just picking an actually random velocity? So I've seen this in a lot of games, and I think I actually used to do this myself, where you just pick a random number for the x and y coordinates, and the problem with that is the way it's distributed and scaled. So for scaling, you run into the problem where if you're going diagonal, let's say you pick the random number from -1 to 1 for both of the axes. Let's say you go into the 1 direction, so +1x, +1y, and that's your velocity. So that's moving twice as fast, if you think about it, because it's going diagonal, as if you were to go just straight right from getting 1 and 0 as your velocity. And the effect that that creates visually is that if you spawn a ton of particles like that, it will create a weird explosion in the shape of a square instead of a circle. So that's the problem with the scaling. Technically, you could normalize those numbers using square roots and stuff in order to make it so that the scaling's correct and it is the shape of a circle, but then you still have problems with the way that it's distributed, like the way that particles get randomly distributed. So to do it correctly, if you want to spread something out in a circle, the best way to do it is to pick a random angle in polar coordinates and then convert that into Cartesian vectors for velocity. So that's a bit of math stuff, and it's really important to, at least when you get into more advanced topics in game development, if you want to make your stuff look natural and look good, a lot of times you do want to get into the math to make things look a little bit better than what the primitive solution might be. And that's just another random tip I'm dropping for you here. And actually, I've just noticed a rather large mistake I've made here. And this is just a side effect of how I'm making these tutorials. This whole section here is actually for the burst, and not for the stream. So if you remember, I said I want a stream of particles and a burst of particles. So technically, this part right here is the clause that's for the stream. So it's just anytime that you're in the middle of the actual movement of a dash that we would run this code. So for that, we'll actually want to take this, and we'll want to create another one of it modified for the stream. But since I just went and did all the math and explained that for the circle, I'm going to add the extra case for the circle here. So we'll do, so if abs self.dashing in 6050 for I in range 20, and this is what I was talking about when you do a bunch of particles. We'll say if our dashing is in 6050, this means if we're at the start or the end of our dash, we'll do this 20 times. We'll create 20 particles in random directions with random speeds, and that will be our burst. All right, so now we can grab this and go ahead and fix the stream stuff over here. So that's going to be, we just drop it right here and boop. And same thing, except with some minor differences. So p velocity will have to be different this time. We'll do p velocity equals, and we'll say the absolute of player.dashing, or the absolute of self.dashing, divided by self.dashing by random.random by 3. So if you remember, an absolute divided by itself is just giving you the direction, 1 or -1, and then we just take the random number times 3, so it'll be just random number from 0 to 3 in the direction that we're dashing. So that way the stream of particles moves along with the movement a bit, instead of just staying stationary. And then we don't want any movement on the y-axis, because you dash on the x-axis, so we don't want that to be moving around. Anyways, so we'll keep everything else the same, and that should cover that other type of particles. So we have the stream particles, and we have our dashing particles right, or sorry, our burst of particles right here. So now if we go ahead and run the game again, we can run around. If we press X, oh, whoops, we're not supposed to have leaf. So that's a fun mistake you can make. We're supposed to swap this with particle. Wait a second, what's this game? That one's supposed to be leaf. This one's particle. Wait, why is that one? Aha! So if we go over to here, when I copied this at the beginning, I left that as loading from the leaf. So we want that to be actually particle, not leaf, and that should fix our dash. So if we go back over here, and you can run around and you dash, and you get your start, you get your end burst and your line, but you don't get the start one, which is not intended. So to fix that, there's an important lesson to learn here, and that is that the order for some of these things does actually matter. So if you think about it right here, we're setting it to 60 in our dash, and then say after a dash we get to our update function at some point, so it goes through this update function, and we have our code here that adjusts our dash basically timer thing. So it'll go from 60 to 59 or negative 60 to negative 59. And by the time it gets down to here, but to this code, if it were set to 60, it would have been pulled away already, so it'd be at 59. So this is one of those situations where you can either take this code and move it up, like up here, or you can leave it as is and then change these numbers. Because technically this 50 for the end of the dash is also wrong. It would be 49 if it's right here. So I'm going to do the easy thing and just copy this and move it over here. I think it reads nicer to have the number 1650 as opposed to having to figure out why it's -1 in the future for some reason. So we can now dash, and we get both ends of our dash, which is great, and we have our line between just as we wanted it. And that should cover pretty much all of the movement stuff that we'll be doing, at least for the player. At this point, we have most of the base of the game done in terms of the movement and the basic implementations of the standard things you would find in a game, like animations, particles, physics, etc. But it's time to turn our game into an actual game. And to do that, I think it would be fitting to have some enemies to fight. And the objective would be to defeat all the enemies and then move on to the next level without getting shot. Alright. So to start adding enemies, we'll do something very similar to the leaf spawners thing we have here. And we'll extract a different type of tile and use that to spawn things. So I'll demonstrate how you can add your own, I guess, spawners for the player and enemies. But then I'll quickly switch to using the pre-made levels I have, because I don't want to sit here for an hour making levels. Alright, so first of all, let's extract some spawners, and then I'll go ahead and add them to the level data itself. So let's do for spawner in, just like the tile, well, just like the leaf spawners, we'll do self.tilemap.extract, and then we'll do spawners 0 and spawners 1. Those will be the tile IDs we're looking for. And this time we don't want to use the whole keep thing, because keep is used to, well, keep the tile in the tile map. If we don't set keep to true, it will actually extract and remove the things that we're asking for. So we actually don't want these spawners to show up in our tile map. We want to just get the location so that we can put stuff there. And that way it works as a spawner as intended. So we'll do if spawner variant is 0. This will be the player spawner. We'll do self.player.position equals spawner position. And then else, we'll just print out the position. Alright, and I'll say enemy. And then we can fill that in later. But for now, let's actually update our map here. So to do this, we can go back over to our level editor. Just go ahead and run this. And let's see if we actually have it in here. No, we don't. So we do need to load in the spawners. So if you look right here, we have decor, grass, large decor, and stone. If you go over to tiles, we have this extra one called spawners, which have a picture of the player and a picture of an enemy. So what we'll do here is we'll say spawners and then load images, and then we'll do tiles/spawners, and that will give us what we need for that. Now if we run this again, we now have the player spawner. We can put it off grid, and we can drop one down there, and then we can go ahead and add a couple enemies as well. And I'll press O to save, and let's go ahead and run the game. Alright, so now spawned us in the right location, and if you look down here, it gives us the 2 locations of the enemies that we added. So with that, we can now actually spawn the enemies. To do that, we obviously need some enemies to spawn. So similar to the player, we're going to go over to entities, and we're going to add a new entity. Alright, so let's add class enemy. And this will inherit from physics entity, same way the player does. And then we'll do definite game, position, size, all that good stuff. Alright, and then we can do super dot init game enemy position size. Alright, so with the enemy, we'll use the custom enemy animations, which are over here in entities, enemy, and it has an idle animation and a run animation. So let's go ahead and load those in. So we can just do enemy/idle animation, load images, entities/enemy/idle, and then we'll say image duration equals 6, similar to the player's idle animation, and then we'll also have an enemy run animation. We'll just swap these 2 idles for run, and then we'll set the duration to 4, similar to the player. Alright, so now we can go back over here, and here's the idea for the enemies. They should be able to walk around, but then not walk off of the edge of an island. They should be able to turn around, and we just have a basic AI for just walking around kind of casually. And then it should also shoot at the player if that's appropriate. So that would be based on the location of the player, so whether or not the shot would line up. So the enemies will only be able to shoot horizontally. So it'll have to see if the player's within range and at the right level on the y-axis. But for the actual movement itself, it's going to be kind of like a Koopa. So if you've seen Koopas, they just walk back and forth, and then if they walk up to an edge, they'll turn around. So part of that pattern for AI is to keep track of whether or not it should be moving. So normally there's like a attribute or something that will keep track of whether or not it is moving and for how much longer it should be moving, and then you just randomly decide when it should be moving. Or you can have like a global timer where it's like if it's like you mod it by however many frames, and then you say if it's in this section of that modulo, then you're walking, so it could be a consistent pattern. But I would like the more random pattern, so we'll just use randomness in a timer. So that timer will be self.walking. And this will be similar to dashing in the sense that it's a timer, but this time we won't include direction because we'll derive it from the flip of the entity. Alright, so the first step here is we'll do an def update self tile map movement equals 0, 0. And if you look at the player, these are the same arguments we have here. So if we want to do the physics movement and stuff, we'll need this super.update thing. So we can drop that in right here. So this is just calling the parent update function from physics entity, which handles the physics, as you know. We pass in the tile map and the movement we want to do. So we can modify the movement here to be whatever we want. So before we actually move, we should do some calculations to determine what we should be doing this frame. So we'll do if self.walking. We'll do a pass for now, and then we'll have an elif random.random is less than 0.01 self.walking equals random.randint 30 to 120. So what we're doing here is we're saying if we're walking, we have this space to do whatever we want, which we'll fill in later. And then otherwise, if we're not walking, basically, We can check if this random number is less than 0.01. Since random.random is random number between 0 and 1, that means that this has a 1 in 100 chance of occurring, which, since we're running at 60 FPS, that's 1 in every 1.67 seconds if we're not walking. So that's how long the average delay is before walking. And then our walking will be set to this random number, which is the number of frames we will continue to walk for. So that's a random number between half a second to 2 seconds. All right, so from here, for the walking, we'll need to do a couple things. We'll start by making it so that it can just walk in one direction and that's it. We'll do movement equals movement 0 minus 0.5 if self.flip else 0.5 movement. So what we're doing here is we're saying that we want to subtract 0.5 if we're flipped, that's facing left, or otherwise we want to add 0.5. So if movement's just given as 0, because that's what the keyword is, then it'll be negative 0.5 or 0.5 depending on what the flip is and if we're walking. And then it'll just keep whatever the y-axis movement was. Now, the next step here is to take the walking thing and reduce the timer. So walking equals max 0, self.walking, you've seen this before, -1. So that'll just cut it down to 0 over time if we're walking. So let's go ahead and actually spawn our enemies. To do that, we'll have to go ahead and import our enemies, and then we'll need to go over to our spawn code right here, and we'll say we want an enemy with the game. We want to give it the spawner's position to place it, and then we'll say it's 8 by 15. You can look at the image yourself and go compute what the dimension should be, but I'm just writing it down here since it's not actually teaching you much. All right, so we also want a self.enemies to add this to. So we'll do self.enemies.append, and we'll add in the enemy. So now with our list of enemies, we need to render them. So I would like them to be right after the tile map, but also still before the player. So we'll do for enemy in self.enemies.copy, because we're going to be removing from that later. We'll do enemy.update. This is the same update code from before. And then we'll give it a default movement of 0, 0. And then we want to do enemy.render, and we'll give it self.display, and the offset will be the render scroll. All right, if we run this, you can see that they're up there and they're walking around. It should walk off the edge because we have, well, yep, they can walk off the edge, and that's what we want to fix. All right, so to do that, let's go ahead and go back to our enemies here. And we want to say, if there's a solid tile in front of where you're walking to and below, meaning that you're about to walk onto a floor, you can keep walking. Otherwise, you need to turn around. So to do that, we need to add some case right here under if self.walking. But we also need some way to determine if there's a solid tile right in front of it. So to do that, we'll go ahead and head back to our tile map, and we'll add, I think, what's going to be the last function for this video. So let's add a def solid check. So this is just checking for a solid tile, and we'll give it a position. It will compute the tile location as the string of the int of the position 0. We've been through this before. Self.tile size plus semicolon plus string int position 1 self.tile size, and that will give us the tile location. If you remember, this is just converting our pixels into the coordinates of the grid system, because we were looking up tiles that you can collide with, which have to be on the grid. All right, so we can do if tile location in self.tilemap, if self.tilemap tile location, type in physics tiles, return self.tilemap tile location. All right. So we're looking to see if this location exists, and then if this is a physics tile, which we have defined up here. So there's two types of physics tiles. We have grass and stone. Those are the things you can actually collide with. So we want to see if it exists, and if it's a physics tile, then we return that tile data. In our case, we're not going to actually use the tile data for anything. We're just going to check if it exists, because if it doesn't hit this line, then it'll return none. So we can just put this behind an if statement. Since none evaluates to false, as a Boolean, this will be either true or false depending on whether or not something was found. So we can go ahead and use this function now. We can head back over to our entities. And right here we can add that special case I was talking about. So we'll have if tile map, remember we have it passed in right here, which is convenient, dot solid check, and we'll do self.rect.center x. And this is where the math gets a little bit funky. We're using some magic numbers and stuff. It's based on the movement. So remember we have this -5 positive, well, -0.5 positive 0.5 depending on flip. We're doing the same thing here, except it's more extreme. We're looking 7 pixels to the left or to the right based on the flip. And that's from the center. And then the next step is to take the self.position 1 plus 23. So that will be below the player in the ground. So this is just kind of scanning out in front of wherever you're facing and then into the ground. And it's taking this location and looking to see if there is a tile there. Now we have this as an if statement, and if it evaluates true, that means there's a solid tile and that we should be able to move. Otherwise, this will do self.flip equals not self.flip. So you just flip it around if there's not a tile there. The side effect of this is that depending on how far you're looking ahead and the tile size and stuff, it could theoretically end up in a situation where you're standing on a tile and just flipping back and forth constantly because there's nothing on either side. So you do have to be careful about that stuff. It's good to think about what your environment is when you're doing these types of things. Like, for example, right now, we have the code for not walking off the edge and turning around when it gets to the edge, but we don't have anything for if it hits a wall to turn around. I can write that up here in a moment, but I don't believe, yeah, they're both on a flat surface where they would walk down as opposed to up, and there's no walls for them to run into. So this is not the greatest example of running into walls, but all we have to do for the walls part is just take this part right here, just grab this, we say if that, and walking, you can drop it right here. If that's the case, then you just do the flip. So we're saying if you run into something on your right or your left, you turn around while you're walking if the solid check passes. Otherwise, you can walk. There's better ways to close this so you don't have to indent it as far, but I'm not going to bother with that. Anyways, that should handle the movement. So let's get into the animations here. So we'll do, this is pretty simple. If movement 0 does not equal 0, self.set action run, because you're moving, so you're running, else self.set action idle. And that's as simple as it is. So if you're not moving, set it to idle. This is a lot simpler than the player's animations because it doesn't have jump or stuff like that. So now you can see that they're walking around and stuff. And they turn around when they get to the edge, which is nice. And they kind of walk for random durations and pause for a bit, which is exactly what we wanted. All right. So the next part is to give them a gun so that they can shoot at us. So I'll go to entities again. And for this, we'll need to modify our render function for the enemy so that we can draw a gun on top of it. So to do that, we'll do def render self surf offset equals 0, 0. So this is like we have down here for the player, except instead of hiding it behind something so we can turn invisible, we're just going to take this as is and call the parent function for the rendering. So this is effectively the exact same as not having that function at all. But we're going to add in some extra stuff here because we want to show the gun. So we'll have if self.flip pass else pass. So the gun will need to be able to flip depending on which direction the player is facing. Let's go back over to game and load in the gun. So we do gun, load image, gun.png. It's as simple as that. And then we go back to entities. And we can render this gun image on top of the player. So we'll do surf.bullet And this is where we're going to have to handle the flipping, because so if self.flip, that means the gun should also be flipped as well, because if you're facing left, then the player image is flipped. So since the gun image is facing right by default, we also need to flip that so it's facing left. So we'll do pygame.transform.flip. We've seen this before. Self.game.assets gun. And then we'll say true on the x-axis, false for the y-axis. So this is flipping on the x-axis. We'll do self.rect.centerx -4. This part is just to offset the gun so that it's put in the right spot. You can play around with this number to visually see how it changes. It's just moving it by 4 pixels. And there's just a specific spot I want this placed at. And then we'll do -self.assets gun.getWidth. That's just accounting for the width of the gun image, because we want to render this from the perspective of the top right of the gun image when the gun is facing left, and the top left when it's facing right. So subtracting the width accounts for that. This is another thing we should just kind of play with the numbers and see what you get so you understand. And then, so this last part is the offset of the camera. So this is the same thing used on the player's rendering as well. And then we can do the y-axis, which is rect.center y, and we don't touch this, we'll just do offset -1, so we don't want any funny offsets there. This is a 188 character line of code, so this is a bit long. Remember, if you get lost on this, go ahead and check out the reference files in the description. So the other side's a bit easier because we had to do special math to do with the flip, plus the actual flip transformation in there. So we'll do something a lot simpler for this one. So surf.blit, self.game.assets gun, and self.rect.centerx +4. So this is the other direction, so we want +4 instead of -4. Minus offset 0, that's the camera, self.rect 0, rect.center y minus offset 1. Alright, so this is much simpler. It's the center with just a 4 pixel offset and the camera. And that should render our gun. That was a bit hectic, but here we go. Oops, I must have written self.assets somewhere. Where did I do that? Ah, yes. This should be self.game.assets. Alright, so I run it, and they're holding guns. If you notice, the guns are held out in front of the enemies. They're floating for now, but it'll look a little bit better when we add the outlines later. And they're a bit small, but that's because it's pixel art. In proportion to the player, they're probably the correct size. It's just a small aesthetic thing that we wanted to tack on. Now, the next step is to make these guns shoot. So the way this is going to work is that not that we have a gun object that can shoot, but instead we're going to make it so that the enemy renders the gun image and then also generates the bullets. Before we can actually have our projectiles, we need to create something for them to be stored in the game itself. We also need the image for the projectiles. So for this, we can just copy the gun thing and say projectile, and just copy that over there, and we're good. So that has the projectile image. You can look in the files if you want to see that. So let's go ahead and add the projectiles. So I'm gonna drop them right around here by the particles. We'll do self.projectiles equals boop. So this is gonna get pretty messy here. We're gonna go down here right below the player because we want the projectiles to be on top of the player, but not above the particles because we want the particles to be on top of the projectiles. So we'll go right here and we'll say for projectile in self.projectiles.copy because we're going to be removing these later. And we'll say projectile 0, 0 plus equals projectile 1. So what we're going to do here is these projectiles, we could make them objects, but since they're so simple, it's easy to just give it a list. So what it'll be is an x coordinate, a y coordinate as a list for the first value. So here's what it'll look like. We'll have x, y, and then we'll have direction, and then we'll finally have a timer. So all we have to do is modify, since these bullets only fly horizontally, we modify the x position. Actually, this would be a list because we're modifying it. We're modifying the x position based on the direction. So we grab the position, we say the x component, and then we add the direction. for the movement. And then we can do projectile 2. This is the timer, plus equals 1. And then let's grab the image here. We want to shorten this to image because we're going to be writing this a bunch. All right, so let's draw the projectile. So we'll do self.display.blit image projectile 0, 0 minus image.get width divided by 2. When you subtract half of the width of something, that just centers it, at least if you're doing that for rendering. Because it's based on top left, if you subtract half the width, it's top center. If you want to do the height too, that'll give you the true center, which we will also do. But first, let's add in our render scroll here so that the camera's applied. And then we'll do projectile 0, 1 minus image.get height divided by 2 minus render scroll 1. So something important to remember here is that if you're like adding something new into something like a world where you have a camera like this, oftentimes if for some reason it doesn't appear, it's because you got your camera stuff wrong. So make sure that you're always thinking about how the camera should apply to whatever you're working on. If you're working on, say, like a HUD element, so like maybe a health bar or something that's popping up in the top left of your screen, you don't need to apply the camera scroll to that. But if you're working on something in the world, you need to apply the camera scroll. And then there's the other way around, where if you're working with something in the world and you want to convert something that was in the units of the screen space into the world space, you have to apply it backwards. So it's just something always important to think about. All right, so we're rendering our projectile here. So the next step is to make it disappear if it hits a wall. So we'll do if self.tilemap.solidCheck. This is the same thing that the enemies are using to determine whether or not they should turn around. We'll do projectile 0. So this is the location of the projectile. So we're checking if the location of the projectile is a solid tile. And if it is, then we want to remove it. So all we have to do is self.projectiles.remove projectile. And then we can add some effects here later, but we won't for now. Now the other case, and this is why we have a timer, is because if it just flies off the edge of the map, we don't want it flying forever, because then if it just keeps flying, it never disappears, and as the game runs longer, you'll get more and more projectiles, and eventually it'll lag out because there's too many projectiles. So what you do is you say projectile 2 is greater than 360. So what we're saying here is if our timer, which is, this is the reason we added it, is greater than 360, which is 6 seconds, then we can do self dot, and this is just this code. So we just remove the projectile again. All right, so let's add one more thing. We'll do elif. We want to add something that checks if it hit the player, because it's a projectile that's supposed to kill the player. So we'll do abs self.player.dashing is less than 50. So what we're saying here is that if you're not in the actual moving fast part of the dashing animation, so if it's either on cooldown or if it's at 0, then we do the rest of what we're about to do here. So this check is just to make it so that when you dash, you're actually invincible. And that's how a lot of games do stuff like that, so it's a fun little mechanic. All right, so now we need to check if the projectile hit. So we can do self.player.rect.collide point, and we give it projectile 0. And if that collides with the projectile's position, we know that it's hit the player. So from here, we can do, once again, removal of projectile. So this will work for now. We could print something out if we wanted. Later on, we'll add some visual effects and make it so that it actually kills you and there's a transition and everything, but we'll get to that in a moment. So let's go ahead and run this and see how it's working. Actually, wait, no, we can't yet. We need to add the projectiles. We need to spawn them. So for that, we go over to the enemy. And instead of using like another random factor, the way we'll do this is that when it decides to stop walking, after walking is when it'll shoot. So this adds a more consistent behavior to shooting, because in games, it's nice if enemies have some way of indicating that they're about to attack. So in our case, it makes a lot more game design sense to line up the shooting with some sort of predefined action. So if, for example, which is what we'll be doing here, you shoot after you're done walking, then the player has all of that time where the enemy is walking to get out of the way. So it's a little bit of a warning for the player and adds a bit more depth to the game. So what we'll do here is we'll say if not self.walking. So if you notice, this is under the if self.walking clause. We're saying if not self.walking. This is because we have this code right here, which is running down the timer. So we'll get one frame where it passes this statement, then it modifies it to go to 0. So it'll go from 1 to 0. And so it'll pass this, and then it'll pass this so that we can get to this part of the code. And this is where we can add this once every walk cycle effect of spawning a projectile. So in order to actually shoot, like I mentioned before, we need to check where the player is and whether or not we should shoot. So first of all, let's calculate the distance between the enemy and the player. So to do this, we'll do dis equals self.game.player.position0 minus self.position0. And we'll also just do a self.game.player.position1 minus self.position1. So this is just the difference between the player's position and the enemy's position. So from here we can determine if we should be able to shoot. So we'll say if the absolute of the distance is y-axis, so that's how far apart they are on the y-axis, because we're taking the absolute. And we'll say if this is less than 16 pixels, so if the y-axis offset between the player and the enemy is less than 16 pixels, now we need to run some other checks. So we need to check if self.flip and dis0 is less than 0. So if you look at this, think about it. So if the player is to the left of the enemy, you will get a negative number, because say, well, to the left would be, say, 0 pixels, and the enemy would be at 10 pixels, so you would get 0 minus 10 is a negative number. So if dis0 is less than 0, that means that the player is to the left. And the flip, when true, means you're looking left. So we're checking if we're looking left and the player's to the left, then we should be able to shoot. And the flip side of this, pun intended, is if not self.flip and dis0 is greater than 0. So if the player is to the right and you're looking to the right, then, or rather the enemy's looking to the right, then it can also shoot. So we'll do self.game.projectiles.append, and this is just that list data, remember, so it's position, and then its direction with speed included, and then the timer. So we'll just do self.rect.center x minus 7, self.rect.center y. So this is going to spawn it to the left because we're facing left, because we don't want to spawn the bullet exactly inside the player. We want it to be cast out a little bit. All right, and then we give it our speed, so it'll be facing left, so it's a negative number, and then we give it 0 for the timer. And then we'll copy this, and then we'll do the same thing for the right direction. We'll do plus 7 instead of minus 7 because that's right, and then we'll also make the speed 1.5 instead of negative 1.5. All right, so that should create our projectiles. So let's go ahead and run the game and see what we have. All right, so we have 2 enemies here. Might be a bit difficult to get them to shoot at me from here, so we'll get over here. So you saw the projectile just briefly there. My body blocked it, so that shows you that that was working. I guess technically on this map, there's nothing for them to shoot at because, well, they saw a projectile go off to the side there, but there's no walls for them to shoot at. So this is not the greatest example for walls, but there are walls on the other maps that they can shoot at. Anyways, so I actually can't get up to this other one up here, but this one is shooting correctly. So if you notice, if I'm in the right spot when it stops walking, so I actually have to be kind of level with it. So if I'm standing down here, it won't shoot. But if I'm level with it, or close to level, it will shoot, and it'll create that projectile, which can hit me, and we can trigger something off of that, like dying, for example. So let's go ahead, since we have all of this working, we can go ahead and load in the custom maps that I had pre-made. So if you look in our files here, so we have all these images, but we also have this maps folder, which has 0, 1, and 2. So I'm going to actually create a function called load map here, We'll call it def load map self map ID. Actually, let's call it load level. And then we'll do self.tilemap.load. And we'll do data maps. And then we need to add str map ID plus .json. So whatever map ID we give it here, it could be an integer, it'll convert it to a string and it'll load that map. Now the other thing to keep in mind is that when you load a map, especially since we're going to be loading maps multiple times because you want to change to different maps, we're going to need to clear out all the particles, all the projectiles, and all the visual effects and stuff, and just reset everything. And then we also need to reload like the player position and everything. So these things right here, these spawners need to be copied down, and the projectiles, and the scroll. So all of this needs to be copied. So we'll just take that, delete it. We'll go over here to the load level, drop them right there, and that should load it in with the level. And now instead of doing this tilemap.load right here, we can do self.load level, and we'll give it 0. So now this should load one of the pre-made levels that I have. You can look into these files if you want. You could copy them out and rename them map.json if you want to open them up in the level editor as well to see what they look like in there. But we'll be running this from here. So let's go ahead and run that. And we have this nice little map. If I stand right here and wait for him to shoot at me, you can shoot at a wall and you can see that the projectile disappears. So that's the test case for that. And we have, this one's a lot more nature filled than the other test map that I had. And there's this little rock section over here as well. But it's a pretty nice map. There's a few enemies hanging around. So the next thing I want to do is to add some visual effects here. Because if you notice, when I get shot, it doesn't look too nice. The projectile disappears. If the projectile hits a wall, it just disappears. And also when they shoot, it just makes the projectile appear. So that doesn't look fancy enough for me. So we're going to do a little bit of trigonometry here and start making this look fancy. So the way we'll do this is we'll add something called the sparks. This is, I guess, one of the most common things you'll see in my games nowadays in terms of visual effects that distinguishes my games from other games. Because there's a very particular way that I do these that just kind of stands out, I think. I don't think it necessarily looks that good compared to other methods. It's just that it's kind of distinctive, so I can look at games and clearly see a difference based on the fact that I use this technique. All right, so these spark effects should be above the projectiles but below the particles. So we'll do for spark in the self.sparks.copy, and we'll do this similar to how we do the particles, or not the particles, the projectiles, where we wrote the code for managing it first and then added the data. So this time though, because it's so much more complicated than projectiles, we will be creating a class for it. So we'll just do similar to the particles here. Actually, we'll do kill equals spark.update, and then we'll do a spark.render self.display offset equals render scroll. This is the basic rendering stuff. And then if self.kill, we do the basic self.sparks.remove spark. So this is just keeping track of the individual spark visual effects that we need to render. So it'll update it, determine if it should be removed, render, remove if applicable. So this is just a self-managing thing right here. All right, so now that we have this, we need to have this spark object that we're iterating over in our self.sparks that we're calling .update on. So we'll have to add that in now. So we can do this as a new script. So we'll go new file, we'll say spark.py, and we'll do import math, import Pygame, and we'll do class spark. This one won't inherit from anything because it's pretty basic. We'll do an init function. We need a position, an angle, and a speed. That's all we need. If you look at my actual games where I have this effect, I'll actually add more options to the spark. This is about as bare bones as you can get for sparks. Normally, I will have all sorts of things. You can configure the size and how fast they decay and stuff, but I don't want to get too much into it here. We'll just kind of assume a lot of things in our update function. A lot of the sparks will look the same. All right, so we need to apply our position equals list position, and then we need self.angle equals angle, self.speed equals speed. And then we need an update function. This will be easy. If you remember, we did that thing with particles where we converted polar coordinates into Cartesian coordinates using cosine and sine. So this time, instead of just doing one conversion and being done, we're storing the position in Cartesian, but our angle is polar. And our speed is the length part of the polar coordinate. So the angle and speed together, represent the polar coordinates for the velocity vector, essentially, if you want to get technical about it. To handle that with our Cartesian coordinates position, because you need that for rendering, we do plus equals math.cosine self.angle by self.speed. Remember, if you're doing polar to Cartesian, you just do cosine for the x, sine for the y, and you're pretty much done. And then you multiply it to add in the length. But similar to the particles thing, the reasoning for using polar coordinates here is so that if you're moving diagonally, it doesn't move faster. But then there's a second use case here, which is where when we get into the trigonometry of the rendering for the spark, you need the angle that the spark is facing. Technically, you could just store it as a velocity and then convert that back into an angle so you can do the rest of the math, but it's easier to just keep it as an angle and then deal with that later. So the way these sparks will work is that it's a white diamond shape, a very long but thin diamond, basically, and it'll move in the direction of its angle, but then slow down. And as it slows down, it shrinks. And once it stops, it disappears. So the size of it should be proportional to the speed as well, so that it shrinks down as it slows down. That way, once the speed runs out, it would have just smoothly disappeared because it just would have shrunk to an infinitely small size. So we'll do self.speed equals max 0 self.speed minus 0.1. So if in effect the speed is its timer. So we'll just subtract 0.1 from the speed every update and return not self.speed. So once the speed is 0, we return true, which is the kill signal, which will remove it from the list of sparks. All right, let's do a render function, and then we pass in a surf and offset, same as we always do. And we'll take, this is where the trig comes in. We want render points equals, and what we'll be doing here is we're going to create a polygon, and then we'll use Pygame to render that polygon. I'll go ahead and render the polygon with this code, assuming this is filled out first, so they can see what we're doing. We'll do Pygame.draw.polygon. We'll give it the surf. We'll make it white. We'll give render points. So Pygame.draw.polygon will take a surface to render to. It'll take a color that it'll render the polygon as, and then the list of points that create the polygon. So this polygon is automatically closed. Your start point and end point don't have to be the same point. So if you're running a square, you have 4 points, not 5. So it's actually the 4 edges. Now, there's an extra argument here if you want to use it for the width, but we don't need to use that. If you don't specify a width, it'll automatically be filled in. And that's actually a lot of the shapes work. The rectangle is the same. If you render a rectangle using Pygame.draw.rect, if you don't specify a width, it'll fill it in. If you do specify a width, it'll just draw the outline of the shape and not fill it in. So you can do some other visual effects there if you set a specific width. All right, so let's fill in our points here. So we need to create that thin diamond shape based on the angle of the spark. So if you're facing right, you should have a horizontal spark. If you're facing up, it should be a vertical spark. So to do that, and that's not just the 2 cases, it needs to work for any direction. To do this, we'll do self.position 0 and plus, and if you remember, when you want to apply a rotation for a movement, so if you want to move in this direction or something, remember you do the math.cosine of the self.angle, and then you multiply by the speed. So in this case, normally if you want it to be like 5 pixels out, you just multiply by 5. But since I mentioned before that the speed is going to shrink, and as the speed shrinks, the actual spark should also shrink, we're multiplying this coordinate by the speed. So what we're doing is we're actually casting these points out from the center of the spark by adding the cosine of the angle times the speed. So there's other stuff I'm about to do here to create this shape. It's going to get pretty messy here. but we're going to cast them out in the 4 directions. So when you have angles, if you remember, a full circle is math.pi times 2. So if you want to, for example, cast out a point behind you, you do plus math.pi, because that's half a circle. So it goes around half the circle and it just points in the opposite direction. If you want to go out just 90 degrees in a direction, you can multiply by 0.5. So that's a quarter of a circle, so it'll just rotate 90 degrees. All right, so that's roughly how that works. So I'm going to get in and do the messy part here. So we're going to multiply the speed by 3 because we want one part of the spark to be longer than the others. So we don't want a square. We want a diamond where 2 of the ends are way further out than the 2 sides. And then we need to apply the camera offset, so that'll be minus offset 0. And then we do self.position 1, and as mentioned before, we just do math.sine, same thing. Self.angle by self.speed by 3 minus offset 1. All right, so we can take this, we copy this, and then this is where we start getting into the different angles here. So we have this one right here, since it's using the angle that the spark is, this is the forward point. So this is the one that's being tossed out in front of where the spark is going. So now let's do one that's either to the right or to the left. You actually don't have to think about which one this is, because we're going to go do both sides. The order does matter, but only in the sense that you don't want to do opposite ends next to each other, because you have to go all the way around. Otherwise you get a weird shape when you try to draw the polygon. You'll get like an hourglass shape, I think, if you do it out of order. But you can go either way. You can go clockwise or counterclockwise. It's just important to not do opposites next to each other. So we do plus math.pi by 0.5, so it's 90 degrees offset. And then we can just copy this, go over to the sine, so that's the y component, and do the same thing. So that's another offset angle. So we're casting it out to the either to the right or to the left. And then the next step here is to make it, because this is one of the side points, we don't want it to be cast out as far. So we'll switch this 0.3, well, we'll switch this 3 with 0.5, so that the ends are going to be 6 times longer than the sides. So now with this, we can just copy this, both of them, because for this we'll do plus math.pi and plus math.pi. So this third one right here, this is going to be the one facing in the opposite direction from where the spark is going. That's why you're adding half a circle to the angle. And then we keep the times 3 because this is another long one. And then the next one's a short one. So for this one, we can subtract math.pi. The other option is to add 1.5 times math.pi, but subtraction looks nicer to me, so we'll do that. So this will be the 4 sides, so we get forward, and then this gets a bit weird because of Pygame's coordinates and math coordinates are not the same. So one of them is this side, backwards, and then the other side, so this creates a full diamond. All right, so I know this is also kind of a bit of a mess of long lines here, so you can check the reference code if you made a mistake here. You can also play around with this to create some other shapes and some other nice effects. Anyways, this is all we need for the spark, so we can take this and we can start adding it to things. So let's first add it to the enemy. So when the enemy shoots, it should create sparks from the gun. So the way we'll do this is we'll just go right here, and we'll just do for I in range 4. So we want to do something 4 times. We'll just do self.sparks.append spark, and we do need to import spark, so we'll go up to the top here and we'll just go boop, 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 spark, spark, and that'll import our spark for us. So we can go back down to here now, and we can finish our spark. So it needs the arguments. If you remember, it's position first. So for this, we'll just take wherever the last projectile is spawned. So self.projectiles -1. We'll take the coordinate component, because if you remember, this part right here, the first part is the coordinates. So that's the location of the last spark. You could just like copy this out, write this as a position and reuse it here, but this is another way you can make this work. And then we'll take random.random minus 0.5 plus math.pi, comma 2 plus random.random. So you can see VS Code telling me what these are. So we have the angle here. So what we're doing is we're taking a random number, and then subtracting 0.5, so it's a random number between negative 0.5 and 0.5, and we're adding math.py to it. So this is the projectile that actually is shooting left. So the angle for left is math.py. So that's because the right, just pointing right, the angle for that is 0. If you look into unit circles, that's how it is, although it's upside down in Pygame for some stuff because of the fact that in game development the y-axis is flipped. So, but either way, the opposite direction from right is going to be math.py. So what we're saying here is a random direction in the direction of left plus or minus 0.5, so there's random variance, but still pointing left to some extent. And then we'll also take 2 for our speed and add random.random, so there's variance in the speed of our sparks here. So this will cover that, and then now we can go over here and do the same thing, except we don't need that plus math.py because we want it to face right instead of left. All right, so this will cover our spark spawning for the shooting. So the next part is the spark spawning for when it hits stuff. So let's go back over to the game where we have this code for the projectiles. And we'll say in here, if it hits a wall, we want some more projectiles. So we'll do 4i in range 4, so 4 sparks again. We'll just append them. And similar to before, we'll need to go ahead and import these sparks. I'll just copy the import statement up here. And we'll go to the top of game, drop it right here, scroll down, and we now have this loaded correctly so we can do other stuff here. So we'll just take the projectile 0, since we're not using the last projectile anymore, we're just using the current one that we're iterating over. So the angle should be this component, and then we want to do a bit of a funky thing where we do plus math.py, but only if projectile 1 is greater than 0. So what we're saying is that we want to shoot the sparks left only if the projectile is going right. Because when you hit a wall, I mean, there's 2 ways to do this. I like the style where the sparks bounce in the opposite direction when it hits a wall, because that's where the sparks would reasonably go. You could also go in the direction of the projectile, so you could flip this around if you wanted, but I like it this way. So we're saying that it bounces back to the direction it came from, is where the sparks will go. And then we'll take the speed as well, which will be the exact same speed thing from before, which is just random number from 2 to 3. And this will cover the wall case. So the last one I want to deal with, and this is going to be the big one, is when the projectile hits the player. So what we'll do here is 4i in range. We're not going to do 4, we're going to do 30. We're going to spawn 30 sparks here. And for this one, I'm going to write out the arguments beforehand. So we'll do angle equals random.random by math.py by 2. Remember that full circle is 2 times pi. So random.random times that will give you a random angle in a circle. And then we'll do speed equals random.random by 5. And then we'll just do self.sparks.append spark. And we'll say self.player.rect.center. We can give it the angle, and then 2 plus random.random. So the other thing we have to do here is not only are we adding the sparks, but we want to add the particles. So this is the death, so there's going to be a lot of stuff going on. You can do self.particles.append. Do we have particles in here? Yes, we do. Particle, self.game, particle, so this is the black one, self.player.rect.center, the velocity equals math.cosine, you've seen this before, plus math.py by speed by 0.5, math.sine, angle plus math.py by speed by 0.5. So this is what the speed is for. So the speed right here is randomly chosen for the particles, but I'm reusing the angle for both the sparks and the particles, but I added math.py to the angle here so that the particles shoot off in the opposite direction of the sparks. Anyways, so that's the mess of visual effects for that. Actually, there's one more we gotta do. There's the frame. So we'll do frame equals, and we'll do random.random 0 to 7. All right. So once again, go ahead and check the reference code for this section if you're a bit lost on this because the lines are a bit long. Let's go ahead and run this. So there should be lots of sparks now. I gotta wait for one to stop walking while I'm up here. Hey, turn around. It's gonna shoot. Oh, it crashed. Enemy has no attribute sparks. Okay, so that was a mistake. So that's going to be over here. We have self.game.sparks, not self.sparks, because this is from the perspective of the enemy. Right. And enemy has no attribute projectiles. Yeah, that's going to be the game.projectiles. Let's see if we got it this time. Hello? No. That kill. Yeah, that's not self.kill, that's kill. Okay, so you saw there was stuff there. So a couple things happened. There was the sparks, which are working when it shoots, but then it crashed when it hit me. So, game has no attribute game. So, what we did here, this should be self, not self.game. And that should fix that. And we should be able to get shot and explode. So you saw there was an explosion there, which is great. Let's see if I can, let's see if I can get him to shoot the wall. So I need him to turn around. There's a wall to the right. If I can get him to shoot there. If he will walk. Will he walk? Let's see. Come on, you gotta go a little bit further than that. There we go. So now if I go down here, we can see if it hits the wall. And the sparks bounce back the other way, just like we added. Alright. So it is possible to get hit. We'll have to add dying later, but first let's make it so that we can actually kill the enemies. So to do that, we use the dash stuff here. Let's go over to our entities. Let's go in the enemy update function, and let's go over to the bottom here, and we'll say if abs self.game.player.dashing is greater than or equal to 50, so that if you're in those frames where you're actually moving in the dashing thing, then we can do if self.rect.collideRect self.game.player.rect. So we're checking if the rect of the enemy collides with the rect of the player. That's like if their hitboxes collide. Then we know that they touched while the player is dashing, which means that the player hit the enemy with a dash. So now we can do something based on that. So what we'll do is if we go back to our game here, we have our enemy code. We want to say, similar to everything else, kill equals that. If kill self.enemies.remove enemy, and then we can go back over to our entities here and we can just return true if we want, because we're in the update function. If we return true, it'll remove the enemy. So all we have to do here is, since they touched, return true, and this is where we get into the mess of visual effects again. So I'm going to cheat a little bit here. I'm going to grab the visual effects that we used for the player's death. I'm gonna copy them, go over to here, paste, and it will have the same effects. So there's a couple things we do have to fix here. So this is referencing self.player because it's from the game's perspective. Fix the indentation. This should be self.game.player. And then this should be self.game. And anytime where we have .player, it should be .game.player. So this is a long thing right here. Just run through it real quick, make sure we got everything. Yep, that should be everything. Now the last thing is that I want to add two big sparks that shoot out from the sides when you hit the enemy. So we'll do self.sparks.append, and we'll do spark self.rect.center, and our angle will be 0 because that's to the right, and then 5 plus random.random, so that's a much higher speed, which means the sparks will be much bigger and go much further. And then we went the other direction, which is going to be math.py, so that's just right and left sparks that are very big that we want to add. So the last thing here is that actually these particles and sparks are in terms of the player. This should actually be the enemy. So we just chop off the player part, so we didn't actually need that player part. So we want to spawn the sparks and particles based on the enemy's position when they hit, and then that should be good. So let's go ahead and try to delete one of these enemies here. Dash through it. It crashes. Not ideal. All right, so we go over here. Other mistake. This should be self.game.sparks. and particles. Now let's try that again. Suboptimal. What this time? We have, oh, right here also. All right, one last time. I think this should be correct. Dash through, and they disappear. Perfect. So you get those two sparks shooting off to the side, which look nice and fancy. And you can, like, destroy them and everything. So, boom. So we can kill the enemies. That's great. The last thing is that we want to make it so that the player can die. So we can get shot, and it does the particles and everything, but the player needs to be able to die, and the level needs to be able to restart. So to do that, we'll go ahead and add a dead attribute here. So we'll do self.dead equals 0 in the game's load level function. We'll have dead equals 0. So this will just be set to 0 by default when you start the game. And when the player is hit by a projectile, we want self.dead plus equals 1. And here's where the magic comes in. We'll go over to the top here and we'll say if self.dead plus equals 1. So it starts at 0, so this won't add initially. But once you're actually dead and it's a positive number, it'll keep adding to it. And then once self.dead is greater than 40, self.load level 0. So all we're doing is we're creating a timer that starts as soon as you die, and after 40 frames, so 2/3 of a second, it'll load the level again and restart you. So for this, all that's left is to actually make the player disappear when it's dead. So all we have to do is head over here and say, if not self.dead, then you can do all these player things like moving around and rendering. So let's go ahead and test this out. So let's get shot. Hello? Nope. There you go, I got shot. So if you notice, you got the delay where you can see the body disappear and the explosion of sparks, and then the level reloaded. So if I actually kill one of these enemies here, and then if I go die to the other one, you'll notice that the one on the left will respawn. And then I will respawn at the start of the level, because I reloaded the level, and all the stuff for like spawning the players, spawning the enemies, loading all the tiles, clearing all the particles, and everything occurs when you load the level. So that's a nice reset for us. So that covers everything for the more gameplay stuff here. This is probably the last big thing that we had to do for this project. The rest is just easy stuff to make the game look nice and just kind of polish it off. So congratulations for getting towards the end of this very, very long tutorial. Definitely the longest I've ever done. So I just noticed that I forgot to add the part that handles the case where you're just falling off the edge for too long. So let's say you just run off the edge. You're stuck like this. The only way to get out of this is to close the game and restart it. So that's something that needs to be fixed. And to do that, it's a really, really simple trick. All you do is you just go in here, take the airtime. If self.airtime is greater than, I don't know what a good number is. So let's say you're in the air for 3 seconds, so 180. We do self.game.dead plus equals 1. Simple as that. Actually, we don't want to do plus equals 1 because this is something that will activate constantly once you're past a certain point, which means the death time will last longer. Actually, you know what? That would be fine because you're probably going to be off screen because of the falling anyway. So we'll do plus equals 1. Actually, I think 120 would be a better number. The other thing we have to do before this will work is we'll have to go over to the game and we need to find the player. Say self.player.airtime equals 0. Because we don't want it to trigger multiple times. All right, so let's just jump off the edge here and see what happens. All right, so it spawns back, which is good. So that way you can't just fall forever, and that fixes that issue. All right, so the next thing we'll want to do is start to get into the polishing of the game. The thing that I had in mind for this part is the Screenshake. So the Screenshake is a pretty simple concept. There's a couple ways you can do it. So one way, well, I mean, obviously it's just a screen shaking supposedly. One way is to modify the scroll value for the camera so that the camera is moving around suddenly. The other technique, which is a little bit more convenient, I feel like, is to modify just this number right here. So when we're scaling up our display onto our screen for the pixel art, we blit it at the coordinate 0, 0. So if we just change this number, let's say we put 50 right here and run the game, you'll see that we've got this black bar on the edge. We can move where we're rendering this thing. So we can like put whatever we want right here, and this could effectively be our screen shake by just changing these values. So we can just take these numbers and generate a screen shake value from them. So let's see here. Let's create self.screenshake equals 0. And over here, let's do self.screenshake equals max 0 self.screenshake minus 1. And that will make it so that the screen shake value is like a timer. We've done this before a bunch of times, that goes down to 0. And if it's positive, we want to offset our screen by it. So this is pretty simple. We just do screen shake offset equals random.random by self.screenshake minus self.screenshake divided by 2. And this will just make it so that you get a random modification in pixels from the number 0 to whatever the screen shake value is. You can just drop screen shake offset right here, and this will offset our screen with the screen shake value. Alright, so now we just need to apply our screen shake. This is pretty easy. Let's find somewhere where we want it to be applied. So right here, when the player gets shot, we'll do self.screenshake equals max 16 self.screenshake. This is so that it essentially sets it to 16, but if it's higher, it won't actually pull it down. That way that a larger screen shake won't be overwritten by a smaller one. Also, something to note is that this is kind of like the speed thing for the sparks, where the effect is increased as the timer is higher. So the offset here is going to be greater when the screen shake number is larger. So it kind of eases off, but you give a big number, it gets a large screen shake and lasts longer. All right, so let's take this and let's copy it over to the enemy code. So let's go into the entities and let's go into the enemy update function where we have the killing based on the player's dash. We can just drop it in here, and this is the self.game.screenshake because we want there to be an impact when you hit an enemy with your dash and destroy them. So now the last thing is when the player's falling, which we just added, you want to do the same thing. You want to screen shake there. We've got to be careful with this, so this should be hidden behind a if not self.game.dead. Actually, no, technically you wouldn't need that because I just remembered the update function won't be called if you're dead, but whatever, I'll leave it there. It's no big deal. All right, so now you should get some screen shake. Boom. So you can tell the screen's shaking when I hit them. And let's get shot real quick. Just show the other case. Boom. All right, so yeah, there's a fair bit of screen shake, which is a very nice visual effect. It adds a lot of emphasis to the different actions. And it's a really simple effect to add it, as you just saw. So I like to add it in a lot of my games. So we actually have our different levels here. If you look in maps, we have 3 of them, or rather I made 3 of them for you to use. But there are 3 maps, and right now we just have it hard-coded to just load the first one. So the next thing is to make it so that you can actually beat a level and transition to the next one. So the way you can do this is by, well, when you beat it, you just call self.loadLevel. You've seen how when you die, you have to just reload level 0. So now we can just take a level variable and use that to load the next one. But I want a fancier transition, so it won't be as simple as just writing a couple lines to just once you win, move to the next one. We're going to have a proper transition, so there'll be a timer and everything. So for that, let's go ahead and do a self.level equals 0 just to start us off, and we'll use this whenever we reload a level. So we can do load level, find the other use case, which is right here, and we can just copy in that self.level value. So now we can keep track of what level we're on with self.level. All right. With that, now we need a transition variable. Self.transition equals -30. This is on the load level. So whenever you load a level, I want the transition to be -30. The way I want this to work is that we'll have a circle of what you can see that shrinks down at the end of a level and then grows bigger at the beginning of a level. So between those two, after it shrinks down, it's a completely black screen, and then at the beginning of the new level, it's also completely black screen, but then grows into a scene where you can see the full thing from that circle. All right, so the idea is that when it's at -30, you want to show a completely black screen, and it'll go all the way up to 0 for full visibility. And the way we'll make this loop is that it'll go from 0 at the end of a level to 30, which is when you get the black screen, so it'll shrink down. It's a bit difficult to explain, but you'll see it as I implement it. So let's go over here into run, and I'll just start writing the logic and I can explain it better once you can see what I'm doing here. So we'll have if not len self.enemies. So if you've killed all of the enemies, we do self.transition plus equals 1. And then the other case is if self.transition is less than 0, self.transition plus equals 1. So what we're getting here is that it starts at -30, it goes up automatically until it hits a transition equals 0, and it won't go any higher on its own. And then once there are no enemies, this will automatically increase transition even more past 0, and then once we're up to 30, then we can do self.level plus equals 1 and self.loadLevel self.level. So the way this will work is, like I mentioned, start at -30. This is the beginning of a level. Your vision goes bigger until 0, and then anything above 0 and it shrinks. So the way you can think about this is that when the absolute of the value of the transition is 0, that's when you see everything. When the absolute value of the transition is 30, that's when you can see nothing. The fact that I'm using the negative and positive numbers is just a trick to keep track of the state of their transition mathematically the way you need it to be. Because another thing you have to think about is that you have to load the level when it's black, when it's completely black, because when the view is shrinking down from the old level, you don't want to transition to the new level yet. You want to still be seeing that old level. And then as soon as it starts opening back up again, you want to be seeing that new level. So it's a smooth transition. So it's important to get this right when it's at the full black screen. So yeah, that's how that's going to be implemented. All right. So the next step is to actually visually implement this. So what we'll do is we'll do if self.transition, we'll do transition surf equals pygame.surface, and this is where we'll do a bit of some graphical magic. We'll do self.display.getSize. So this will just create a black surface, the size of our display, and this is what we'll use for the transition. So the trick here is we'll draw a circle on the surface, and then we'll set the color key of the surface to the color of the circle. That way that the circle we draw is a transparent part. So if we blit this surface on top of the screen, you'll just see the outer edges that aren't inside the circle. So that'll give us the effect we're looking for. We just change the size of the circle. So we can do pygame.draw.circle, transition surf, that's the destination. So we're not drawing something onto the screen for once, we're drawing it onto something else. And then we'll draw this thing, which we're drawing onto our screen or display or whatever. And so this is going to be white, like I mentioned. It just needs to be a different color than black. It can be anything, because we're going to color key it. And then we'll do self.display.getWidth divided by 2, self.display.getHeight divided by 2. So pygame.draw.circle will draw a circle, and all these draw functions are like this. It takes the surface, then the color, and then the extra arguments. Usually if there's a singular position, this is where you'll find it. So in our case, we have the center of our circle, and then now we have to give the radius. So the radius will be, oh, and here it's telling us, so you can read that if you want. So our radius will be 30, because that's the number we were choosing before. We could change this number if we want the transitions to be faster or slower. And then we'll do minus the absolute value, remember I was talking about the absolute value of the transition, of the self.transition. And then the trick here is to multiply this by 8. So this comes from the dimensions of the screen, so you can do the math and do 30 times 8 and you get 180. So this is just to make sure that the circle can expand to its proper size and everything. So also, if you notice, this is clause behind the self.transition, so when you're not transitioning, when it's at that 0 and waiting for you to beat the level, it won't run this code. And that's because this code is actually a little bit expensive in terms of performance because you're generating another surface, drawing a bit circle, and then blending it onto the display. So it's an extra step we can cut out to save some performance if we want. So we'll do transition surf.set color key because we just do the circle onto it. And we want this thing to ignore the white color. So that will become transparent now. And then we just blend it onto the display. And just throw it at 0, 0 because it's the same dimension as the display as specified here. All right, so now if we run the game, and if we defeat all the enemies, it should theoretically transition, if I did it right. Let's see. And there you go. So we got the circles, and here's the second level. So you can just like run through it and try and kill all the enemies, and there's 3 of them, which I think I'll save the 3rd one for the end here. But something interesting to note is that I don't have the, let's see if I can go and shoot at me. I just accidentally dodged them all. The transition applies differently when you're dead. So one hacky way we can deal with that is to go over to this right here and say if self.dead is 10 or 30, because if you notice, self.dead actually goes for longer than the other transition stuff. Actually, no, it should be 10. We'll do self.transition plus equals 1, and actually it should be greater than or equal to 10. And then what we'll do is we'll actually take this, cut out the plus, and just do self.transition plus 1, and then we'll take the min, and we don't want it to actually go across 30 because that will trigger it to add to our level count. So we don't want that. We just want the transition to go as high as it can without actually going to the next level. So what we'll do is just lock it right before we go to the next level so that it's mostly done the transition, so it looks nice, but then it can stay on the same level. Oops, there's a typo in there. Where is that transmission? That's not correct. All right, let's try that again. There's one more issue we'll have to fix here. There we go. So that's working as intended. So we get ourselves our nice transition here when you die. But there's one more thing we have to fix, and that's this thing right here. We load the level by adding 1 to it, and the problem is this level can go too high. So what we'll do is, this is just kind of to stop it from crashing. Theoretically, you'd add more levels and extend this however you'd like if you wanted to make this a full game. But in our case, I'm just going to do something to prevent it from crashing. And we'll just take this and we'll say the min of self.level plus 1 and len os.lister data / maps. And we got to import OS to do this. But the way this will work, where we go, import OS. The way this will work is it's capping this by using min to the number of maps that we have. Although actually, now that I think about it, this should actually be -1 because we have 3 maps, but since we started at 0, the highest value is 2, so we don't want to go above 2 if we have 3 maps. So you just do -1 there if you're naming them like this. All right, so I won't run through that right now because that would take a while to actually run through the whole game, but you'll get to see this cap later on when I finish the game and run through the whole thing. But for now, I can just test it to see if it's still moving to the next level. And that's how I would know and test these things, because technically that line of code doesn't execute until you finish a level, and as you saw, it just worked properly there, so that's good enough for us. So let's go ahead and take that idea of rendering onto a surface that isn't your display for some graphical effects purpose, and let's take that to a whole nother level here and have ourselves a bit of fun by adding some outline visual effects. So to do this, we're going to need a second surface. And to do this type of thing in general, these types of visual tricks, a lot of it actually comes down to creativity more so than knowledge of the tools that you're using. I mean, you have to know how to use the basic functionality for your tools, but a lot of it really does come from the creative application of the basics. But this is just another example of something that I came up with a long time ago, and it's fun to use. Anyways, so to do this, we need a second display. So we'll do self.display2 equals pygame.surface. It'll be the same dimensions, so 320, 240. And we'll do pygame.src alpha. Actually, wait. Sorry, I had this backwards. Also, there's no underscore in src alpha. I feel like there should be, but there isn't. Anyways, so we'll drop it right here, actually, on display. Display is the one that needs it, not display 2. So the way we're going to break this apart is that we'll have display and display 2. So display is the thing that most of the stuff is going to be rendered onto. The naming here is slightly misleading because we're trying to make the code that we already have work for this. And this is just kind of a finishing touch. And this is something I actually recommend if you're making games. If you're almost done with a project, you can kind of just throw code cleanness out the window, because if you're not going to be working on it much longer, it's not too much of an issue. And this actually applies to a much broader section of game development than just the end. There's this funny idea that I heard a long time ago, is that there's two types of game developers. There are game developers that write good code, and there are game developers that release games. And funny enough, I actually have not released a big game since I started writing good code. Some of that is because I got a bit too much into trying to do things properly, and then some of that is just kind of other stuff going on. But overall, don't worry too much about your code structure, especially if you're working by yourself. As long as your stuff works, a lot of times it's not as important as people think it is. Also, there's the whole performance component as well, so you do have to keep that in mind. But let's move on here. So we have our two displays here, and the way this is going to work is that we render most of the stuff as normal onto the display, and we want to give some things an outline, not everything. So the way this will work is that the stuff that we want to give an outline will render onto display, and the things we don't want to give a background, so we'll do this for the particles and the background. For that stuff, we render it onto display 2. And the way this will work is that between those layers, so there's the back layer and the front layer. So there's the background, which won't have an outline. Then there's the foreground, which is going to be the particles. And before the foreground is drawn, we need to add our outlines. So there'll be a step right before the particles where we turn whatever we've drawn onto display into an outlined version of itself. So the way we'll do this is, first of all, we need to break up our rendering here. So we'll go down to where we render a background, and this needs to be display 2 now, because we're drawing the background and that shouldn't have an outline. And now self.display needs its own color, and this needs to be transparent because we're going to be doing some tricks here. So we're filling display with pure transparency. So if you put it on top of something else at this point, you would get nothing. But anything we draw onto this will not have a black background. It'll just be whatever we draw onto it. We can just split onto something else, and that's what we'll get. Anyways, so the next step is to jump over to that spot I was talking about. So we'll find the part right before the particles. I do want to include the sparks with the outlines because I like how that looks. But we'll need to create a display mask, and we'll do equals pygame.mask.fromSurface. And we'll pass in the self.display. So what we're doing is we're making a mask from the display, which is where we're rendering everything that we want it to have an outline. So if you don't know what a mask is, a mask typically, it can mean multiple things, but usually in computer graphics, a mask is essentially like an image with just two colors, black and white, or you can think of it as on and off, ones and zeros, however you want. But the idea is that you can do binary operations on them, but in our case, we're actually using it for something different. We're using this to convert something that has multiple colors, like tons of colors, into something that only has two. So what we'll do here is we'll create display silhouette. That is a very difficult word to spell sometimes. Thank you, French people. I'm assuming it's French. And we'll do display mask. So this is a mask we created. Remember, think of it as two colors, white and black. And then we'll do to surface. And actually, in terms of Pygame, it'll call it the set color and the unset color. So set color being kind of the white portion. But what we'll be doing is we'll do set color equals 0, 0, 0, 180. And then unset color equals 0, 0, 0, 0. So if you don't know, when you see 4 colors like this is red, green, blue, and then alpha. So the alpha is the transparency. So if it's 0, it's fully transparent. That's what we did when we filled the display up here. But 180 means that it's slightly more leaning towards opaque rather than transparent. So that 128 would be halfway because it's 255 is the max. And these first 3 are just saying it's black. So right here, it doesn't matter what the first 3 are because the last one's transparent. But for this one, it does matter because, well, that's going to be black. So this is going to be the color of our outlines. And the way this works is from surface, well, actually, if I have it, it says this. So it takes a surface, and then it will either use a threshold, which you can specify for what gets categorized as set and unset. But if you have a color key set, or if you have transparent pixels, it'll just take those and use that as unset. So in our case, because we filled it with this transparency, anything that's transparent will be unset. So what we get as a result is anywhere where we rendered something before is the set color, which means that it can turn into this. So now what we get is just kind of blobs of black wherever we drew something. So to kind of show you what this looks like, I'll do display2.blit, display, actually self dot, and then we'll do silhouette. And then we'll give it 0, 0 for now, and then we'll change that later. So if we run it right now, we get an interesting result. So you've seen this before. This is where everything's just kind of lagging behind, and we're not clearing the background properly, so we do need to fix that. The problem here is that we're rendering display instead of display 2, and we should be rendering display 2 when we're over here, which I forgot. But now you should see, here we go. Here's just the silhouettes of everything we're rendering. So you can see what's going on here. It looks like a nice fancy effect, but we're going to use this for the outline. So the way this is going to work is if, for example, let's do the next important step here, which is display2.blit self.display 0, 0, 0, or 0, 0. So it's just drawing it back on top. So this is just putting whatever we drew in this frame back over on top of the display. So we rendered our silhouette, and then we're rendering our stuff we rendered again. So if you run this again, you just get the game. And that's because this stuff is perfectly covering wherever we drew our silhouette. So if we want to see where the silhouette is, we can just do like 4, 4 or something. And you see we get that outline sticking out. Well, it's not outline, it's a drop shadow kind of. So there's a funny little shadow on everything now. But we don't want this shadow in particular, we want a proper outline. So to deal with that, we draw this 4 times. I'm going to replace those coordinates with offset, and we'll do 4 offset in, and this is where the magic comes, -1, 1, 0, -1, and 0, 1. And if you do that, you render it 4 times with an offset of these amounts. That'll do 1 pixel in each direction, so it's left, right, up, down. You get an outline. So now if you look at this, we have ourselves a nice fancy outline. Although now that I'm looking at it, I don't like the outline on the clouds. So let's go ahead and take display 2, which is the one that doesn't get the outline. This is the output. And when we render the clouds, we just swap that with display 2, and we can go ahead and run this. And our clouds no longer have the outline. So it's just the actual foreground stuff that has the outline, which looks really nice. And the sparks also have the outline and the projectiles, but if you notice, the particles do not. And it's important because the particles are already black themselves, so you don't want to mix it in there. Otherwise it'll look funny. The particles will be weird shapes. So it's better if you just don't do the outlines on them. It doesn't look out of place, like I said, because they're black, so that's convenient. All right, we have ourselves our nice outline effect. There's lots of different things you can do with masks as well that are quite fun. I recommend playing with this thing as well to try to figure out and understand fully how it works if you don't quite understand. Like I mentioned, there's a lot of stuff you can do with masks. If you look through my games, you can see me doing all sorts of random things with it. It's just a nice graphical tool. I think in Pygame, one of the best uses, which funny enough is not what they're, I think, usually used for. One of the best uses is to actually just compress an image down into 2 colors so you can do some type of thing. But one of the more common use cases is to do intersections with masks for pixel perfect collision. They allow for binary operations where you can say, if this mask is set in a location and this other one is, then it'll be set. So that way, if you have like a player's mask and an entity's mask, you can check for a pixel perfect collision by overlapping them and seeing where they're both set. And there's all sorts of stuff you can do that people use them for, but this is an interesting graphical trick. This is making use of just Pygame's abstraction for them for how it can efficiently convert this into a surface. There are ways to do this by hand, or not by hand, manually, where you're setting pixels, and it would be super slow. So this is just the fast way to do it. All right, that's pretty much it for the outlines though. Okay, we're in the final stretch here. The last thing that I wanted to add to this game before I would say we're done is to add the sound effects and music. So for the sound effects, it's going to be pretty simple. We just do self.sfx equals jump pygame.mixer.sound. So this is how you load a sound in Pygame. You just do pygame.mixer.sound, and then you just give a path to the sound. So we'll do data sfx jump.wave. And then we'll just go through and then do this for our different sounds. There's ways you can optimize this so that it's more extendable and takes less code, but I'm not going to worry about that because this is meant to be a simple example. So I'm just renaming all these and making sure we're loading all the things we need. So we have dash, hit, shoot, ambience, jump. Those are our sounds. So you could add more if you wanted. And then I'm going to tweak our sounds a little bit. So we're going to have self.sfx ambience.set volume 0.2, and we're going to go through all of them and adjust them. So these are just going to be constant values that determine how loud each sound should be when we play it. Normally, when you have sounds like this, they're not going to be quite at the right level for what you're expecting in the game. It's best for your sounds to be as loud as possible when you load them in, and then you just scale it down because you can't scale it up. So we'll do 0.4 for shoot and 0.8 for hit, so 1.0 is the max. We'll do 0.3 for dash and 0.7 for jump. So the quietest sound is going to be the ambience, the loudest sound is going to be when something is hit, and then the second loudest sound is going to be your jump. So we're just kind of organizing it like that. I've already gone through beforehand and make sure these values sound good, so you can mix it however you want. But that should cover the loading and configuration for our sounds. So I'm going to go ahead and add the music actually. So the music's going to be pretty simple. Let's go ahead down to run here. We'll do pygame.mixer.music.load. We'll do data music.wave. So for audio files in Pygame, there's quite a few supported technically, but some of them can have issues when you try to package the game into an executable. I know that I've had issues with OGG or OGG files, whatever you want to say. I've been meaning to look into it and figure out what the solution is to get this to work because they're a much smaller file size. But if you want things to work well, it's just best to have everything as a WAV file, and then Pygame works well with that, and then the packaging works well with that. I believe there's some restrictions on what can use different file types, so the music player and the sounds have different restrictions for what file types you can use, but you can look up the documentation to see that. They actually might be the same nowadays, I'm not sure. I know that there's some rules on the different operations you can do because, for example, I believe on MP3s there's some weird stuff with the way they're compressed that affect which types of things you can do it on it. So there's stuff for controlling playback, like you can fast forward and pause and play and do all sorts of stuff. So certain things might be restricted on certain formats and stuff like that. But all that's on the documentation, so you can look into that if you're interested. Anyways, so I just use waves for everything. If you're concerned about file size, you can look into some of the other solutions, but waves are high quality audio-wise, and then they run fine for most use cases, so that's usually my preference. All right, so we'll do music.set for volume. So this is the same as when we set the volume for the sound effects pretty much, except instead of it being a Pygame.mixer.sound object, we're calling it right here. So something interesting to notice is that we're doing music.load. So this is not outputting an object. This is actually just meant to be something where you can have one thing loaded for your music, and then we can set the volume for the one music thing, and we just do set volume 0.5, and then we'll do pygame.mixer.music.play. So in the play, there's a couple options here. You could see them right here if you want to look into them. But what we'll be doing is we'll be using -1. So whenever you play a sound or music in Pygame, the .play function can take a number, and that will be the number of loops you want. So if you say 0, it doesn't loop at all. If you say 1, it'll loop once. If you say -1, it'll loop forever. And that's what you want for music. And the other thing we want this on is the ambient. So we'll do self.sfxambient.play -1. So if I run this, you should hopefully be able to hear it. So there's music playing, and you can hear some birds, which is nice. Hopefully I got the mixing right. We'll see when I'm editing this later. Not that I can change it at this point. But there's the ambience and the music. The next step is to add the rest of the sound effects that we have here. So we have a few of them. We can just look at them, and this is normally how I make games. I go through and add the sound effects at the end. But you can just look through here and kind of add them based on what they're associated with. So like shoot, for example, is pretty easy. You just grab this. So this points to the sound object, and similar to the music thing, you just do .play on it. We also did that with the ambience right here. So anyways, we just got to find the shooting code, which we know is over in entities. And if we go and find the enemy and find where it spawns the projectile, which is right here, we can play the sound. So we just go right here, we do self.game.sfx.shoot.play, and that will cover what we need for that. And we also have a jump function, so we can actually go down here into, where is it, jump. And well, this is a bit messy. So we have return true. So there's a couple ways we can do this. We could drop it in all these 3 cases for jumps, or we can do it the hacky way and go over to here and say, hey, we call jump. We had that whole thing where we return true, so we know if the jump actually went through or not. So we can say if that went through, then we can just do self.sfxjump.play. And now we have the hit sound. So for the hit sound, that'll be for 2 things actually. So the enemies can get hit and the player can get hit. So for the enemies, that's right here. So we just drop that and we just grab hit, we play that. And then the other thing is when the player gets hit, and that one's over in the projectile code in the game. So if we go over here, this is the projectile loop. We find where it kills the player, which is right here. We drop this, we say shoot, we say play. And then we have a couple more things, I think. We have dash. Actually, I think this is the last one. So dash is pretty easy. So if we look over here, we have our dash function. So this one doesn't return anything. So we can just drop it here. We could add a return here and do it similar to the jump if we wanted, or we can drop it right here. It doesn't matter at this point. So we'll just say dash.play, and that should cover all of our sounds. So let's just run the game and see how this goes. So you can hear me jumping. It's a nice boop sound. If I dash, you can hear me dash, which is cool. And let's see. When he shoots, you can probably hear it. Sounds like someone just hit a tennis ball. All right, so if I dash through him, you can hear the hit. Or if I get shot. Shoot. Oh, that just crashes. That's gotta be fixed. So that's just, go over to here. This should not be self.game. That should be self.sfx. And that should fix that. So let's just test that case real quick. And, wait, that was shoot. That should be hit. Okay, there we go. Let's see. We should have it now. There we go. All good. So all the sound effects are in. So the game is technically complete, but there's one last thing we need to do. The last thing that I wanted to do was to make this game into an executable. With Python, we call this packaging. For things like C++, you might call it compiling, but technically with Python, what's happening is that we're taking the Python interpreter, which interprets Python code, and then bundling that into an executable with the Python code. So that way you run the executable and it runs the interpreter and then it runs the Python code. So that's how that ends up working. So the executables kind of have a minimum size based on how much stuff you're including and also however big the Python interpreter is. So I think the bottom end of it is like 20, 30 megabytes or something. And then it'll grow depending on how much you're including. All right. So to get started with this, let's open up a command line. So you can just do Windows key cmd. We've done this before to install Pygame. So it could be your terminal, your command prompt. You could even put PowerShell if you wanted and do it there, but I'll do it in cmd. And we'll just do py-m pip, so it's the same as when we installed Pygame. So whatever pip is for you, and then we'll do install, and it'll be PyInstaller. Make sure you get the casing right on this. It's capital P, capital I, no spaces. And then I already have it. So I'm going to go to navigate to my game. So I'm gonna go desktop. It's gonna be different for you, obviously, but just navigate to the folder where your game is. For me, this is going to be Ninja Game. And if I do dir here, you can see all my stuff. So this is the same as what I have here on the left. And if I go ahead and do py-m PyInstaller, depending on how PyInstaller installed, you might be able to just type PyInstaller. But for me, I have to do py-m PyInstaller because PyInstaller is its own module. I mean, we just installed it, so yeah, it's its own module. Sometimes it'll be bound to just PyInstaller, so you could just type PyInstaller. But we do this, and then we have to say the name of the main script that we're running. So in our case, the script that we run to run the game is game.py. So we just do game.py, and this would create the executable. But there's extra arguments you can add here. So there's like stuff for adding icons and stuff like that. There's an icon thing, I believe, in Pygame as well. And then there's the icon that shows up on your taskbar on Windows. I think on different operating systems, what has control over what parts varies. So I think on Windows, that's how it's split, where I think Pygame controls the top left icon on the window, and then on the taskbar, it's based on the executable. But then I think on Linux, it might be, I can't remember if the packaging has full control over it or if Pygame does, but I think it varies by operating system. So if you want to get the icon correct, you would have to do both of those, so you can look into that if you want. So there's an argument for that in PyInstaller. We won't mess with that because we don't have an icon for this game. But there's two arguments that I commonly use. So one of them is no console. So normally if you don't use this and you run the executable, you'll get a window that pops up. It's the console output for the game. So you know how we have this console down here where, I mean, we could print out whatever we wanted and we would see it in our output down here. So it would create a command prompt window, or actually not technically command prompt, but like some kind of shell window where you can see the output of the game. So if you don't want that, and you don't want the users to see that extra window in the output, I know a lot of people get confused by it. Most games don't have something like that. So you would just do one file no console to get rid of it. And the other argument is one file, the thing I accidentally just typed. So one file will make the whole thing one file. The big thing is that it gets rid of all of the files that Python generates because of it having to include the interpreter and all the packages and everything. So it'll generate like, I don't know, 50 files at a top level, and then there's hundreds or thousands of files lower down that you could dig through that are just all over the place and it looks really messy. But the problem with one file is that the people over at Microsoft have still not dealt with an issue on Windows where Windows will flag things made with PyInstaller as a virus because people make too many viruses with PyInstaller. So PyInstaller is really popular for, I mean, just making any type of executable from any type of Python thing. So because Python is also one of the most common things used for making viruses, people are usually making their viruses and then packaging them with PyInstaller. So PyInstaller, especially if you do one file, has some very specific things like that kind of identify the executable. It's not intended to identify the executable, but there's certain things that it just kind of tends to put in there because they're packaged the same way that will show up in those viruses for like just the data for that executable. And then anything else you make with PyInstaller that might not be malicious, so in our case, our game. So the people at Microsoft have not figured out that they're hooking off of the stuff that's in stuff made by PyInstaller to detect viruses, which, I mean, to be fair, I guess it does detect a lot of stuff that is made with PyInstaller without them having to recognize it, but it catches a ton of other stuff too. So anything made with one file will fall under that pretty much. So you can remove that. And then because people don't generally make viruses where there's like 50 other files and it has to be in a zip folder and everything, Because people don't typically do that, I think coincidentally that whatever that signature is that they're hooking off of from the way that PyInstaller makes things is no longer there. And because the executable is smaller, Windows doesn't freak out as much. Sometimes it still does, because I guess maybe some people are still making viruses like this. But this is the better way to avoid Windows freaking out when people download your game and try to play it. So basically you can use one file if you want it to be one file. Otherwise don't. Either way, this technically doesn't include all of your assets. So a lot of your extra files, so like your images and stuff, aren't included in this. So what you would have to do is you copy them over either way to whatever your output is. But I'm pretty sure there are ways that you can also include other data like images and stuff so that you can properly make the whole thing one executable. So depending on what you're doing, you might want to do that. It's just good to know about. But in our case, because if we ever want other people to play this, we probably don't want them getting as many virus warnings. They'll still get them because that's just how PyInstaller is. You can do this. And if you really want to get rid of those warnings, one option is, I think, to pay for a certificate with, I don't know if it's with Microsoft or some other organization, to basically prove that your executable is not a virus. I don't bother doing that. And then the other option is that there's some weird tricks you can use with PyInstaller for how it builds things to get it so that it builds it in such a way that it doesn't cause that issue, but it's very difficult for mine, so I don't want to get into the explanation. Or not necessarily very difficult, but it's a bit confusing. Anyways, something else to note is that if you're releasing on Steam, Steam just takes the executable, or actually all of your files, and then you tell it which executable the game should run when they click play. And because Steam itself is just calling the, I guess, the command line or terminal arguments or whatever to run that executable, the Windows warning never pops up. So no matter how you do this, it doesn't matter if you're releasing it out for something like Steam, they're not going to see any virus warning. So this really doesn't matter too much if you're doing something like releasing it on Steam. But let's go ahead and run this, and this will generate our executable. It can take a moment. And while I'm sitting here, something else to mention is that PyInstaller actually works on a bunch of different platforms. So it works on Linux, and it's supposed to work on Mac OS. It's supposed to use the same arguments for them, but I've had some issues on Mac OS. I know I tried with I don't know, maybe it's like a 2008 MacBook, which is like 15 years old now, and I tried that, I don't know, like 5 years ago when PyInstaller wasn't as popular, and I had a lot of issues with it. I don't know if it's fixed now, so I don't know. You can try that and see if that's working. I'm pretty sure it works now, so it should be mostly cross-platform. Not that your executable's cross-platform, but you can build it on multiple platforms. And the way that works is that if you want to build it for a specific platform, you have to be on the platform you're building for. So if you want a Windows executable, you got to be on Windows. If you want an executable for Mac OS, you got to be on a Mac. If you want something for Linux, you got to be on Linux when you run this. So it's kind of a bit of a mess. And just one extra tip for those of you who are considering releasing something on Steam. I don't know if this is still the case, but I know when I released something in like 2018 and 2019, they had a requirement for all Linux games that they had to run on Steam OS, which is the operating system for Steam Machine, which was released a long time ago, and they were still requiring that people supported that in order to say that they supported Linux, even though almost no one uses the Steam Machine nowadays. And that was running on, what was it? I think it's over a decade old, maybe coming towards 15 years old version of Debian, which has some very different requirements for how things run. So if you want it to work on that, you might have to get a really old version of Linux to build on for this to pass Steam's requirements for what counts as Linux supporting. That was a bit of a headache for me. Anyways, we should have our executable built. If we go over to the game folder, we'll see that we have a couple new folders here. We have build and dist. So just ignore build, that's just where a bunch of the build files are. We don't need these. This exe doesn't work on its own. So what we need to do is we actually go over to dist. I think it's for distribution. And there's a game folder here. This folder is actually named after, I think, whatever the name of the Python file you gave it is. And then here's where everything is. So this has all sorts of stuff in it. So these DLLs that I think Pygame's using, and we have like Python stuff. So here's the Python DLLs for the running the game or interpreting the code. And we have like Pygame, NumPy, OpenGL, etc. There's all sorts of stuff in here. Anyways, the thing we want is game.exe, but if we run this, it crashes and says, blah, 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 can't find this, can't find the decor. So it's trying to load the decor and can't find it. So what you gotta do is you go over to your game and you grab the data and scripts. You don't actually have to grab scripts, but I grab them anyways. And just anything that the game's dependent on. So in our case, it's data and scripts. We're not using map.json anymore, but if we were, we would have to grab that too. But let's grab these two. I'm gonna copy them both. And then let's go over to game, same folder as this executable, because you treat this game.exe like game.py, and you just drop them in here. So the paths need to be the same. So if we refresh now, we have data now, which has all of our stuff in it. And then we also have our scripts, which are there if you want them. Depending on what you're doing, you might have put something in scripts that you might need. So it's worth just throwing in there. All right, so let's go ahead and run our game. And it runs fine. And this is the executable, not the Python script. So this will run even if someone doesn't have Python. So some common issues that can occur are, well, first of all, sometimes there's issues with PyInstaller just installing to begin with. If you have those, you're just gonna have to look it up and try to figure it out. There's all sorts of things that could happen. And then there's random issues that can happen during the build process, which is also usually related to your install, unless you have some weird arguments. And then the last thing that's most common is when you run the game if it crashes. And so a couple things that can happen here that you can watch out for are fonts. So I don't know if it's still an issue. I know at least it used to be that the system fonts in Pygame did not work in PyInstaller. Another thing, as I mentioned before, is the audio files. So if you use an OGG file, a lot of times it'll cause crashes as well. So there's just stuff to be careful about. And then there's also the whole missing resources thing. It used to be that, and I think sometimes it still does this, it depends on the circumstances, it will just say like failed to execute script and won't give you the information you need, as opposed to doing that thing we just saw here a moment ago where it gives you the whole crash output so you can debug it. If it says failed to execute script, sometimes you can open up a command line, navigate to the executable, and run it from there by just typing the name of the executable. And then if you get that crash, it'll show the output here. I think that's more common if you do one file, is when you would have to do that to see your issues. Anyways, so we have our game here. Let's go ahead and beat it, because we might as well, since we just finished it. And it's an executable for everyone to play. So I'm just going to run through the levels here. So just gotta beat all the enemies, dash through them, don't get shot. Pretty simple. I haven't done this a bunch of times already because I tested this plenty of times while I was initially making this before I did the tutorial. And fun fact, this tutorial's been recorded over the span of, I don't know, 50-something days. And I made this base game a very, well, not a very long time ago, but a while ago. I just messed up. So this one's the last level, it's a bit trickier. So you gotta actually jump over stuff and try to dodge things. You can move right after you spawn, which is an issue that could be fixed, but it's not that big of an issue, so I'll eventually figure this out. A bit harder than I remember. I think the trick is to go right first, but okay, we got those guys, that's the hard ones. There we go. Let's try to not mess it up this time. Alright, there we go. So now there's this little island down here with a couple guys on it. And we have these guys over here. And we just got get a good dash over on these guys on our left here. There we go, we did it. And if you notice, like what I mentioned before, it loops back, well, it doesn't loop back, it caps it at this third level and you can't go past it. It'll just restart it when you beat it, because that's the last level. So you could add more if you wanted. All right, so the last thing I'll mention is that you can go over to here and send this to a zip folder. And that could be like your game, for example. and you could call this like ninja game. So another thing is that, for example, this executable is a bit hard to find for users. So you extract it, you see this mess in here, and you're like, where's the game? So this is the game. I mean, you could rename it to help make it easier to find. Another thing you can do is create a batch script in this folder that executes this executable, so that you can see it'll be like just a folder called like the name of your game or something, and then there's an batch script right here that you could just double click to run the game. If you look at my games, that's how I've got it set up, at least in the more recent ones, so you can go see how that's set up if you want to use that, but I won't teach you about batch scripting here. So that's pretty much everything for just creating something they can share with others, and that's pretty much everything for creating the game. Congrats on reaching the end of this 7-hour tutorial. Hopefully this is just the beginning for you, and if so, you may be wondering what some next steps may look like. The next steps will depend a lot on your skill level at this point. For some, you may have some ideas already for how you could make games at this point without having to depend heavily on tutorials. If so, I recommend you do that, since that's one of the best ways to solidify your knowledge. If you're feeling a bit daring, you could consider participating in a game jam like the Ludum Dare, the Alakajam, or Game Maker's Toolkit. Game jams are a great way to get used to the game development process from the idea to the release stage, and I recommend participating as soon as you think you're able. For those of you who aren't yet ready to make games on your own, don't worry. This is actually the norm when you first start, and is commonly referred to as tutorial hell. It's defined by the absolute dependency on tutorials, and in order to get out of it, you have to focus on developing your problem-solving skills so that you can take what you have learned and generalize it into other solutions. This is the essence of what makes an engineer an engineer. In fact, I believe that for most people, you only have to learn the skill once, and if you switch to a different skill altogether, even if it's not even related to computers, you'll learn very quickly. You can improve your ability to generalize concepts best by picking apart things that work and making minor changes to both see what those changes do and to see if you can turn it into something else. Additionally, a sample of one is often not enough to see the abundance of different ways concepts can be used, so it doesn't hurt to check out a few more tutorials if you're still struggling. Don't focus too hard on just Pygame either. Oftentimes people aren't actually stuck with Pygame, and instead they need to learn more about Python or programming. Pygame itself is pretty simple, and there's not too much to learn in terms of its actual functions. It's all about how you take those limited tools and build something with it. There are plenty of functions that Pygame has that I didn't mention in this tutorial, but aside from maybe rotations and text, they aren't really essential. If you want to learn about a few more functions Pygame does provide, or some interesting techniques, you can check out my amateur or advanced Pygame tutorial playlists. Alright, that's all I have to add. If you just sat through the full 7 hours and you learned something useful, I'd think that'd be worth clicking subscribe for. This tutorial took quite a bit of time to make. I put out usually rather advanced Pygame related content all the time, so there's tons of other interesting stuff on my channel. Anyways, thanks for watching, and good luck on your game dev journey.